Hello, everyone. Welcome to the Graduate School of SGP 2022. I'm Ruijun Hu, and with Giselle Chanel, we are chairing this year's graduate school. The goal of the graduate school is to give a primer into the topics to young researchers in the field, but also to compile a repository of lecture materials over years. This year, we have topics ranging from character animation, morphable face models, geometric deep learning, there's something wrong. Okay, sorry, there is something wrong. So this year we have topics ranging from character animation, morphable face models, geometric deep learning, geometric computing, and high order mesh generation. Moreover, there is also a dataset and software session to introduce several top quality datasets to stimulate related studies, as well as to guide beginners to use Blender for beautiful figure generation. During the following 2 days, you will be able to follow the courses on Zoom, and each course will have a Q&A session at the end. Please join the SGP Discord to ask questions. And after the graduate school ends, videos of all the courses will be made freely available on the website shown here. We thank all the speakers for making the effort for this event and hope you will enjoy the lectures and the discussions. Now let's start our first tutorial. Taku, please share your screen. The first tutorial will be character animation given by Taku Komura from the University of Hong Kong.
Hello, can you hear me?
Yes.
Yeah, good. Okay, I will now share my screen. Let me share the screen I want to show. Okay, yeah, you can see it now?
Yes.
Okay. So let me start then. Okay. So shall I start? Or? Okay. Hello, everybody. Thanks for coming to this lecture. Today I talk about character animation. And so my name is Taku Komura. Thanks, Regent, for the introduction. And so I'm a professor in computer graphics in the University of Hong Kong. And just to introduce myself, I previously worked in the University of Edinburgh as a professor. And before that, I was working at City University of Hong Kong and also RIKEN in Japan. And so I obtained my PhD in University of Tokyo in year 2000. I've been working on this kind of character animation and physical simulation, robotics, and also biomechanics as well. Okay. And just to introduce some of our work in, some work on our group, we also do some kind of a cloth simulation type of projects now using, this IPC method for simulating the collisions between the cloth and the body, and also self collisions. You can see this kind of wrinkles can be nicely generated. And also we work for facial animation, 3D face motion from speech. So I think probably I should have enabled the sound. So I think you cannot hear the sound now. But basically what happens is that given the speech, we can like animate the face of the character. Okay. And so that's well, and another thing that we have been working on is like the interaction of the human body with 3D objects. So you can see here that the characters like interacting with these 3D objects that like we can like specify which object that the character should interact with, and then the character automatically moves towards it and then interacts with it. Yeah. And also, we recently produced some framework for animating this kind of a dancing motion, given the music. Sorry, I think you cannot hear the sound of the music, but basically, given this music, the character is going to like automatically be animated to produce, follow the music. Yeah. And so we have like several positions for PhD and postdocs. So like please feel free to apply. We are funded by various companies and also by the funding body in Hong Kong. Okay. And so for today's topic, so if we talk about character animation, so this is a image snapshot from the Shrek 3 movie. And you can see in this single image, there are already many topics that are related to character animation. So we first talk about like this full body motion. So we need to generate the realistic movements of the full body. And also, we also need to do the spatial animation. I don't cover that, but I think in the next lecture it will be covered. And there are also like hand movements that we need to generate for especially like interacting with 3D objects, like grasping this kind of like a bottle. And also we wish to like generate realistic crowd movements. Yeah. And finally, there's also topics like skinning and clothing. But today I don't talk so much about that. So basically, the topics that I covered today are like the full body motion synthesis and the crowd animation, and also like the hand motion synthesis. Okay. And because this is a lecture, I talk about some basic topics. I hope it's not too boring to you. And when we want to talk about like this full body motion synthesis, what we usually do is that we synthesize the motion of the skeleton. Yeah. So even though we have like a nice high resolution mesh of the character, we basically control the skeleton. And then the skeleton, the mesh is going to follow the movements of the skeleton. Yeah. So this is the skinning problem. Okay, so what we only need to worry about is how to control the skeleton for the full body motion synthesis. Yeah. And so this kind of like a body has a hierarchical structure like you see over here. So it is composed of like a number of rigid bones which are connected at the joints. Yeah. And there are different types of joints, including like this kind of like a translation joint and like hinge joint, a universal joint, and like a 3 degrees of freedom gimbal joint or the ball joints. Yeah. So these are like this kind of like a hinge joint is good for modeling the knees and the elbows, and this kind of a universal joint good for the wrist joint. Also, like these 3 degrees of freedom joints useful for like the shoulder and the hip joints modeling. Okay, and so given all these kind of like joints, okay, so when the character does make a different pose, then there's going to be like different joint angles at each of these joints. We're going to like concatenate all these degrees of freedom of these joints into a single long vector, which is called this generalized coordinates, which is representing the pose of the character. Yeah. And so if we want to animate the character doing different kind of movements, we need to like generate a series of these vectors that is representing the motion. Okay. And so for producing this kind of like a motion of the character, full body motion, there can be like roughly these 3 different methods. So the first one is like this keyframe animation, and second one is the physical simulation, and third one is the motion capture. Okay, so let's have a look at each of these topics a bit. And so keyframe animation is a classic technique for animating these kind of like a full body characters. And what we do is that if we want to like generate this kind of like a nice jumping motion, what we do is that we're going to design the poses of the character. If we design the poses of the character one by one, it's going to be a huge amount of effort because there are many frames for animation. Yeah, so instead of doing that, what we do is that we are going to like pick up some representative poses of during this jumping motion and then just design these keyframes. Yeah, so these are called the keyframes, and then do an interpolation between these frames. Yeah, and so this is a very manual process. But for like designing these keyframes, we can use something called this inverse kinematics demo that this is made by one of my student, Sebastian. And so like you can see how we can have like this kind of a tool where we can like drag the bodies or like, the direction that the character is facing, and then generate different poses of the character. Yeah. And so using this kind of like an inverse kinematic, tools, we can design the keyframes and then interpolate between them. Okay. And so this is a demo video that I found on the web designed by this James Refus Moscardo. So this is like a really nice looking keyframe animation. So even though it's like a manually designed, you can see it looks very artistic and nice. Yeah, actually, I think we cannot generate this kind of a nice looking artistic movements by the motion capture. Okay. And so you can see that, this is very nice and good. Lots of movies, films use this kind of approach for designing the motion, but at the same time, you can notice it's very time consuming and costly. Yeah, you need to have very good expertise for designing this and also a lot of effort for making the movie. Okay, and so that what we wish to do is that we want to like reduce this kind of like a cost, and so another approach that we can use is using this kind of physically based animation. Yeah, so this is Newton's laws of physics. So assuming that this Q is again this generalized coordinates I mentioned before. Yeah, so what we want to do is that we want to like control the character by using this equation. Okay, and so Q is the generalized coordinates, and so the Q is the original is this posture, Q dot is the velocity, and Q double dot is the acceleration. Yeah, so we want to like generate the motion of the character through this forward dynamics pipeline. So what we do is that we are going to give this torque. This is like the torques at the joints. So these are going to be like the torques made by the muscles. And then we are going to like calculate the acceleration of the joints. Yeah. And using these accelerations, we're going to do some time integration to calculate the velocity and then calculate the joint angles. Yeah, so we are going to update the joint angles at every frame. So we do this every frame. So we keep on specifying the torques at the joints at every frame, and then we need to synthesize these series of movements. Yeah. So this is how things go in this kind of physical simulation. Yeah. And so we can like generate passive motion as well as voluntary motion. So let's look at this. So the passive motions are the motions where we are not like producing any active torques at the joints or muscle forces at the joints. So this is called also called ragdoll physics. Yeah. So this is rather simple because you don't need to control. What you need to do is that you just need to like let the physical equation generate the motion given these kind of external forces. Yeah. So this is a movie that was generated by this company Animats, which were in the late 90s. So you can see that this kind of animations is simple in sense that you don't need to actively control the character. You just need to add some kind of external forces to the body and then see how the body behaves. Yeah, so it's like a ragdoll. So it's rather simple. On the other hand, for computer animation, of course, we want to produce some voluntary motions where the character is actively producing torques at the joints. Yeah. So these motions like walking, running, or reaching out, or all kinds of active movements by the character, they are voluntary motions. And so for producing such kind of movements, we need to like exert force by the muscles or, generate torques at the joints. Okay. But this is not such an easy problem, yeah, because we usually we know how the body is moving, but we don't know how the muscles are activated for producing these kind of movements usually. Okay, and so we need to follow this laws of physics for doing that, but that's not very easy. So people have been using PD control for doing this. So PD control is a method that is used in robotics, and the idea is pretty simple. Okay, so what you do is that basically you specify some kind of a desired pose. Yeah, so you have the current pose, which is the Q, and then you specify this desired pose, which is this QD. Yeah, we also have the desired velocity, this QD dot. Yeah, and so what we do is that we compare the current state of the character with the desired state. Yeah, so assuming we have like this kind of a two-arm robot, and so the current state of this robot is like this, yeah. And say we have this desired state, which is like this upright posture. So what we do is that we are going to calculate the difference of the current pose and the desired pose. So we do this for both the joint angles and the joint velocities. And then we are going to add torques to the joints such that this difference is going to be minimized, yeah, is going to be just decreased. Yeah, so we set up this kind of a rule, this PD control equations for calculating the torques, yeah. So what it does is that basically, if the difference between the desired pose and the current pose is large, then there's going to be more torque added to the joints to approach to this target pose, yeah. And so, so once this character reaches this target pose or the desired pose, then there's not going to be any torque added to the joints. Yeah. So that's the idea of this PD control. And so if we want to like generate this kind of like a walking motion, so what we do is that we are going to prepare a series of these kind of target poses, So what we do is that given the current pose, we are going to specify this target pose, and then the body is going to be exerting torque to approach to this target pose. Once we are close enough to this target pose, we're going to switch the target pose to the next pose, yeah? And then there's going to be, again, torque added to the joints to approach to this next pose. And then once we are close again, we are going to switch the target pose to another pose, yeah? So we can keep on doing this, and so we can prepare a number of poses for like generating this kind of like a cyclic locomotion. And then we will be able to like generate this kind of a walking motion in the physics-based animation. Okay, and so that's how people have been working on this. So this is a movie by Nancy Pollard and Jessica Hodgins in '97. So you can see that they proposed a method for like generating this kind of a running motion of this character. Okay. And so, that's a very nice. And well, so this is great. So now we can like generate this kind of a complex motion by using the laws of physics. That's good, but actually, it's not so easy. Yeah. So there's so there are a lot of parameters that we need to set. So this target poses and also these PD gains. The PD gains are these A and C's. Yeah, so these gains are the coefficients that we multiply to the differences of the current pose and the target pose. Yeah, and to compute the torque. Okay, so if so we need to like specify all these parameters for animating the character nicely, and this is not very easy. So for example, if the PD gains are too large, then the motion is going to appear too rigid, and if it's too small, it cannot follow the motion well. Okay, and it appears more smooth and soft, but it doesn't follow the motion well. And also, like another big problem is that there's no actuator for the body center. Yeah, so all the joints of the body, they have like you can like do this PD control to them, but for the body center, which is the root of the body, there's no actuation. Yeah, so for keeping the balance, actually, we need to like make sure that the center of mass is well above the support region of the body. So this is actually the difficult problem. So lots of people have been working on this after this Hodgins and Pollard's paper. Okay, and Anyway, so then let's go to the last method for generating these movements, which is like using the motion capture. Yeah. So motion capture is a device that is used for like digitizing the real human motion. So we can have like a lots of cameras set up in the room and then put some reflective markers on the body. And then the markers can like be tracked by these kind of like the cameras, and they do stereo vision to reconstruct the 3D motion. Yeah, so this is called the optical motion capture system. Yeah, so lots of people in the world use this, and actually this optical motion capture is, I think this is the most popular approach for capturing movements, thanks to its robustness and accuracy. There are other motion capture devices like the magnetic motion capture or the inertia-based motion capture or video-based motion capture. These are also very good. So like the video-based motion capture is actually an active research topic in computer vision, and so these are also getting much better and better. And but for now, we often use this kind of optical motion capture. Actually, they're very reliable now. So you can see that there are like lots of markers of multiple bodies, people interacting with one another, and still the system can like predict the skeletal movements of each of these characters well. Yeah, so that's very nice. Okay, and so that's great. Also, there's inertia-based motion capture made by this company XSense is also pretty popular and good now. So you can see that the advantage of this inertia-based system is that it doesn't have any capture volume. So you can like do the motion capture in a open space like outside, and like you can like do walking and running in a large open area and track the motion well. So this is also very, very good. Okay. And so that's how we can capture the motion. But even though we capture the motion, in many cases we don't want to just replay the captured motion, but maybe we want to like control the character, in an interactive fashion, say for like computer games. Yeah, so maybe we want to use like interfaces like game pads or the mouse to control the character in arbitrary fashions. Yeah. And so for that purpose, what people have been doing is that they capture a large amount of human motion capture data, and then, construct this kind of like a state machine called the motion graph. Yeah. So the motion graph is like, is a graph structure where each of these, edges represents like the motion transitions, and also these nodes representing like the short motion clips. And then, as far as we are like traversing along this graph, we can continuously generate some emotions that we wish to see. Yeah, so all the motions are also labeled. So they're like dancing motion, punching motion, or ducking motion. And we can like, traverse along these graphs to generate a series of movements that is following the user instruction. So that's very nice. Yeah. So this kind of like a method was going on for a long time. Actually, it's also going on now. But the one of the main problem is that we need to like nicely segment the motion and then label them and then align them and like generate a nice compact graph structure. This part is difficult, so automatically generating the graph is possible, but usually the graph structure is not very good. And then if there are lots of unnecessary transitions happening, then it's not very easy. So we need to like manually tune it to produce a nice structure. So that's how people have been working on this. And but recently people have started to do transition to like methods like this motion matching or deep neural networks or physically based motion tracking. So let's have a look at these methods. Yeah. So motion matching is a technique that is developed by Ubisoft Montreal, and it's a method that is based on nearest neighbor search. Yeah. So given the current state of the character and also like the user instructions, which is like the direction that we want the character to move towards, the system searches in the whole motion database that matches to this this current pose and the desired direction. Yeah. And so And then once the motion is discovered, okay, then we are going to import it and then blend it to the current pose of the character. Yeah. So this is a very simple approach. Yeah. So you just need to do this nearest neighbor search. So it's not very complicated. Okay. And actually, so let's have a look at this video that is describing this, this motion matching method. So you can like, so given all these different poses, the system can, search for the next pose that can be, following the current pose. Yes. Okay, so that's how it is going. And this motion matching is actually it's very simple, but it's used a lot. Yeah, so I think lots of games are using this motion matching nowadays because it's simple and like you can like animate nice realistic movements. Yeah. And so the quality of the motion is always good because it's actually replaying the original motion capture data. Yeah, so that's the quality is assured. Yeah. And also it's also like you don't need to do any training. Actually, you just need to keep on adding motions into the database if you have some extra motion that you want to see. Okay, so that's also useful. You don't need to do like a long training process like deep learning. Okay, so the disadvantage is that because it's a nearest neighbor search, the search time can grow as the data size increases. And also the features for the matching, it must be carefully selected. Otherwise, you might, if the feature is bad, actually, you might see some kind of a foot sliding kind of artifacts appearing because at the end you are doing some kind of like a motion blending. And the last thing is that well, maybe it's not a disadvantage, but it's like it's actually not generalizing anything. Yeah, so it's just replaying the motion in the database. So there's no like a newly generated motion, like mixing different parts of the body or blending between different movements. Yeah, so there's no generalization like that. Yeah. And so anyway, so that was the motion matching, and then another stream of research is this using this deep learning. And so deep learning is, I think most of you know about it more than me. And so it's like you can like learn a framework to learn from a large amount of data. Yeah. And it's been applying it for like speech synthesis and image synthesis, image recognition, and all kinds of applications. Yeah, it changed the society now. Yeah. And but it's also been applied for computer graphics and computer animation purposes. I think most of you know, as you are working on these geometry processing type of techniques. But so let me just go do a brief introduction. So like I think in computer graphics, like this kind of like a method by Iizuka was doing this kind of automatic colorization. I think this is one of the early works of this applying deep learning for computer graphics. So it's like adding, given this grayscale images, you can like color it automatically. And so these are done by using supervised learning. So given all these huge amount of the color images, you can grayscale the image and then do some kind of a regression. So this black box is trained so that given these kind of grayscale images, it's colored. Yeah. And so you can do this supervised learning for this case. Also, there are lots of research about like this kind of a classification. So you can have like a deep neural network that does the classification of these images. Also, there are like unsupervised learning approaches for like learning from a huge amount of face images. Yeah, so using like a huge amount of face images, we can like learn the space of faces, and then learn all these different axes of different aspects of faces synthesize a new face. Yeah, and so these deep learning approaches, it can learn from a lot of data and can automatically extract these important features, and also it's parallel friendly, can handle non-linearity, and it has a high compression rate and also fast data reproduction. So that's very good. Yeah. So we actually did this kind of like a motion, application of deep learning for motion synthesis and for like learning representation of motion, and also using that for synthesizing novel movements, and also like editing the motion in this subspace for like synthesizing realistic movements. And this is actually a work that we've done like 6-7 years ago, but I think there are some important aspects, so I wish to like introduce these here. Okay. So the motion data is here we are representing the body by these kind of like joint positions. So previously I was talking about the joint angles. Actually, we can do the learning by joint angles as well. But it's known that joint positions are easier to learn. So in the old days, we were always using this joint positions. Yeah. And so the joint positions are like all the joint positions of the joints of the body. And so say we have like 20 joints, then there's going to be like 60 degrees of freedom. Yeah. So it's 60 degrees of freedom for representing the full body pose. Okay. And actually, so learning the full 60 degrees of freedom is actually not so small. It's relatively large. Yeah. And so also like it's not like all these points in the 60 degrees of freedom is representing a nice looking pose. So there can be many constraints, like the distances between the joints and also like the joint angle limits. So the valid poses within this 60 degrees of freedom is not very huge. Yeah. So there's actually a subspace in this 60 degrees of freedom where the poses appear natural. Okay. And so let's call this motion manifold. Yeah. So there is going to be a motion manifold within this 60 degrees of freedom where the poses are appearing nice. So we wish to learn this kind of like this subspace, this motion manifold from the large motion capture database. Okay. So for this purpose, we can use the convolutional neural networks. Yeah. So I think like everybody knows about what the convolutional neural network is nowadays. And so it has been a great success for image classification and video classification, speech recognition, or whatsoever. But what we do here is that we are going to train this network by giving lots of images. Yeah. So given each image, there's going to be like a convolutional filter that is going to be sliding over the entire image. And these filters are convolved with the input image. Yeah. And then once the convolution is done, we will be able to generate this kind of like a feature map, yeah, that is generated by convolving the filter to the input image, yeah. And so we can make lots of these kind of different feature maps by applying different filters. And so then for each of these feature maps, then there's going to be, we do the same process. So there's going to be another convolutional filter involved with these feature maps to generate the feature map of the feature map. Yeah. And then we'll repeat this process. And finally, there's going to be like a fully connected layer for like doing some image classification. Yeah. So that's how people have been using this before in the old days. And once you do this kind of like training, so these filters, the convolutional filters, are going to be optimized to like do some kind of a recognition or synthesis of these different classes of objects. And so, for example, if it's like a face image, you train it with a face image. So the low-level features filters are going to be somewhat like edge filters, and then there will be filters representing different parts of the face, like the nose and the mouth and the ears. And so then at the highest level, there's going to be like filters representing the entire face. Yeah. And so the same for if we do it for the cars or elephants or chairs, then these kind of low level to high level features are going to be automatically learned. Okay. And so the thing is that we can do this for the motion capture data too. Yeah, so that's why I'm introducing this. Yeah, and in this case, for the human motion data, we were doing this kind of like an autoencoder thing. So given the motion of the character, we are going to do some kind of autoencoding, convolutional autoencoding to calculate the feature, the latent variables, and then we construct the full body motion by deconvolution. Yeah. And so that's what we can do. So we do this by this in the convolution in the temporal dimension. Yeah. So this is a temporal convolution filter. So given these kind of like poses of this character during the animation, then we are going to prepare this kind of like a temporal convolution filter. We are going to convolve it with the poses of the character and then slide it over time. Yeah. And then by doing this, each of these convolution, we can calculate the hidden units on the upper layer. Yeah. So and then that we can get all these the latent variables. And then we want to further decrease the dimension. So we're going to do some max pooling. So among these calculated, hidden values, unit values, we're going to like pick the maximum value of it and then, decrease it, the dimensionality to like you see over here. Yeah. And so then, so we need to do the deconvolution. So given these kind of like, the latent variables, we need to reconstruct the motion. So in that case, we're going to do this inverse pooling. We can like pick the maximum value, randomly pick the hidden units and copy the value there. And also we can also like do some interpolation between them to have like a smooth series of hidden variables. Yeah. And so we do this for like multiple layers. So this process of we do the convolution and then max pooling and convolution max pooling, we can do this for multiple layers and then get some the top level is going to be like the subspace for the human motion. Okay. And so like, for example, so this is like a motion capture data visualized in an image. Yeah. So you can see that, this is like the vertical axis is the degrees of freedom. Yeah. So you can see that it's like 60 degrees of freedom. Yeah. And so each of these are representing the coordinates of different parts of the body. Okay. And then this is the time. Yeah. So this is like the time of from 0 to like 150. And this is a motion like a raising, lifting the arms. Yeah, so you can see that the degrees of freedom corresponding to like these arms are like, getting higher at this region. Yeah, and then going back to the normal pose again. Okay. And so like using these convolutional filters, we apply the convolution filter, then it becomes like this. Yeah, so it's becoming sparse after applying these filters to the motion. Okay, and so we can like doing this procedure, we can like compute lots of filters that are necessary for reconstructing arbitrary types of movements. Okay, so you can see that all these filters are representing some type of movements of the body. Yeah. And so we can try to like combine them together to produce arbitrary movements. Okay. And so they are somewhat like the basis of the human motion. So if we visualize these filters, it becomes somewhat like this. Yeah. So you can see that in the left filter, you can see this arms are like swinging back and forth. So this is probably necessary for like this kind of a walking motion. And also like these filters in the middle, it's like you moving the knees inwards. Maybe it's necessary for some dancing motion. Also like here, there's some movements of the arms. Yeah. So each of these filters are somewhat like the building blocks of the full body motion. Yeah. And then we can like, use them for reconstructing arbitrary movements. And for now, okay, now let me show some simple applications of these filters. So of this subspace, so we can do something like the motion denoising. So given some kind of like a noisy pose, we can like try to like project these noisy pose or noisy motion onto the motion manifold to reconstruct a smooth natural motion. Also, we can do something like motion interpolation. So given these two different, different motions, we can like try to interpolate them on this motion manifold to generate some natural motion that appears realistic. Also, we can like use these you know, the feature maps for like searching similar movements and in the latent space. So here is an example of doing this kind of like motion filtering, denoising. So this is the noisy motion on the left, and the right motion is the ground truth motion, and the motion in the middle is the projected motion. So it's a denoised motion. So you can see that the noises are well you know, denoised. And so this is some kinect motion. So the kinect motion, you know, it's very noisy. But after like projecting onto this motion manifold, you can see the noises are somewhat removed. Yeah. And so you can do also things like what is it? Yeah, so this is like even some markers are missing, some joints are missing. We can project onto the motion manifold and reconstruct a natural looking motion. We can also like give some kind of like keyframes to the body, to the motion manifold, and then project it to reconstruct the natural movements. Yeah. Also, like so this is an example of like interpolating the push-up motion and walking motion. So if you just naively interpolate them, you get some weird motions like this. Yeah, so this is not realistic. But if we like do some interpolation in the motion manifold, then we will get something like some motion that is like mixing the bits of the push-ups and the walking motion. Yeah, so that looks a bit better. And finally, we can like do some kind of motion search. So like using these kind of like you know, using these hidden units, we can search for similar motions in the database. And so here is like given like this the ground character walking motion in the database. If we just like search in the database using the joint tables, then some strange walking motion can appear. But if we use the motion manifold, oh, sorry, where's the yeah. So by using the motion manifold, all the motions that are searched in the database will be like a natural looking walking motion. Okay. And so this motion manifold thing, so it's can be effectively, so we can learn some important bits of the motion, you know, by using this convolutional autoencoder. Okay. And so this you know, method scales well. So this CNN, I think you know that scales well. You can learn millions of images. Here we can also learn a large amount of motion capture data from this CMU motion capture database. So that's also good. And actually, this you know, this is representations useful for various applications, whereas especially this motion synthesis. Yeah, I talk more about this motion synthesis next. Okay, so that was the idea, the initial bits of like using this kind of like a temporal convolution for motion synthesis, and now let's think about like synthesizing motions that follows the instruction of the user. Okay. And so in the case that we want to like, you know, interactively generate the motion, so one simple approach is like you give some kind of high level instruction to synthesize the motion. So in this case, we can think of like drawing a line over the ground and then let the character run over this line. Yeah. And so this is a very simple interface that, you know, will be useful for the animators for guiding the characters. Yeah. And so if we want to do this using this large motion capture database, how do we do this? Yeah. So the easiest way to do it is like, so if we can use this deep learning approach for this, that will be great. Yeah. So what we can actually do is that for given all this locomotion or motion capture data of moving over the ground, we can like calculate this corresponding trajectory over the ground. Yeah. And so that will be like then there's going to be a correspondence between these lines over on the ground and the full body motion of the character. Okay. And so then we will be able to do some regression of this line on the ground to the full body motion of the character. Yeah, so that's the simple scenario. Yeah, so we just do some convolution. We apply what CNN for this, so we can use the convolutional network to regress this line over the ground to the full body motion. Yeah, and so we can like train these convolutional filters that slide over the ground, slide over the time, to like do this mapping from the line on the ground to the full body. Okay, that's very simple. Here I'm showing only one layer, but we can again put multiple layers in the middle to make the network more deeper. Okay, and so that's a very simple idea. So, but actually, if we do that, what happens is something like this. Yeah, so you can see that the body is somewhat like sliding over the ground and not producing realistic walking motion. So that's not very great. So why is this happening? So if you think about it, the problem is this ambiguity. So this ambiguity is a big problem in when doing this kind of like machine learning. Okay. So given this straight line on the ground, there can be like millions of ways that the person runs over this line, right? So it's a very, this doesn't have so much information. Yeah, so it's just telling where the body should be at each of these time points. Okay, and then there can be like millions of poses corresponding to each of these lines and points on the line. Yeah. And so there's too much ambiguity, and that if you just blindly train a network to like learn this kind of a mapping, and something like this is going to happen. So it's like arranging all the poses, and then it becomes like this. So not very great. So we need to first reduce the ambiguity. Yeah. So how do we reduce the ambiguity? And what we can do is that we can specify when the foot is on the ground. Yeah, so when the left and the right foot is on the ground, we can like specify this, and then there's going to be much less ambiguity. Okay, so for this purpose, what we need first do is that from the motion capture database, we try to calculate the foot velocity and height. Yeah, and then try to find out if the foot is on the ground or not. Yeah, so this process is rather automatic. It doesn't require too much effort. Yeah, so you can like prepare some kind of a function based on the foot and velocity, foot velocity and the foot height, to figure out, automatically label if the foot is on the ground or not. Yeah. And so you do this for both feet, yeah, and then do this for the entire motion capture database, and then we will be able to add this label to each of these frames. Okay, and so then, okay, now so the purpose was to generate this kind of like a the motion synthesis regression. Yeah, so we want to draw the line and then generate the character walking over or running over this line. So what we do is that, given this line, we are going to train a small neural network that predicts the frequency of this walking, and also like the contact duration. Okay, so in the training data, we can actually collect this data. So given all this foot contact information, we can find out the frequency of the foot stepping, and also like the duration that the foot is on the ground. So we can obtain this data. Yeah, and so we train a smaller network that predicts these variables given this line on the ground. So this line on the ground, actually, it's not only a line, but it also includes the timing information. So you know where the body is at which time. Yeah. So given this information, so you know whether the body's running fast or walking slow. Yeah. And so from this information, you can like predict this frequency of the locomotion, and also the duration that foot is on the ground. So these parameters can be extracted automatically from the motion capture database. Yeah, and then then we will have this small network that predicts given the line, we predict this block function that is representing when the foot is on the ground. Okay. And so that's what we do. So we have this original line input, yeah, which is on the right, yeah, so which is this parameters, and then we have a small network that predicts these this frequency and time duration that foot is on the ground, and give this as additional input into the network. Yeah, and then we do the regression to the full body motion. Okay, so that's what we can do here. Okay, and then actually then the system starts to work. Yeah, so you can see that the character is now like stepping. It's not sliding on the line anymore, but it's like doing some stepping and doing some natural looking walking motion. But when you watch it carefully, you can see that the feet is somewhat around here. The foot is like sliding over the ground, which doesn't look very natural. Yeah, so especially around this area, you can see that the foot is like sliding over the ground while moving, which is not very great. So we can like use this inverse kinematics that I mentioned in the beginning. Yeah, so which is used for like this keyframe animation to constrain the position of the foot. So then we can like try to keep the foot on the ground static. But on the other hand, because we are editing the pose frame by frame, there is going to be some discontinuity appearing, which is not very good. Yeah, again, around this region, you can see that there's a bit of a discontinuity happening. Yeah, so this is not very great. Okay, so what we can do here is that we can do some motion editing. Yeah, so but when we do the motion editing, not just editing the joint pose like by using inverse kinematics, but edit the motion in the hidden unit space, in the subspace of the human motion. So the motion in the subspace of the human motion, this is guaranteed to be appearing more natural because they are learned from the large motion capture database. So what we do here is that we can try to like constrain the foot on the ground in this subspace so that the motion appears realistic while also satisfying some constraints. Okay. And so that's what we can do here. Yeah. So what we do is that we're going to do some projection on or editing of the motion in this subspace of the human motion. Yeah. And so that's what we are going to do. Okay. And so when doing this, what constraint satisfaction problem. So what we do is that so we are going to like constrain the foot so that it's not sliding on the ground. Yeah. So this can be done by like constraining the velocity of the foot. Okay, to be 0 when it's like on the ground. Okay. And also when not only just moving, putting the foot onto the ground, but we also want the character to follow this trajectory. Yeah, so that was the original constraint. So we can add this extra constraint for the full body, the body root. Okay. And so what we changed the structure of the network. So previously we were just regressing to the full body motion at the end, but here we were going to change this part with the motion autoencoder. Yeah, so that was pre-trained, like using the method I described before. So we can generate this subspace of human motion capture, and then put this structure at the end of this network. Yeah. So when we are doing the regression from the line to the full body motion, it goes through this hidden units of the human motion. Okay. And so what we do is that we are going to do the optimization. We first give this line as the input, and then we do some kind of like a regression to calculate the motion. The computed motion, we are going to like do some editing again in this latent space so that these constraints that I just mentioned are satisfied. Yeah. So the foot must not slide over the ground, and like the body should follow this line that is drawn by the user. And then the motion becomes like this. Yeah, so you can see here the foot is not sliding over the ground anymore. It's well constrained, and also the continuity is preserved. Yeah, so that's what we can do. Okay. So you can see that we can follow, let the character follow these different lines nicely, and yeah, generate this kind of like a motion. Okay. Yes. And also we can like give constraints by like specifying the joint angles. So like, and you can generate this kind of like a punching motion and like, you know, kicking kind of motion as well. And so it's like somewhat like that. Yeah. So these are like the another possible like user instruction for controlling the body. Yeah, so you can also edit the walking motion by specifying these trajectories of the arms, like you see over here. Originally, it's like the just a raw running motion, but you can like make it to like grasp these kind of objects while running. And also like you can like change the end effector position to like make it like walking over some steps. Yeah. So that's one thing. And other thing that we can do is that we can also do some kind of like a, you know, stylization. Yeah. So this is like a neural stylization. I think this is a famous paper, so most of you know. But what you can do is that you given this kind of a content image, you can convert the image into this stylized image. Yeah. So this is a style image that you give, and then you can like convert this content image into this style. Yeah. So similarly for this kind of like this picture, you give this image as the input and then give this image as the style. You can convert this content image into this stylized image. Yeah. So that's actually we can do the same thing for the human motion. Yeah. So what we do here is that we want the hidden units to be like the hidden units, the same as the hidden units as the content image, which is this image. We want to the hidden units to be similar to the contents. And at the same time, we want this gram matrix of this hidden units. The gram matrix is actually the coactivation of different hidden units. You know, we want them to be similar to the stylized image. Yeah. So we can like try to optimize the hidden units so that they becomes the contents, you know, the values themselves are similar to the contents, but the gram matrix is similar to the style image. Yeah. And then so that's something that we can do. And we can like give this kind of like a zombie motion as a styled motion, and then convert this kind of a content walking motion into the stylized motion like you see over here. Yeah. And so like this kind of a old style motion as a style, then you can convert the walking motion into this old style walking motion. Yeah. Okay, and this is like a depressed motion. Now you can convert it the walking motion to the depressed motion. And what else? Yeah, so those are the things that we can do. Okay, so I was talking about this motion synthesis. So yeah, this content that I presented was a bit old, but there's an important message there where the main issue is the ambiguity in the future. Yeah, so the ambiguity is actually the problem that we suffer from a lot in this kind of a motion synthesis. And also like because given the high level inputs, you know, there can be many corresponding output motions, and then you know, the motion becomes smoothed out and looks bad. Yeah. So like it's always necessary to like somehow provide this kind of like information for reducing the ambiguity to like avoid this kind of a smoothing effect. Okay. And but actually there are other generative models nowadays like this motion VAE and the normalizing flow approach, which are like a sampling from the noise to reduce this kind of ambiguity. They also work pretty well. Okay. Especially this motion VAE is like used a lot also for computer vision purposes. So it's quite a valid approach. Yeah. And what am I okay with time? Is it fine?
Yes, yes.
So is it okay to continue?
Yes.
Okay. Yeah, so I think I talked nearly an hour or something, but so then now let's go to a different topic, this physically based control, you know. So actually physically based control is a very hot topic again. Yeah. So previously I was talking about this kind of like animating this character using the physics equations, and this PD gains and the target poses were difficult to manage. Also like the balance, keeping the balance was another difficult issue. So actually, now we can like decide these complex parameters using reinforcement learning. Yeah. So reinforcement learning, I hope you know about it well. But it's an online learning approach to compute the parameters that maximize the value function. Yeah, so each of the agents will explore and learn the set of action at each state that maximizes this value function. So we are going to define this reward. Actually, the reward is what we define, and so this is like what we want. What is like the objective function at every frame. So then we are going to like integrate this objective, this reward over time. And we want to like, so that's going to be this value function. So we want to have the character to move in such a way that it's going to maximize this integration of the reward over time. Okay, so that's actually a good method for this kind of physics-based motion synthesis. So what we can do is that we can set the reward to something like how well the body is following the motion capture data. Yeah, so now we can have like a motion capture data, and like we want to like minimize the difference of the simulated body and the motion capture data. Yeah, and we can define a reward like this and put this reward into the reinforcement learner to produce a controller, a policy for the full body motion. Okay, and so this is called this imitation reward. Actually, so this is what this Jason Peng was doing for this deep mimic. So using this deep mimic, now we can like simulate this character well to follow this reference motion capture data. Yeah, and so you can see that the motion is followed very well. Okay, and so that's great. Yeah, so this is. So now the previous, this difficulty of like producing this balanced motion is now simplified much more, so we can control the character to follow these reference motions well. And what is it? So the issue of this deep mimic was that we had to train a controller for each of these different motions. Yeah. So for each of this jumping motion, we need to train a jumping reinforcement learner for this motion to simulate the jumping motion. You cannot use this for the running. Yeah. So and also for the kicking motion, you need to have a kicking controller. You need to have a have individual controllers for these individual type of movements. So the scalability was an issue. And well, also like the motion appeared a bit, these videos looked good, but actually the motion looked a bit blocky sometimes. So because of the high gains that are used for the PD control. So, because by using this adversarial training, this adversarial training includes a reward that judges how likely the motion looks like the motion capture data. Yeah, so it's like trying to, we have a adversarial reward that is like evaluating how likely the motion is, the motion capture data. And this actually can improve the realism of the generated motion quite well. And so this is like their recent paper. So you can see that the motion looks very natural and realistic. Yeah. And so you can also like see this natural interaction between the body and these obstacles. Yeah, so looks very good. Yeah, and so and one of my students was working with Daniel Holden for this kind of like a motion tracking. Sorry, the video doesn't work for some reason, but that's this method is a supervised learning approach instead of using the reinforcement learning, and so it looks it's more scalable. Anyway, this physics-based animation, in summary, it's like the advantage is that you can synthesize novel motion by applying external force to the body. So this is good for like applications like computer games. So you can like produce novel movements from from the motion capture data. So you can like, it's not just replaying similar motions in the motion database, but you can like produce quite new situations. using these physics. Yeah, so you can add forces to the body and see how it recovers. So that's very nice. And the difficulties are like this scalability was one of the issues. So like as I mentioned, the deep mimic requires like training one controller for one type of motion. So like so that was one of the issue. People have been dealing with this since the deep mimic problem paper was appearing. And for the adversarial training, there's can be like a mode collapse happening, which is like if you just have a reward that specifies if the motion looks similar to the motion capture data, if the system always like replay the same motion capture data, it's going to be okay. So that's called this mode collapse. So if we want to like produce a wide variation of movements, this can be an issue. And yeah, so another thing is like this robustness and also like the recovery motion. So once the body falls down, you need to like have motion of standing up and run again. So and also like this balance control is an issue. So these are like the topics. I think many people are working on these now. So probably this is going to be solved soon. Anyway, yeah, so that's what was for this physically based animation. Yeah. So okay, any questions up to now? Is maybe it's good to have question time here, or should I go on until the end first? It's a bit difficult because I don't see anybody. Any response from the people? So sorry if it was too boring.
No, maybe you can go and we can have the Q&A session in the end.
Yeah. So how much more time do I have?
I think you have 15 minutes.
15 minutes. Oh, okay.
Yeah.
Okay, then
Then we can have the Q&A. Yeah.
Okay. Yes. Okay. So now let's talk about the crowd motion. Yeah. So we wish so now previously I was talking about just controlling the individual characters. Now let's think of like controlling a crowd to respond to the other characters and obstacles. So we will have many characters moving at the same time. Yeah. And we watched them to produce like various human-like movements, such as watching the show window, chat with others, not just walking. Yes, well, yeah. So crowd control usually is just walking, but maybe we want to see other motions like chatting with others and interacting with the environment. Okay. And so the previous methods, there are like lots of methods that is based on flocking and rule-based controllers and are like RPO. But now we can also like use these kind of like a reinforcement learning for character control. Okay, and so the flocking, if I hope some of you know about it, but it's like assuming you have like these kind of agents which are moving in some direction, there are going to be 4 different types of forces applied to them to produce realistic interactions between each of these agents. Yeah. So the first one is this separation. So if you get too close to the others, there's going to be force to push you back. Second one is this alignment. So if you have like these kind of agents moving in one direction, you also follow that direction as well. And there can be like cohesion. So if you have like characters trying to move away, then you try to like stick to them. And finally, there's going to be the avoidance. So if there's some obstacle, you are going to be pushed by some force to like avoid it. Yeah. So these 4 types of forces are applied to the agents to produce a natural behavior of not only each agent. Well, so you apply this to all the agents, and then a nice looking group movements can be generated. Okay. And yeah, so sorry, I think I would put in the wrong movie here. Oh yeah, this is what I wanted to show. So this is like sorry, I think I put in the wrong movie. So I wanted to show the what's the flocking movie of made by Reynolds at the time, but sorry, I put in the wrong one, so I cannot show that. But anyway, like a flock of birds, or like, you know, characters like flock of birds or school of fish can be well animated by this kind of a flocking. But if it's like a human behavior, you know, there are, you know, just following these kind of forces is not really good enough for producing high quality realistic body movements. Yeah. And so for this, avoiding such kind of like you know, well, not avoiding, but also like producing realistic human motion, there are rule-based methods that are proposed, which are like you know, deciding how the body should move in all these kind of different complex you know, situations, like colliding with one another, or like, you know, also like you know, avoiding this kind of like obstacles in some narrow area. Okay. And so this is has been you know, this kind of rule-based approach is like valid, is a valuable approach for producing realistic human movements. Okay. And so but like this, as I mentioned before, this flocking is, you know, we need to set the weights between these kind of different forces, and also it's difficult to like produce social behaviors. And the rule-based approach are good for like producing social behaviors, but you know, you need, if you have a wide range of interactions, then you need to increase the number of rules. Yeah, so that's not very scalable. And so now then we can like use these reinforcement learning approaches that I just mentioned. So for like controlling the characters to, you know, consider the long horizon. Yeah. And so we can, if we want to like produce the different behaviors, we can have like a loss function or reward that produces each of such kind of behaviors, such as like moving towards the goal or avoiding obstacles, and interacting with the others, or like focusing on some interesting objects. Yeah. And so this CCP, this configurable crowd profiles, is actually published in this SIGGRAPH this year. I wish I thought this paper is very interesting, so I was you know, I brought this up, and it's actually you know, including the weights of these 4 rewards that I mentioned before. This you know, the goal, getting to the goal, avoiding collisions, interacting with others, and focusing on interesting things. We have rewards for each of these kind of behaviors. And so, and the weighting for these rewards are actually included in the state space, so that we can, you know, switch between these kind of rewards during runtime. Yeah, so that's very very interesting. So let's have a look at the short video of this. So here, the left one is the goal seeking, and the left one is, this one is the collision avoidance, and then we have a grouping and also this interaction. Yeah. So by changing the weighting of these different rewards, we can like generate different behaviors that looks, you know, that we often see in the real life. Yeah. So you can see that here, you can like generate this kind of motion of gathering around some kind of like a interesting object. We can also like have like a people grouping together. If it's goal seeking, it's simple. It's just so the characters just walk towards the goal, and collision avoidance is also an important factor. But these can all be learned all together in this reinforcement learner. So this is a very interesting idea. Okay, and so that was for the crowd animation. And well, another topic that we have been working on is this kind of like a hand animation. So you know, hand motions are actually rather difficult to capture due to some occlusions, you know. So you know, a specialized setup is needed for with many cameras. So this is a you know, a setup in by Facebook when they were capturing this hand movements. And so you put on a glove like this with many markers on the hand, but you can see that when you're manipulating objects, there's going to be a lot of occlusions happening. So some markers are going to be hidden from the other, from the cameras, and then it's going to be very difficult to like do the motion capture. Yeah, so they have this kind of like a complex setup with many cameras surrounding the hands, so that it doesn't miss much the markers that much. Okay. And so yes, but like when we are animating the character movements during runtime, we cannot expect that we have like this kind of a special setup, so that's something like an issue. So what we can do instead is like we can like do some kind of a learning so that the finger motions can be automatically generated from abstract information, like the wrist movements and the object movements, and also the geometry of the object. Yeah, so this is by doing some kind of like a learning, we may be able to adapt the finger movements to this geometry and the object movements and the wrist motion. And so this is something that we did recently. And so this is again like a deep learning approach. So you give this wrist motion and the object motion, the finger motions are predicted. Yes. Yes. So for this purpose, what we can do is that, again, we capture lots of motion capture, and that's kind of a special setup. So this work was done together with Facebook. And so we capture the motion of the object as well as the fingers. Yeah. And then we are going to give in this network, we are going to give the trajectory of the object and the wrist, as well as the pose of the current pose of the hand, and also like the relation, some features that is computed based on the current pose of the hand and the 3D geometry of the object. So this is like a volumetric representation of the object, also the distance between the fingers points and the object, and also like the directions. Yeah. So these kind of features are given as an input to predict the next pose of the character in the next frame. Yeah. And also when we do the prediction, we also predict the distance between the finger and the object, fingers and the objects, so that we can do some post-processing to like adapt the pose to different geometries. And so you do this over time, and so this framework is like trained for the right hand, but we can do the flipping for like predicting the pose for the left hand. Yeah. And then both hand movements can be predicted over time. Okay. And so this is like the setup for doing the motion capture for the fingers. Yeah, so this is like you can see that we have the glove, and with where the small markers are attached to it, and like these interactions of the hand, the body motion and the object motions are tracked together. Yeah, and so this database is actually available on the web. So if you're interested, you can download this. And so we can like train this system with manipulating different geometries. So like these kind of primitive geometries, as well as the geometries of these kind of 3D objects that we use in our lives. And then train the network to like predict the finger movements at every frame. Yes, so you can see in this example, this object with complex shapes, or like, the finger movements to manipulate these complex shapes can be produced. Yeah. So you can see that the fingers are adapting to these geometries. So actually the input is the same for these two images. Yeah, so you can also do the scaling of the geometry. So by using these kind of distances between the fingers and the object, you can like generalize better to like different geometries. And so it's good to use this kind of abstract information for the features. Okay, and so this is the video of this online yeah, control. So there's a little bit of a latency. Yeah, so this geometry is not seen during training. So okay. Yes. Okay. Yeah. So I think like this kind of like a hand pose prediction is very useful for these kind of VR applications. Actually, this Oculus Rift, they predict the finger poses from the camera inputs. Yeah. And so, but for training this kind of model, you need to have very high quality training data. So like you need to at least have this kind of setup once. Yeah. With many cameras to accurately track these finger movements as well as the object. Yeah. And so for other topics, there are also other topics like finger pose synthesis during conversation. So like when humans talk to the others, they use the fingers a lot to produce different gestures, and like there are works like that, predicting these finger movements from the full body motion. So you just track the wrist motion and and then the detailed finger movements are generated on the fly by regression. Yeah, and also like I think some people also like do things like predicting the finger movements while playing some instruments, and so those are also like related to these finger motion synthesis. Okay. Yes, so actually, yeah, I'm a bit early, but so this, this is like the last slide. So in summary, so this character animation synthesis involves a lot of topics, including the full body motion, the facial animation, hand motion, and the skinning cloth simulation. And recently, this physics-based animation is becoming a major stream. You can see that in the SIGGRAPH program. There's a session for this physics-based animation and for the full body motion. So that's quite a popular topic now. And but we are like hoping, so these efforts that we're doing for character animations not only used for computer graphics, of course, we wish them to be useful for computer graphics, but also, other topics like robotics, computer vision, and AI, other AI areas. We are hoping that we can like contribute to those areas as well. Okay. And so that's pretty much all. Yeah, I thank thanks to these funding bodies that are supporting our research. And as I mentioned in the beginning, we have several PhD and postdoc positions available. So please feel free to apply if you are interested. Okay. And so thank you very much. And I can answer two questions now.
Thank Taku for this very informative lecture. And now we have time to answer several questions. Here's one. Is there any hope to study the acceptable position manifold with purely geometric approaches?
So
Acceptable position manifold.
what is the acceptable position manifold? Is well, do you know? Well, is it like an acceptable position manifold given?
I think it's maybe referred to the motion manifold, because this motion manifold is only a subspace of this full position, joint position space. So I
Yes.
think he asked, is there any hope to study this motion manifold with purely geometric approach without any learning-based method or something like that?
Without learning with the geometry, let me think about it. If the okay, I can interpret this question in various ways. If I was wondering if he means the person asking is asking about learning from the point cloud or something. So if we wish to learn from the point cloud, I think you need to bypass through some kind of like a representation for these geometries first. If so, like maybe using the point net or whatever representation for the body and the objects first, and then do some passing through some digitization. And well, that's going to be easier for sure for if you just want to learn about the nature of the human movements or the how human what manipulate the objects. I think that's definitely easier. If you just want to directly learn from the geometry, like the point cloud data, that's actually very challenging but interesting. Yeah, so well, I'm not a very I'm not a very good researcher for this machine learning. Actually, it may be possible, I think. Yeah, so it's like given the scale that these deep learning networks can learn, it may be possible to learn from a wide, just purely from the point cloud to like synthesize like the missing body motion or like like predicting how the body is going to move in the future. I think actually that's a very interesting and challenging research. In case that you don't want to go through these kind of like procedures like fitting some skeleton into the body or like fitting some models to the geometry. So well, yeah, I think that's very interesting. I think it's good to look into such kind of a direction for further generalization. So the only thing I can say is I think it's very interesting and challenging to work on.
So I think another related question he's asking is, like here you use autoencoder to learn such a manifold. So is there any way to directly define such a manifold using mathematics? Like,
well, yeah, actually, that's what mathematics, like people have been using lots of methods like PCA or like, there are other like, methods for nonlinear approaches for representation learning methods, I think. And yeah, so like, yeah, of course, there can be better methods as well. I think like a convolutional autoencoder is classic. People have been using like the transformers for like learning these, related parts of the body moving in sync. So I think like yeah, these new machine learning methods, they are like when the new thing appears, we should always try them to and compare with what we have already. Yeah, and what is it? Yeah, so like but I think like the temporal convolution is actually a good good approach. It's very classic already, but it's whenever we try something, you know, it usually works well. And so like I hope you can like you know, the new guys can like keep on trying with the new novel, you know, inventing new machine learning approaches that can like generalize well to these new situations. Yeah, just again, this is like an encouragement. So like there are new methods appearing in machine learning. We should always like jump onto it and try them. Yeah, so this is something that a regular routine that we all have to try.
Mm-hmm. So once the manifold is ready, when we search for a natural motion sequence, can it be interpreting the evolution of the motion as a geodesic on this manifold?
So can you say the first part again? Sorry, I missed the
So
first part.
once we have this manifold, so this is all plausible like joint positions. So
Yes.
if we try to generate a motion sequence, a natural motion sequence on this manifold, can we interpret it as a geodesic path on this manifold?
I see. Okay, so this manifold is representing the, you know, the temporal convolution filters. You know, it's represented by the temporal convolution filters. Yeah. So if you have like two different points, it's actually representing some motion, one short motion sequence. So if you do the interpolation, actually it's like doing some interpolation such that it's like producing some motion in the middle. Yeah. So say you have like a, you know, a running motion and a walking motion. Yeah. And then you have like points on this motion manifold. And then like you are going to do the interpolation between the two. That means you are going to produce some transition from the walking to the running. Yeah. And so if you want to like evolve over time, so it's like going to be like moving along this manifold in some fashion. Yeah. And so possibly yeah, we can also like make use of it for some motion prediction as well. So like try to predict what the next pose is in the future. Okay, so yeah, actually this periodic autoencoder that I mentioned in the very beginning is actually another representation of the human motion that is assuming that the motion is usually periodic. Yeah. So you know, this is it's somehow similar. So we do the autoencoding, but we have like a FFT layer in the middle to like convert the motion into the frequency domain. And so this is also like interesting in the sense that you can like the point on the manifold actually represents a longer sequence of the motion. And you can also like use this for like motion prediction type of applications, as well as like you know, interpolation of movements. So if you're interested, please have a look at it. Yeah.
Okay, so one last question. So I noticed that through most of your lecture, all the characters are only skeletons, and when you switch the head animation, the hand has matches. So I wonder why, like previous works on character animation, cares focus more on skeletons.
Yeah, so that's something that is yeah, interesting. Where, you know, especially like if we are mainly working on this kind of like a character in the background, or like just a character without so much interaction with one another, we, you know, also like for the ease, for the simplicity for the animators, it's much easier to just control the skeleton instead of the surface geometry. And so that's like trying to like reduce the dimensionality of the problem. And on the other hand, as you mentioned, like if you want to like grasp objects or like, you know, interact with another character, then we need to start considering these kind of like, you know, the distances between the surface of the hand and the object geometry. So yeah. Well, I think like yeah, for still people like somehow use that as a constraint instead of like the representation itself uh to like to reduce the dimensionality of the problem. Yeah. So yeah, for the future research, yeah, of course we need to like consider how these deformation of the surface is happening. And actually like this works by Michael Black is like you know moving in that direction. So like simulating like predicting the deformation of the surface given the skeleton motion. And so I think like we will probably need to like consider that all the time when we are simulating these kind of like close interactions between the bodies and the objects. Yeah.
Okay, thank you very much. So time is up. So I think all the audience can ask more questions in the Discord, and Taku can check the questions later and answer there. So let's thank Taku again for this very informative and interesting tutorial. Thank you very much.
Okay,
and
thank you very much
now,
for listening.
okay, thank you. And then, okay. And now we will have a 10-minute break, and we'll be back at 8:30 for the second tutorial. Thank you.
Hi, my name is Bernhard Ecke. I'm a junior professor at FAU in Germany, and today I would like to give you a tutorial about 3D morphable face models. I would like to thank the two organizers and hosts today, Hussein Hu and Teseo Schneider, and I would like to thank you very much for putting this nice program for the grad school at the Symposium of Geometry Processing together, and also for inviting me. So 3D morphable face models are a pretty large topic and also historically grew quite a bit, so I can't possibly cover everything in today's presentation. So my goal of the presentation today is to give you a rough overview and to catch your interest. So you will see a lot of small things, and behind a lot of those things there is a whole line of research, and a lot of PhD students spend time on things that I might mention in one word or in one sentence. So the purpose is to give you a rough overview, to catch your interest, that if you feel like that could be something interesting for you, that you could dig deeper. The presentation today is pre-recorded, but at the end of the presentation I will join the virtual room to answer your questions that you might have. So let's start with a quick introduction of myself. I did all my studies at the University of Basel in Switzerland. So I did my bachelor's there, I did my master's there, both in computer science, and I also did my PhD there in the research group of Professor Thomas Vetter. During my master's, I already started to kind of work on 3D morphing models, but more on the shape modeling perspective. And the goal of my master's thesis was to try to understand the relation between skulls and faces. So given a dry skull, could we estimate how the face would look like? Or given a face, could we estimate how the underlying skull would look like? So one of them has a forensic application, and the other one would have an application in animation if you would know how the bone structure would look below the skull. In my PhD, I then switched to 3D morphing models and to the analysis of faces from 2D images, and this is something I will heavily cover today in my presentation. Besides my education in computer science, I also did an upper secondary school teaching diploma, so I can teach computer science at high schools. So this was a little bit a sidetrack, but it's kind of my backup plan if this whole professor thing doesn't work out. After my PhD, I was then fortunate enough to get a fellowship from the Swiss National Science Foundation to go to the US, to go to Boston, and to go to MIT. I first joined there Professor Paulina Golland's group, and then moved to Josh Tenenbaum's lab, first at CSAIL and then at the Department of Brain and Cognitive Sciences. At CSAIL with Professor Paulina Golland, I worked on the lateral ventricles in the human brain, and we were trying to predict the outcome of stroke patients from white matter hyperintensities that we observe in MR images. We, in particular, were using shape modeling tools and modeled the hyperintensities on the surface of the ventricles, as a feature on the surface of the ventricles. In Professor Josh Tenenbaum's lab, I then moved back to faces and explored several questions around 3D morphing models, more from a cognitive science or neuroscience perspective. For example, those black and white Mooney faces that you can see here on the left, or those very colorful faces. I will tell you something about those towards the end of the presentation. If I'm not doing research, I'm a passionate scuba diver, and I also have a glider pilot license. So I'm very happy to also chat about that anytime you meet me in person or also virtually. After all of that, I joined the Friedrich Alexander Universität in Erlangen-Nuremberg, where I'm here as a junior professor. We always say that's the best university you have never heard of. You might not know the name yet, but I hope that you might remember it in future. So it's a pretty big university with 40,000 students that covers all different directions of the scientific education. And we have a pretty strong technical department, and you might know some of our alumni. So let's dig into the actual topic. If I show you a picture like this, it takes you some split seconds and you start to interpret this image. And this is one of my research goals, to understand scenes like this one here, and to use slightly different tools than what most of the computer vision community is doing. I would like to get a rich understanding of that image. I would like to reconstruct the 3D scene from such a single image. With 3D morphable models, I will present one tool to you how we can enable that. If you look at this image, you might have seen that image before. If you wouldn't have seen it before, you would immediately start to interpret it. You would be in particular interested about the faces. You would probably also estimate where those people are gazing at. And you would assume there might be something outside of the picture. So you might even reason about things that you can't actually see in the picture. And if you look a little bit longer, you potentially also realize that somebody is not paying attention. This works much better in a real presentation where you have an audience, because there is always this one person who doesn't pay attention in a real audience. But he might also be steering the presentation or writing a very important email or whatever. So we can't really blame him. Okay, if you throw such an image in current machine learning algorithms, like detecting faces is kind of almost solved. Estimating the gaze is something you get, and you could also segment all the objects in that image, and you would probably get satisfying results. What currently doesn't work yet is if I want to have a very rich scene description, if I want to know the interaction between those people, if I would like to have the 3D reconstruction. So what I'm basically looking at in my research, and I will show you that later, is the scene tree behind this photograph. So let's also dig into a slightly different motivation if you would like to manipulate face images. So if I show you two images like that, I could ask you which one is the real one and which one is the manipulated one. But the question that I'm asking is slightly different. So those images are actually both manipulated. And they are manipulated in a way that one of them should appear more trustworthy to you than the other one. And probably most of you would agree that you perceive the one on the left as more trustworthy than the one on the right. And the question is here, we can also change other factors like smiling, or the size of the eyebrow, or the size of the nose. So the question here is, how can we make such changes? Those are pretty subtle changes. The result is photorealistic. So how can we make such changes when what we get is a single 2D image? And the tools we are using are actually very similar then to analyze the picture that I've just shown you before. So what are the challenges if we would like to manipulate that image? And here I will use, on the one side, the 3D morphable model. So those are those synthetic faces that you see here on the bottom. But I will also use a smiley model. So a 2D, very simplistic model to basically explain you all the math on a very easy level, because I have no idea what everybody brings as a backpack from the method side with you, and I would like that it's very inclusive, that everybody can understand the basic concepts, and some of you might get like how it works in detail, but everybody should at least be able to understand the basic ideas. So the first thing we need to understand is where do we need to change stuff. So what we need here is the concept of correspondence, and I will explain that in detail. Then we need to know what to change. So we need some statistics. We need somehow a data set that tells us those are people that are smiling, those are people that are not smiling, those are people that were rated as appearing trustworthy, and those are people that are rated as appearing not so trustworthy. And there are actually studies that show that those trustworthiness doesn't correlate with the perceived trustworthiness, but that's a very different topic. So the last thing we have to think about is how do we apply that change? And for that we can apply linear models, but we also can apply nonlinear models. In the methods that I show you today, we keep it simple. So we go for nonlinear with almost anything. But of course we go with linear for everything. But of course, for almost anything, there are also nonlinear methods. So you will find a paper that does almost every single step that we are doing here linearly in a nonlinear fashion. What you see here on the left are 10 faces that were released with the Basel face model, which was the first publicly available morphable face model. And then we can build a statistical model based on those. And what we would like to change is what you see on the right. So we have a face in some state, and we would like to manipulate that face into another state. For example, here we would like to apply a smile. And the simplification we take here is a smiley model, a 2D model, which is very simplistic. It also has the coordinate grid in the background. That's just for orientation. And our model basically has just a few points. So it has 2 eyes, 2 points for the eyes. It has 2 points for the nose, and I think it has 4 points for the mouth. So this is a drastic simplification. For the 3D morph model for faces, we have around 65,000 points. So it's first of all much less points. And the reason why we do that is smileys are fun. And the other reason is it makes it much easier to explain the concepts, because the underlying math of a 3D morph model is actually pretty easy. So I will always try to show you that relation from this 2D smiley model to the 3D morph model. So if we would like to do some calculations with those smileys, because at the end, this manipulation we would like to apply, this vector we would like to apply to change a face is somehow a computation. So if we have the image on the left, the smiley on the left, and we would like to make the smiley smile, we have to apply some change, we have to apply something. So the question is, what do we apply? And the other question is, what can possibly go wrong? So if we have the original image here, what we can do is we can say like, okay, we would like to add happiness. And then the question is, how do we measure happiness? So what we need is some kind of a data set. And in this simple case, we just have 2 images. We have the one on the left is one that's smiling very strongly, and the one on the right is one that's smiling much less. So we define happiness for this simple example just as the one on the left is more happy than on the right, and there is nothing else different. So the difference between the smiley on the left here and the smiley on the right is what we define happiness. And we would like to apply this difference to the original image. So what could potentially go wrong if we do that? And what goes wrong is if we just do that on a pixel basis, point by point, we get something like this. And this looks very funny. It's also kind of smiling, but it's not what we expected. So we have somehow ghosting artifacts around the eyes. We have 2 mouths. It doesn't look quite like a smiley anymore. It looks like something. It looks funny, but it's not what we were looking for. So the problem we have with this calculation is that we didn't solve the correspondence problem. And correspondence is something that's really an underlying modeling technique for a 3D morph model, and it's very important. And even a lot of the morph models that are used today have this very strong assumption of correspondence. And I would now like to explain you what that correspondence means. And correspondence means that in each face, so in each 3D face and in each smiley, we have points that we can locate in all of them. So for example, in the smiley, it's the left eye. So one of the 2 blue eyes, the right eye, the other one, the nose, the corner of the mouth, somewhere in the middle of the mouth. And for each of those points, we have to find the point on the other smiley. And we do the exact same thing with 3D faces. So we search for the tip of the nose, we search for the corner of the eyes, we search for the corner of the mouth, and we do that for each of the 65,000 points. And that's what we call dense correspondence. So it's not only for some of the points on the face, it's really for every point on every face, we find the corresponding point on all other faces. And that's a pretty strong assumption. It works pretty good in practice, but it's a very strong assumption, and there are also some cases where this assumption is pretty wrong, especially for modeling texture, or if you have some features where there is no correspondence. So there are some features that you can very easily imagine. So for example, folds, this nasolabial fold, is in some people stronger, in others less strong. But we could say like that's a fold that we will find correspondence in a lot of people. But what do we, for example, do with the wrinkles on the forehead? Like I have 3 or 4, other people have none, some people have 5 or 2. So there is just no way to find the corresponding fold in another face for every of my folds. The same also with small texture features. If I have a small mole, you will not find the same mole in another person. So on the texture, you also can't really find a lot of those correspondences. Or even with eyebrows, there is the additional problem that how do you define the correspondence? Do you define it on the shape or do you define it on the texture? And you will get a very different result. So here in the smiley model, everything is easy. In the 3D morph model, it's getting more and more tricky. But what we do for the following few slides and for simplicity is we just assume that this correspondence assumption is right, that we can assume that for every point in my face, we will find a corresponding point in every other face on the world. And that assumption makes everything much easier. And that assumption enables us to use very simple math and very simple statistics to model faces. So on the 3D face, it looks like that. We find the point on the nose, we find the point on the corner of the mouth. And doing that on a 3D face is actually pretty tricky in practice. What we need to solve this correspondence problem is called registration. And registration is something that a lot of people spend their PhD with. So there are a lot of different techniques how to register one face with another face, or another 3D thing with another 3D thing. So for example, bones or other body parts or cars or whatever. And the reason why this is so tricky is because it's a very non-convex optimization problem. And one of the very tricky parts is that you assume the strict correspondence and it might just not be there all the time, so you need some good priors. And in some regions, like the tip of the nose, it might be pretty easy to find the corresponding point, or for the corner of the eye. But what do you do on the cheek? You need some kind of a smoothness assumption. You need to assume that on the cheek it's more smooth because you have very few features. And at the end, it's also very hard to evaluate that correspondence because it's also very hard to label that by hand. So the actual evaluation of this correspondence you get by a specific application. So after the correspondence, you can build a model and then you can apply the model and then you can assume that model is better because the correspondence was good, or that model is not so good because the correspondence was bad. So it's very hard to evaluate that step. So let's do some calculations with this correspondence assumption. And now for the smileys, I add the coordinate grid. So we now calculate with coordinates. For the smileys, those are 2D coordinates. For the 3D morph models, those are 3D coordinates. So for each point on the face, we have a 3D coordinate x, y, z, and we have a color, an RGB color for each of the point on our 3D face. And once we have that, we have a representation that, which is in a format where we can do some calculations. So for the smiley models, it's just an x, y coordinate, and we can do calculations like, for example, calculating the average face. So for the smiley model, we have a data set which has 6 smileys, and we build all of them by hand, and then we can calculate the average. So we take all those 6 smileys, we take all the points, and for each of the values we calculate the average. So we calculate the average of 0.1 the x coordinate, we calculate the average of 0.1 the y coordinate, and then we just visualize that average, and what we get is this smiley you see on the bottom right. And that's basically exactly what we also do with the 3D morph model. We take a data set, and what I'm showing here are the 10 publicly available faces from the Basel face model. The actual Basel face model is built from 200 3D face scans that are in dense correspondence. There are also bigger 3D morph models. There's, for example, one that's built from 10,000 faces, but the concept for all of them is very similar. You take those faces and then you use them to do statistics. So the easiest statistic you can do is to calculate the average. So what you see here on the bottom is the average phase calculated from those 10 phases you see on top. And then besides the average, you would probably also like to visualize the variation that you get. The visualization, sorry, there is one step before I show you the visualization. So first of all, you need to have the parameterization. So I told you before that we have the shape and the color parameterization. So we have X, Y, Z coordinates for each of those points. Those are around 65,000 points for the Basel phase model. And we have the same also for the RGB colors. And each of those values corresponds to one particular point. And you can look at those distributions. And this plot is actually taken from a paper where we say like, okay, this linear Gaussian model might not be the right one. So this is a particular distribution that we measure at the eye. But for a lot of points in our data set to build a Basel phase model, the distribution is Gaussian or very close to Gaussian. For some points it's not, so for those points it might be better to use other modeling techniques. So we have a lot of those distributions per feature point, and then we can apply our favorite statistical method. Since most of our distributions are Gaussian, we use a Gaussian model and we just use principal component analysis for most experiments that I show you, and almost everybody or a big part of the community still relies on simple PCA based model because they are low dimensional, so it's easy to optimize in that space. They are linear, that also makes a lot of things easier. And of course there are nonlinear extensions. They also have some benefits, but I will show you later one example where you have a challenge, a 3D reconstruction challenge, and there the state-of-the-art models are actually not doing much more complicated things than what I'm showing you here on the modeling side. So this is how the 3D Morphable model then looks like, and that's actually from the original paper from Blanz and Vetter, who proposed the 3D Morphable model in 1999. So what you see in the first row here is the visualization of the first three principal components in terms of shape variation. So those are the strongest shape variations in the data set. And the bottom three examples are the first three principal components of texture variation. You can see that there is also a little bit of illumination baked in here. So different models will have slightly different first principal components, but that's basically how you can imagine the different parameters of a 3D Morphable model to work. To give you an idea of the dimensionality of this parameter space, for the shape model and also for the texture model, if you have 200 examples, you get 199 parameters. Most people in practice use only the first 50 parameters. Those capture 99.something% of the variance. So for most of the experiments, that's enough. If you need a better model, then usually the number of parameters is not the limiting factor, but the expressiveness of the PCA model, because you can see in the texture model that a lot of the small details are missing, and they can also not be properly modeled if you just add more and more parameters to the model. So if we go back to our smiley model, and we go back to our task where we would like to do the manipulation, if we take this representation point by point for the original image, and we do our calculations of this happiness vector now not image based, so not pixel per pixel, but we do it point per point and only for those corresponding points, we can actually calculate this happiness vector. So we get a vector and we can apply that vector to the original image. And what we get from that is a manipulated image. So first of all, we get numbers, and then we need a renderer. So we just render it in the same way as we render the other smileys. But here we have to explicitly do it. And what we get is a smiley that applies exactly this happiness vector to the original image. What you can see here, it's not only the shape of the mouth changed, also the eyes moved down. That's because in our happiness vector, the happiness seems not to be disentangled from the position of the eyes. So if you would like to find a good happiness vector, those two examples might just not be sufficient. We might actually need more examples to calculate this happiness vector, and I will show you how we can do that. So if you would have a lot of examples of people that are smiling or not smiling, and you somehow have this label, how strongly they are smiling, and you have the representation in your model space of all those examples, you can calculate this vector, and then you can apply this vector to your model. And that's exactly what was also done with those vectors for perceived trustworthiness, that you have a lot of data that was labeled by humans, and then you can estimate that vector and apply that vector on model instances. So if you would like to play around with those tools and play around with 3D morph models, for both the smiley model and also for the Basel face model, we have a model viewer, and you can download the model. You can play around with those models. You can change the parameters, so the principal components, to see what the strongest variations are. You can, with the smiley model, do those manipulations yourself, like the smile vector is in there. And with the 3D morph model, with the Basel face model, you have a separate color model, shape model, and an expression model where you can change the expressions on top of that. The expression model for the Basel face model is slightly different than those smile vectors. Those expressions are actually separate face captures, where we then model the expression space as a deformation from the shape space. So this now helps us to understand how this portrait manipulation could work. But there are still some very important components missing, because we don't know yet how we get from this 2D image to the 3D morph model. Because we can apply this smile vector or trustworthy vector on a 3D model instance, but what we get is a 2D image. So we somehow need to infer the 3D shape and the 3D texture from this 2D image. And that's also a task where various people spent their PhD on, including me. I in particular looked at how we can solve that task if there is some occlusions. So there are various different techniques how we can try to estimate the 3D face shape from such a 2D image. And that's very important if we would like to manipulate this image with such a method. A project that I was recently involved in did do that with 3D morph models, but in combination with stylization, which is a 2D method for image generation. So the idea here was to use the photorealism capabilities of 2D stylizations, but to combine them with 3D morph models. Because we have seen before that 3D morph models have this challenge that they can't model the texture accurately. So this linear, simple PCA texture model might not be sufficient for a lot of applications. So if we want to do some complex changes on the images, we will need a more complex texture model. So in other words, the results that I've shown you before, where we change one single 2D image, that works as long as we don't change too much of the texture. So if we only move around pixels, then it works. But if we want to also apply changes on the texture, then we need a method that enables us to synthesize textures. And this is possible with this 3D morphable stylization that was built by Safa Medin. He did an internship at Mitsubishi Electronics Research Lab, and I was very happy to be able to help him there. So if we go back to the image that I've shown you in the very beginning, you might remember that the task we had to reconstruct the 3D scene is actually pretty similar to what we need to do if we would like to reconstruct those 2D images for manipulation. So the input is a 2D image, and we would either like to understand the image, or we would like to understand we either would like to understand the image or we would like to apply a manipulation. But what we need for both of it, at least if we follow this approach, is that we reconstruct the 3D from this 2D image. So we would like to reconstruct a 3D face from this 2D image. And the way we do this is called inverse rendering. And what we need for inverse rendering is first to understand how rendering works. So for a lot of you that might be very basic. This is basic computer graphics. It might be a bit special with our face model. So what our face model gives us is a shape model that you see here on the left. So we get a 3D shape that's just a simple mesh. And on the right, we get a texture model, so we get a texture. And if you have a shape and a texture, you need two more things, and then you can get an image. One thing is you need a camera model. So in our case, we go with a simple pinhole camera model, which is not that unrealistic, but it's a pretty simple model. And we need an illumination model. And what we use here is a spherical harmonics illumination model. If you have never heard about spherical harmonics, the idea of spherical harmonics is to approximate the light that comes from the environment. And the nice thing about spherical harmonics is that it gives you a low dimensional representation of this environment map. So you get 27 parameters that explain basically the illumination in the scene. And it has been shown that for diffuse reflectance, those 27 parameters are pretty much sufficient. We have a very recent work currently on arXiv that shows that if you use a neural representation, you can build more powerful illumination priors with 27 parameters, and that is especially valuable if you also would like to take specular reflections into account. And even on faces, you might also see it on my forehead now, there are some specular reflections, so that might also be important if you want to do inverse rendering of faces. So what you get if you have all those parameters is a rendering of a 2D face. And this here is a synthetic face that we render on the bottom. And if we would like to do inverse rendering, what we have to do is basically go the opposite way. So we take the 2D face as an input, and we would like to infer all the other parameters. So given this 2D input, we would like to know where is the camera, what is the illumination condition, what is the texture, and what's the 3D shape. And this is an ill-posed problem. And it's ill-posed because there are multiple possible solutions. You might know that if you do a selfie with a camera, your face sometimes looks distorted. And if you want to solve the inverse problem, you don't really know if this distortion comes from the camera projection or if this distortion is actually that that person has that shape. So that's the ambiguity between the camera and the shape. You also have another ambiguity with the texture and the illumination, because some appearance of faces you can explain with both the texture of the face or the illumination condition. So a slight change in skin tone you could also just explain by an illumination variation. So there are some ambiguities. It's an ill-posed problem, and what you need to solve this ill-posed problem is a very strong statistical prior. And that's exactly what the 3D Morphable model delivers us here for this application. What we need is we need to know how do faces look like. So what is a likely setup for the scene? And once we have those priors, we can use them to solve this ill-posed problem. And in our case, we have priors on the shape, we have priors on the texture, and we have priors on the illumination conditions, and we even have some very simple camera priors, like almost all the faces are somehow facing you. If you see my head from the back, you don't have any face, so then it's not important for us anymore. So our camera prior assumes that the face always is in somehow a pose up till 90 degrees. And of course, we don't want to solve that problem for synthetic faces. We would like to solve that problem for real-world faces. The person I'm showing here, by the way, all the time is Sandro Schönborn. I did my PhD in the same lab as Sandro Schönborn, and he was basically co-supervising me during my PhD. So that's why you see his face here very frequently. So this slide here is again over 20 years old. It's from the original presentation of the 3D morphable model at SIGGRAPH. So you have the input image, and you would like to generate a synthetic image here next to the input image, and you would like to adopt it in a way that it looks very close to the input image. And the first thing you need to do is you need to detect where the face is, and then you have to adapt all those parameters. So you have to find the pose parameters, those are the camera parameters, you have to find the illumination condition, and you have to find those shape model parameters, or the morphable model parameters, which are here depicted with alpha and beta. So you need to find which linear combination of faces you need to regenerate this input image. And there are a lot of parameters. So for the pose, illumination, and shape and texture parameters, you have easily like 200 parameters that you have to optimize at the same time. The really tricky ones are especially the pose, because if you don't get the pose right, everything else doesn't make any sense. So you need some strong inference techniques. In the original paper, they initialized the pose by hand, and you even saw the hand in the video before. In later work today, you have strong landmark detectors or also direct pose regressions. What you get out at the end, if you solve this optimization problem, is a reconstruction of the face. So you get a 3D model of the face, and what you can do with that is what we have done before. You can do the manipulation, you can re-render the face under different illumination conditions, and you get the 3D model, so you could also use it for other applications. You can rotate it, whatever. So here I would just quickly like to show you the full pipeline to do one of those image manipulations. And that's a short video, and the text is in German, sorry for that. So the first thing we have to do is we have to find the face. We did that with a face detector. Then we start this inference process. And what we used here as an inference technique is Markov chain in Monte Carlo. So it's a sampling-based approach, and we are slowly converging to the face. You can see that we adapt the illumination, the shape, and the texture. At the end, we have a pretty good reconstruction. We blend in the real texture, and then we can rotate the face. We have a 3D reconstruction that we can visualize and use for various applications, including the image manipulation. So if we go back to this image, we could of course also apply everything that you've seen on this image. I spare you the manipulation. I also honestly didn't do that, but we can run the 3D reconstruction for all the faces in that image. And it might be very hard to see now what the reconstruction is and what the image is, because it's overlaid. So let's remove the image. And I would hope that all of you agree that in this representation is much more rich than if we just say this is a face, or this is a segmentation of a face, or this is a segmentation of a body, or those are the labels of the face. So the goal here is really to get a rich understanding of the scene. You can also see some biases of our model in this reconstruction. The model was built in the model that we are using here is the Basel face model. It was built in Switzerland, and almost everybody in the model who was scanned was a student at the University of Basel. That means we have a very strong bias to people that walk around in Switzerland and to young participants. So that's why you can see here that especially the older folks are not very well reconstructed. So this whole idea of modeling shapes that way is even older than 20 years. It's over 100 years old. And that's a pretty nice book from Darcy Thompson, where he describes how you can model things that we can see in nature. And one example he has, you might have seen in shape modeling courses, is this example with the fish, where he basically says like a lot of fish are just deformation of other fishes. So you take a fish and you apply some kind of non-rigid deformation, and what you get is a new type of fish. So he said like a lot of the fish that are around you can explain by deforming another fish. If you dig a little bit deeper into the book, and I would actually recommend all of you to dig around in that book, it's publicly available and it has some beautiful work in there. You can also see much more complex models for other things that you can observe in nature. So it has a lot of very nice visualizations, and it also has statistical models of dinosaurs. So I got recently very excited about dinosaurs, and this book also covers that. And it also has some applications that perhaps go more in a medical direction. So the Morphable model that you've seen before is very similar to statistical shape models, and those are used in a lot of medical applications where you want to model bones, or where you want to model skulls for reconstruction purpose, for example. So a lot of what's covered in this book is also covered by statistical models, how they are today used, especially for medical applications. So since those 3D Morphable models are over 20 years old, 2 or 3 years ago, a group of people met at a Dutchfield seminar, and one result of that Dutchfield seminar is that some of us, 13 here, put our heads together and wrote a survey paper about 3D Morphable models. And the idea of that survey paper was to really cover widely what happened in this last 20 years. Because a lot of the things that I told you before are things that were actually already in there in the initial paper, or in some variants in there in the original paper. And of course there was a lot of research done in between. So we have over 300 references in that paper. And we kind of structured that somehow. We made tables to show what things are publicly available, which models you can just download, which data sets are available, which inference methods are available, which registration techniques are available. So there are also plenty of tables in there. But the main idea is to give you a very broad overview over all the different topics that are involved in building the models and using the models. And I just want to give you a brief overview over what's covered in that survey paper, because it shows how wide 3D Morphable models are and how many small challenges are involved when you Morphable models. So the first challenge is the capture. So we need some kind of data. Today we have Morphable models that are built on 2D data, but in terms of quality they're just not the same as the Morphable models that are built from 3D data. So capture setups today look something like the two on the right. So the image that you see on the top, that's a light stage. This is a light stage that was built in academia by Will Smith in York. There are also now commercially available light stages that fill whole rooms. And at the bottom you can see a capture setup from industry, from Disney Research, which also enables capture of emotions and motions. And is highly photorealistic. So dynamic capture is a whole different challenge. And here you can see that the eyes are closed, and that has a reason. Like capturing eyes is just a very hard problem. Today we are lucky that not everybody has to build such a sophisticated capture setup, because there are a lot of shared data sets. Of course, sometimes it's not exactly what you need, but very often it's just much more easy to use one of those data sets than to build your own. There are still a lot of remaining challenges, because almost all those captures, at least the 3D data, are captured under lab conditions. Those setups are very expensive, so you need to buy expensive equipment, and you also need to have space to actually put them. Modeling expressions is pretty tricky, and there are also some ethical challenges, because the data that you capture is what your model is later built on. So that basically defines in which direction your model will be biased. And it also has some privacy implications, because all the faces that you capture are real world people here. So that's something we have to think about when we collect data and when we make data publicly available. On the modeling side then, I've shown you the most simple principal component analysis based models. So what we have today is some models are based on a UV representation, some models are mesh-based. Very recent models are also implicit models, which are learned representations. In the original paper, there was no modeling of facial expressions. There are now also for facial expressions, linear models, non-linear models, models that model facial expressions in a statistical way or with blend shapes. Some models have this very strong correspondence assumption. Some models also break or challenge this very strong correspondence assumption. And today we also have models that are shared. So on the right here you see some of the publicly available 3D morphable face models. Some are only shape models. Others provide a shape and texture and also expression model. So there is a wide variety of different models that are available to you if you would like to use them today. Also on the modeling side, there are quite some challenges. If you have seen the captures before and you looked at the renderings that I've shown you, there is a pretty large gap between what we can capture and what we can model. And that's even the case if you use the most fancy non-linear GAN-based texture representation. There's just a huge gap between what you get in a high-quality capture setup to what we can model in a model that has a low-dimensional parametric representation. Some parts of the face are particularly hard to capture. So for example, eyes, mouth and hair, for all different kind of reasons. One is the physics of the scanner. Hair is also very hard to represent in a lot of representations, for example in the mesh-based one. And the mouth is sometimes closed, sometimes open, but it's just very hard to somehow model the interior of the mouth. Another challenge is the interpretability of the resulting latent space. So for a PCA model, you at least know it's the biggest, the direction of the biggest variation. And with deep models, the interpretability doesn't get better. And as I told you before, with the data, every model will be biased. So understanding those biases and being aware of those biases when building applications is very important. The next thing then is rendering, so the image formation. How can we generate 2D images from those 3D morphable models? So today we have much more complicated illumination models than we used 20 years ago. So 20 years ago in the original morph model paper they used a point light source. Today I already told you spherical harmonics are very popular, but there are definitely also more complex illumination models, and people are also thinking about including not only diffuse reflection but also specular reflection, like you see here on the right. That's the first publicly available model that gives you a diffuse and a specular albedo. The data here was captured with the light stage that you have just seen before. Today we also have differentiable renders. That's actually a fun fact that the 3D morphable model paper from '99 used a differentiable render and stochastic gradient descent. So we didn't change that much when it comes to differentiable renders here, except that today they are much more accessible and there are huge toolkits and they're also available to everybody, and not only the authors. Like in '99 it was just not so common to share the resulting source code. And a lot of the rendering today is also focusing on animation and not only still images. But also on the image formation side, there are a lot of remaining challenges. So for example, this pinhole camera model is not too bad, but it's also not very exact. Then not everything in the rendering process is differentiable. And again, we have the realism gap. So it's not only the model that limits the realism, it's also the rendering that limits the realism here. The next topic in this survey paper is then analysis by synthesis. So that's the part that I showed you before, where we would like to do the 3D reconstruction from the 2D image. And this is basically a computer vision application. So there are a lot of different methods how to do that. And you find a table in the paper that says like that method does that with that idea. And the state-of-the-art methods are also highly enabled by having not just one single loss function, like in the example that I showed you. We just try to minimize the distance between the input image and the reconstruction, but a collection of losses. So also perceptual loss, face recognition loss, a loss on the prior for regularization. So it's a huge collection of different loss functions, and that seems to work best. A lot of focus in the community is being put on shape. So a lot of the papers that you see out there are actually not reconstructing the texture at all. At the same time, a lot of the code that's published today comes with shared code, and there is even a challenge. And what you see here on the right is the now challenge. So the idea is you get 2D images, and your task is to do the 3D reconstruction. And what they did to enable this challenge is they have 3D scans of the same people as they have 2D pictures from, so you can compare the reconstructions against the ground truths and then measure how well you reconstruct those methods. So what you see here now on the right is one of the state-of-the-art methods that does that 3D reconstruction with a lot of details, and goes down to almost a millimeter in shape distance. So there are some open challenges also here. So for example, the benchmark, this now challenge, is only interested in shape. We don't look at texture at all. So this benchmark doesn't care about how well the algorithms reconstruct the textures. There are also a lot of ambiguities, and those ambiguities, I told you before, is what we need the strong priors for. But some of those ambiguities are even not 100% understood how we could resolve them. That's, for example, texture and illumination, the camera, projector and the shape, or also an ambiguity between identity and expression parameters. Yeah. So then we have a particular chapter in the survey paper about deep learning, because of course deep models had a pretty big impact in basically all of the different parts of Morphable models, but we decided to have a separate section to list all those impacts and somehow state why they are so important. So especially for nonlinear models, deep methods are highly valuable. You can build joint models, for example, for faces and speech. Deep methods are also heavily used for the inverse rendering task, mainly enabled by those differentiable renderers that are now available in PyTorch and all the other frameworks. They're used to learn models, so also to learn 3D models from 2D observations, and I will show you an example of that later, or also to build implicit models where we are not having this strong correspondence assumption, and where we don't, where we are not limited by a mesh-based representation. The example you can see here is, for example, one of those deep reconstruction methods, and what's particularly strong about this one is the speed. So before deep learning, there was just no method that could reach that accuracy in that short amount of time for reconstruction, and that's definitely enabled by those fast inference techniques. What you see here is now an implicit morph model, so you can see that it's now not only the face that's modeled, but also hair. Hair was usually not modeled because it's very hard to model hair with a mesh-based representation, and it's also very hard to capture hair, and it's very hard to model hair, especially when you assume strong correspondence. And there are also different beard styles, so mainly the correspondence assumption in that model is not as strict as in the classical morph model. There are also, on deep learning side, several open challenges. So if you approach any of those tasks in a learning-based way, you always also run into the risk of overfitting to that particular distribution. And one core strength of those simple linear models is they're pretty strong when it comes to generalization. And you lose some of that benefit if you use learning-based methods that are kind of more limited to what they observe in the training data. So for extrapolation, for out-of-distribution generalization, I think the classical linear models are very often stronger. Another open challenge is that for a lot of those techniques you need a lot of training data, so we would like to use less data, and that's again something, if you just build a simple linear model, 50 face scans are plenty. If you want to build a deep model, you definitely need more. Then the model building side, you still need high quality data, or you need a lot of data. So one of the key tasks or key hopes here, I think, would be that we could build stronger models from 2D data that's just much more available in the internet, for example. Last but not least, I would like to talk about different applications, and there are some applications that are more obvious to use, some applications are perhaps less obvious. So 3D morphing models are heavily used for entertainment purpose. They were used also for face recognition applications. I'm not sure if that's still today the case, but one of the tasks that 3D morphing models are, for example, helpful almost 20 years ago was if you wanted to go from a front view to a side view. That's probably today just solved with a lot of data and large networks. Then there are also forensic applications, like the one that I've shown in the very beginning. If you would like to reconstruct the skull and the face from the skull, or vice versa, or if you would like to have how are they called, the pictures that the police shows you, if that was the same person. There were also some projects in that direction. Then there are various medical applications. I actually have an example here. So for reconstructive surgery, imagine you would like to reconstruct a nose for a person that's missing a nose. Then the statistical model is very helpful to be able to provide a nose that fits the face and is not catching too much attention, if you would like to avoid that. And the 3D morphing models are also heavily used to study the human visual system, especially to see if face processing is somehow doing something statistical, and also some inverse rendering based methods. For all those different parts of 3D morphing models, and that's also something we covered in the survey paper, that there are some challenges that are shared. There are challenges that show up in all those different directions. One of those challenges is that we would like to have a low dimensional model for the inverse rendering problem, because the more parameters we add, the harder it gets to solve the inverse rendering problem, versus the degree of detail. With all the parameters we add, we gain details. So it's kind of a trade-off, what details we get and how much parameters we have. Another challenge is how to compare the results. So in a lot of papers, what you will see to compare the results, you will see a quantitative evaluation. And very often it's just a quantitative evaluation because it's very hard to provide numbers. And some of the numbers that are in papers in our community are just not really helpful, but those are the only numbers that we can deliver. So the comparison and benchmark is definitely a huge challenge, and some of that, the problem is not actually that you couldn't measure it, the problem is that data is not available or not easy to get where you could measure it. Another challenge is that if we would like to go beyond faces, so if we would like to apply some of those modeling techniques on other objects, like for example tables or chairs or cars, there are currently big parts of the computer vision community trying to do exactly that, and there you don't have this strong correspondence assumption. But at the same time, the in the wild inverse rendering problem is not working as well as it's tuned here for this faces application. And as I mentioned before, there are some ethical challenges with regards to the data, the capture, the model building, but also the various applications that you can imagine that you can build on top of such models. At the end of the paper, we then also try to imagine how the future could look like. So how representations in the future could look like, how we could break some of the modeling assumptions, how we could get rid of a lot of the manual work that's still today put into building high quality 3D morphing models. And then if there is actually one model that can fill all the applications, or if we need models that are specific for some applications. So for some applications we might need the photorealism, and for other applications it might be much more important that we have a low dimensional representation. The current trends in computer vision are definitely very helpful when it comes to 3D morphing models, because 3D modeling, inverse rendering, and all those implicit representation ideas are all something that I believe will push 3D morphing models way beyond what they are today. So now I would just like to show you some additional ideas on top of this classical morphing model. And now the things that I show you are even more biased towards the research that I was involved in than everything before. So most of the results you see now, I was directly involved in. So when we build a 3D morphing model, that's again the data from Basel. What I've shown you before is building a model from shape and texture. And what we do now is we also include some attributes, like here age, height, weight, and sex. So those are the attributes that were collected when the scans were collected. And what you need to be able to include those attributes is you need a method that's somehow able to deal with shape, texture, and attributes in the same model. The method we were using here is coupler component analysis. It's a very simple extension of principal component analysis that basically separates the marginal distribution, which can be continuous, it can be categorical, it can be binary. It separates this marginal distribution from the dependency structure, and that enables you to throw everything together in one model. And what you get is a model that not only contains shape and texture, like before shape and texture were modeled separately, now it's a joint model, it also contains attributes. And we use that model on the one side to build a face model where we could, for example, constrain the model on a subpopulation. So we call this a patient-specific model because we were thinking of medical applications here. So you could say, give me the posterior model of male at a certain age, and you would get a model that's built on your whole data set, but conditioned on those attributes that you give the model. And we also explored that for a really medical application. That's one thing that I also showed you in the very beginning of the presentation, when we were modeling those lateral ventricles of the brain. We here had also some attributes like the age or the sex, and then some stroke-related attributes. So if they have hypertension, if they smoke, and then those 4 numbers, which are some kind of stroke outcome scores. And we basically looked how strongly those attributes correlate with the shape of the ventricles and also with the degree of hypertension in that direction on the surface normal of the ventricle, which is here visualized in color. And you can see that there is quite some variation. On the very left you see the unconditioned model, where we have the average ventricle with the average white matter hyperintensity. And then we have the first degree of variation. If we condition the model on male, it looks very similar. If we condition the model on 80 years old, you see that the ventricles are bigger and that there are more white matter hyperintensity, so the intensity of the red is a bit stronger. If you take a much younger person and a female one, the ventricles will be smaller than in the old person. And also the hyperintensities are something that correlates very strongly with age, so you see that there are almost no hyperintensities in this young female population. The really cool thing here is that the model is always built on the full data set. We only condition it on those attributes. So you can build a model on a combination of attributes where you don't have a single training point. So if I would say like male, 37, 80 kilogram, smoker, hypertension, I would get the distribution of the remaining flexibility given those attributes. And I would even get that if I have no single training data that fulfills those attributes. And that's, I think, the strength of that model. Then there are various different medical applications. That's actually an application which was one of the first projects I was involved here at FAU from Maximilian Bayer, who is a PhD student here. He built this model back when he did his master's at Regensburg. So he had a collection of breast scans, and there are some very different challenges when you model breasts than when you model faces. So for a face you have a lot of features. For breasts, this correspondence assumption is very tricky, and it's very challenging to establish this correspondence, and you would also like to disentangle the variation of the breast from the variation of the torso, because it's also very hard to scan breasts. So he built the first publicly available breast model, which has, of course, several interesting medical applications that are now to be built, because the model is pretty new. Another application I'm involved in is actually more related to this inverse rendering setup. So if you have a 2D image, we can reconstruct a 3D face, and we can reconstruct it pretty accurately. So this could also, in a medical setting, enable some diagnoses that are not enabled yet. And doing a diagnosis based on the face is a very tricky topic, but there are diseases or syndromes where the diagnosis is classically done on the face. And fetal alcohol syndrome is one of those. Like, the facial characteristics are one of the things that are used to do the diagnosis. So the model the method we are trying to build here is a method that would give you a score based on a 2D image of the face. It has been shown that if you have the 3D scan, you can predict the same attributes as the doctors would note down pretty accurately. But the challenge is that a 3D scanner is not something that every one of us has at home. So if we could enable that with a simple unconstrained camera, it would be much easier. This project was done together with Professor Tinashe Mutswanga at the University of Cape Town and Felix Atuer from Uganda, who did his master's thesis on this. I told you before that there is this now challenge, and when I prepared this slide here, Junlu Lee, who is a PhD student who was visiting Thomas Vetter in Basel, who I had the pleasure to co-advise together with Adam Kortilevsky, scored on rank 1 on this now challenge. So what she did is she implemented a method that combines ideas from classical inference with modern learning-based techniques. The key thing that she changed is to make it occlusion aware. So to decide for each pixel if we should adapt the model to that pixel or if we should not adapt the model to that pixel. So the paper is called To Fit or Not to Fit. So for each pixel we have to decide if we should fit that pixel or if it's some kind of occlusion. And with this simple but powerful idea, she outperformed the state of the art that you have seen before that had all those details with a simple PCA-based morphable model. So there is nothing nonlinear going on the modeling side here. Today, if you go to this Now Challenge webpage, we are not on rank 1 anymore. So this screenshot was taken somewhere in March. I don't have the truth of that on my slides, but we are not rank 1 anymore. There is now an other method that scores even better. That method is, however, using supervision. So Junlu's method is still the best unsupervised method on the Now Challenge if you do the non-metrical evaluation. Another project I'm involved in is together with Skylar Sutherland. She was a research assistant together with me at MIT, and she's now a PhD student in Yale. And the basic idea of this project was to just assume that the human brain has some kind of a 3D morphable model. And if we go with that assumption that we have somehow a 3D morphable model in our brain and we use an inverse graphics pipeline to solve our vision tasks, the question is, how can we acquire such a 3D morphable model? And 3D scans is definitely not something we have access to. So the very basic idea of this project is to throw away all the training data and to learn the models and do it in some kind of a self-learning way. So let's throw away all training data. So what do we have to build in? What do we have to build into an infant that they can learn a 3D morphable model of faces during development. So we built a computational model to show that if we only built in an average face, we could learn such a model. So what we build in is an inverse graphics pipeline, an average face, and a very simple method to generate some random faces. So what you see here are some random deformations in shape space, in texture space. So we can generate a lot of images, and they're not realistic faces, but we can generate those images and we can train a face detector on it. So that's exactly what we did. We train a face detector on it, and we do an initial fitting. So we fit this model that we built from that very weird data and fit it to do the images. And what was pretty striking is that those reconstructions look pretty good. Of course, the 3D shape that we get from them are definitely not perfect, but the reconstructions look pretty good. So the idea then was, let's start with this CNN reconstruction, but somehow we need to escape that space of this very simplistic model. So what we did next is a Markov chain Monte Carlo based inference. That's that we get the generalization, that we can escape the space of what the CNN is trained on. And we built on those final fitting results from MCMC a new model. And the tricky part, or the key how we made it work, is that we need some kind of quality control at every step. After the initial fit, we have to decide if that was successful or if it went wrong. After fitting the generative model, we have to again check if what we get as a fitting result is anything close to the image or not. Because if we include something in our model and build a new model that has some crappy shapes in there, it doesn't work. So this quality control has to be very conservative and has to make sure that no wrong reconstruction ends up in there. And what we end up with is a 3D morphing model that has some of the basic statistic properties as the model that we get from 3D scans. But of course, the quality doesn't yet reach the quality that we would get from 3D scans. What I like in particular about that method, there are also other methods that have similar ideas, is that this one here really uses very minimal data, and it doesn't use anything that's pre-trained on other data. Every other method that tries to build a 3D morphing model from 2D data uses either pre-trained landmark detection networks or face recognition networks as loss function or whatever. We don't use any other data to train this model than around 100 2D face images and the 3D template face that I show you here, the average face. So after all of that I've shown you, I would also like to acknowledge all the awesome people I had the pleasure to work with. On the right, you see my group that I did my PhD in from the University of Basel, and all the other faces are mainly people that I later met in my career during my stay at MIT, or collaborators all around the world. Some of them I've only seen via Zoom, and also some first people that I started to work here at FIU, and of course my family. Thank you very much for your attention, and as promised, I should be here virtually to answer all of your questions. Thank you very much.
Okay, thanks Berhad for this very interesting talk, and we have some time for some questions. So maybe let me start one. I didn't know much work on face manipulation, but I saw some works on computer vision, like they generate different faces with different emotions, using method that directly apply to the images without using 3D face model. So I'm just wondering, so what's the advantage and disadvantage of using like this kind of 3D deformable face model?
Yeah, you definitely did the right observation. There are plenty of methods that can do such kind of manipulation without any 3D model. The challenge is that for most of those models, you only have frontal faces that you want to manipulate. The moment you would like to manipulate the face from a side pose or like an almost side pose, you either need to retrain that model or you need a 3D model. So it's just a question of how flexible the model should be that you build, and if you're willing to retrain the model for profile views. So most of those other methods that do some kind of image manipulation, the results that you show, that you see are usually only on frontal faces. And that's a challenge for a lot of the data-driven methods. You will find tons of face images online, but the high-quality data sets, the curated high-quality data sets, they're almost frontal. Like they have some near frontal faces, but they have almost no side views. So it's very hard to solve the full pose range in a purely data-driven way, and that's why we prefer to use a 3D model for that.
Okay, thank you for your answer. Another question I have is, like for all those examples that you show in the lecture is more like static 2D images. So what about those applications like generates those facial animations? Like for example, giving a single image of someone and like speech, you want to generate this kind of facial animation. Is this somehow related to this deformable model? And does it apply to generate such kind of facial animation?
Yes, definitely. It's definitely related. It's just not the kind of research I'm doing. That's why it might be underrepresented in my presentation. So there are definitely people who animate from a single image. So you have a single image, you do a 3D reconstruction, and then you animate with some pose change. And again, they're exactly the same as what you commented before. If you don't want to change the pose, you can also work with 2D methods. But there are definitely people doing that with 3D methods. And then also in terms of videos, it's not only on what you want to generate, it's also what the input is. So if you have a video input, you get much more information. So you might be able to reconstruct the face without any prior if you just show enough poses. Like there is now an app where you can scan your face just by going around with the camera. From my perspective, that's less challenging because you have multiple views of the same object. So if you just have one single image, the task is much harder to solve, and you can much easier argue that you need strong priors. And that's why I focus on single images, but there are definitely also people either taking video as input or generating video from single images.
I see, thank you. And also I saw you mentioned that some of your recent work on like self-supervised facial model generation. Like, can you give a little bit more details? I didn't really follow what's the magic there.
Okay. So the magic is that there are multiple different papers that want to learn such a 3D model from 2D data. And the question is, how do you do that? And then what most of those papers have in common is that you somehow take the average face as starting point. So you kind of have one template you can start from, and then the different methods differ mainly in what they take as additional assumptions. And one method, for example, says, okay, we just solved that with a lot of data. And we solved that also with video data. Because as I told you before, if you have multiple views from the same person, it's easier to do the 3D reconstruction. So you can use those reconstructions from video and try to learn a statistical model of faces. We, however, said we don't want to use that because they heavily rely on a landmark tracker, like a tool that tracks feature points in the face, like corner of the eye, tip of the nose, corner of the mouth. And they heavily rely on those detectors and use those detectors to do the 3D reconstruction and to update the model. And our problem with those detectors is that how do you train those detectors? And to train those detectors, you need tons of training data. And we don't like training data. That's why we said, like, can we learn that in a different way? And then what you basically do instead is that we not only learn the face model, but we also learn those detectors. We learn how a face looks like. And what we take as input, as starting point, is really just one template mesh, which is the average face. We do those are the deformations that you have seen, like crazy weird deformations for both shape and texture. And then we train everything just from that very simple model in the beginning. And in the beginning, you can't detect all the faces, but you will detect some faces. And the few faces that you detect, you can fit and 3D reconstruct. And then you update your model. And the moment you have an updated model, you retrain your face detector. So you retrain your face detector and your pose regression. And that way, you will detect more faces. You will be able to reconstruct more faces. And then you will be able to slowly bootstrap your model into something that comes pretty close to a model that's built from 3D data.
Okay. So it kind of, so like previous method, you also start with some average template, but you didn't use some pre-trained landmark detectors. You kind of iteratively do some face reconstruction and face detector to somehow help you to explore more reasonable faces in that large searching space.
It's I'm not 100% sure if I got your question right, but it's not that our method is necessarily better than the method that uses those landmark detectors. It's probably actually much worse. But the benefit is we don't need anything pre-trained. We don't need those landmark detectors that somebody has built from like millions of face images that are manually annotated. So that's the main difference, that we say, like, okay, we don't want any other training data. We don't want any other networks. Others, for example, also use a face recognition loss, which is also trained on a lot of images, or a perceptual loss. And we just omit all of that and say, like, okay, we really want to learn how to detect and fit faces from scratch. So it's more a proof of concept as this is the right way to learn a 3D morpho model.
Okay. And for all those 3D deformable models, like you also not only care about the geometry, you also care about the albedo reflectance. So
yes.
Okay. So you mentioned the latest work, the latest work. It can predict the reflectance and albedo together, but the previous don't. So what's the main challenge here? Why it's like wait so long to get both different aspects can be correctly reconstructed?
Yeah, so basically all other methods before just assumed that the specular map is constant. So they still assumed that there is some specularity, but they just had one constant value over the whole face. So you could still model specular reflections, but not dependent on where they are in the face. And that actually differs. Like on your forehead, you have a different reflectance coefficients than on your lips, for example. And we just built the first publicly available statistical model for that. And already in the average of this specular reflectance, you get quite some information how the specularities are different over the face. And we published that at CVPR 2 years ago. And there were two other methods that basically did something similar. And they also had scans that were collected in the light stage They also modeled the specular and diffuse albedo separately. I think we had more scans. Theirs might be of higher quality, but ours is publicly available and theirs is not. So you can choose which one you want to use.
Okay, thank you. So finally, do you have any suggestions like for the beginners who wants to work along this direction?
Yes. So if you're interested to do something in that direction, of course, there are tons of papers and research talks. But the easiest way to get the feeling for how good or how bad that stuff actually works is to get your hands dirty. So to take one of those repositories of one of the methods that you're really interested in and just try to run it and run it on your own images and see what quality you get. And then you could potentially think about how you could improve that. And one resource we have, which is pretty useful for that, is on GitHub actually a list. It came together with that survey paper that I presented. And that list on GitHub basically summarizes all different tools around 3D morpho models that are publicly available. I will put the link after the Q&A in the chat for those who are interested.
Great, great. Okay, thank you for the wonderful talk and the valuable suggestions. And
Sure.
so I think our second lecture ends now. Thank you very much.
Thank you very much for having me, and thanks for organizing all of that.
Thank you. Okay, now we will take a 15 minutes break and come back at 4:15. Thank you. Hello, everyone. Welcome back. The next tutorial today will be learning to represent 3D shape with programs given by Daniel Ritchie from Brown University. So Daniel, please share your screen.
All right, will do. Just give me a second here.
Cool.
Okay, am I audible? Can folks hear me?
Yes.
Okay, excellent. Great, just had to address one last thing there. And as soon as this thing feels like starting. Wait a minute.
Great.
My laptop is just being a little bit laggy. Hold on a sec here. Okay, well, for some reason, my first slide doesn't want to display, but it looks like my other slides are showing up. So great. So thanks, Rizzi, for the introduction. Thanks for having me today. Good to see a lot of folks in the audience. So today I'm talking about learning to represent shapes with programs, and so I wanted to unpack that title a little bit to dig into what we'll be discussing today. So the first part of this title is learning. So particularly, what kind of learning problems are we interested in? There's a lot of different ways that we might use machine learning to help with creating and manipulating and editing 3D shapes, some of which you've already heard about here and will continue to hear about throughout the week at SGP. For the purposes of this tutorial, I'm just going to focus on two kind of big major classes of learning problem. The first one is reconstruction. Oh, you know what? My images and my slides have disappeared. Let me just go ahead and reboot PowerPoint real quick. That should fix the problem. Give me a second here. Apologies for the technical delay. I'll just double check that this does in fact fix the problem. Yes, okay, great. So once more. All right, so the two problems that I'm going to focus on, we're going to talk about in this tutorial. The first is some form of reconstruction, where our input in this problem statement is some kind of unstructured or noisy or otherwise sort of raw input geometry. This could be in the form of multi-view images or even single-view images, point clouds from some 3D scanning device. And through some complicated function that we learned from data, we want to produce some clean, high quality, or perhaps more structured geometry, something that maybe knows something about the part structure of the object or some other higher level attributes that it possesses. And the second problem is generation or generative modeling, where classically we kind of think of this as having no inputs, but you could also think of it as having a set of random numbers as inputs. Again, we provide this to some function we've learned from data, and what we'd like to produce is some, for each set of random numbers, we produce some random high quality shapes from a target distribution of shapes of interest. So in this case, it could be chairs, airplanes, cars, whatever you want. And if you're a probabilistic modeling kind of person, if you like taking that viewpoint like I do, these are actually pretty closely related problems. Each of them is just trying to model a particular distribution. In the generation case, we're just modeling this marginal distribution over all possible shapes from a particular set class of shapes, where X represents shapes. And in reconstruction, we're saying we're trying to model this conditional distribution of sort of complete shapes X given some incomplete or measured shape Y. Okay, so those are the learning problems we're talking about. So what do I mean by representing shapes? There are lots of different shape representations, lots of different geometry representations out there in the world, each with their strengths and weaknesses. There's no one geometry representation that kind of rules them all. We often use different ones for different tasks, and we transform between them. So I wanted to actually start out this, well, it's morning for me, but afternoon for some of you, with a little warm-up exercise. This is the thing that if we were at the conference in person, I would ask you to go ahead and turn to your neighbor and talk about this, but you know, we'll make do over Zoom. So what are some shape representations that you know about, and what might their pros and cons be, especially with respect to the learning problems that we talked about on the previous slide, in terms of being able to output geometry for synthesis or reconstruction? So let's see. I will happily take raised hands over Zoom from anyone in the audience. I can see everybody's boxes up here on the screen. I see someone type something in the chat. I can't really read the chat very well from here. Someone says, here we go. Got it. Meshes, point clouds, or SDFs. Okay, great. So let's think about meshes, right? Meshes are kind of our classic, most widely used representation in graphics. So if I have a mesh, anybody want to go ahead and offer some ideas about what might be nice about working with meshes? We have meshes, point clouds, SDFs, and voxels, yes. So specifically with regard to meshes, anybody have any thoughts? What are the nice properties of working with these as a geometry representation? Let's go ahead and write this down here, meshes. All right, I see some activity in the chat. So yes, pros, very efficient to represent whatever you want, that's right. So they don't actually require a lot of storage to represent a surface, because particularly if that surface is flat in a lot of places, we can use large planar polygons. Okay, so we'll say they're sort of efficient storage, definitely. That's a great one. Topology, yeah, okay. So Chizang mentions topology. Yes, so we actually do get this notion of surface connectivity. We actually know how the surface is connected. Not all representations give us that. Yes, rendering, absolutely. So they're super easy to render. In fact, so yes, for ray tracing, ray triangle intersection is very easy. And of course, we have decades of technological investment into triangle rasterization techniques. So they're great for rendering. Probably the best representation we have in terms of our pipelines. What about some downsides, especially thinking about this in the context of learning? If we're trying to learn some kind of a model that might output this kind of geometry representation. Any thoughts we have? So Alexander says connectivity can be irregular. That's right, tessellation dependence. So let's think about this. So yes, that's true. We can have irregular connectivity. And why might that be a problem for learning? Anybody have any thoughts about this? See, Sylvia has also mentioned Booleans, right? Yes. So doing Booleans on meshes is actually quite challenging compared to other representations. So Jisho says overfitting on mesh connectivity. Yeah, that's right. Yes, the same shape can have multiple resolutions. So we have this kind of, this is not a plus, this is a minus. We have this kind of, how do I want to call this sort of identifiability problem. The mesh size varies, and it's harder to learn with varying input sizes. That's right. So irregular structure in general is not so great for example, neural networks, which like to process things in batches and very regular computations on a GPU. Yeah, so generally this kind of topological connectivity is tricky. And especially when it comes to introducing meshes with boundaries, or meshes that have that are sort of higher order than that have genus higher than 0, it can be tricky to figure out how to actually train a machine learning model to spit that out. Miles also mentions, yeah, if you want nice UVs, you might also have to have very, very regular topology. So yeah, generating meshes that have nice kind of topological edge flow in the way that a human created mesh would have, pretty challenging. Definitely, I would say, still an open problem. Okay, so this is good. Let's talk about maybe one more. We could spend a lot of time doing this. I don't want to take up too much of our time on this. This is kind of an exercise to kind of get our brains engaged. But what someone also mentioned, I think, point clouds. So we'll take a look at point clouds briefly, and then we'll move on from there. Okay. And I do apologize for my terrible tablet handwriting. Hopefully folks can at least remember what I was saying when I was writing these words. All right, so some advantages of point clouds, and again, specifically keeping in mind learning problems where we want to actually generate or output point clouds. Any particular bonuses or pluses that we get from using this as a shape representation? Kinjal mentions, yeah, easy data acquisition. Absolutely. They're very easy to acquire, right? These are kind of, you get some depth images, you unproject them, you fuse them together, you've got point clouds. Yeah, so Sylvia makes the same point. Yeah. So acquisition is very easy for point clouds. Glad to hear you like it, Sylvia. What else might be nice about point clouds? Maybe anything particularly learning related? Learning on point clouds for those who've tried this or thought about it? Any ideas? Almost. So easy to input or output to a neural net, as Baptiste says. Okay, so Miles mentions, I mean, this is Miles's comment is kind of a corollary to the acquisition. Yeah, you can create training data more easily. That's true. It's probably the easiest form of data to gather in large quantities. Easy to input or output to a neural net. This is kind of somewhat true. We do have architectures, things like PointNet or PointNet++, DGCNN, which are relatively simple. So I'll put it this way. I'll put it so simple. Relatively simple neural net architectures compared to some of the things you might have to do if you were, say, trying to represent convolutions on a mesh surface. Mark mentions there's lack of topology is both a pro and a con. Mark, do you want to elaborate on that? What do you mean by why that might be both a good thing and a bad thing? Okay, yes. So yes, obviously the fact that we have neural nets that work on point clouds relatively easily, that's a pro. And the negatives to having a lack of topology, yeah, basically any operation you want to do on one. So the fact that we don't have any connectivity means we don't really know technically what the actual underlying surface, we don't have a great representation of what the underlying surface is as a continuous surface. We just kind of have point samples from it. So especially if our point cloud is sparse in some regions, we might not know if that actually is a true hole in the surface or whether we just undersampled that particular representation. I'll also add, yes, you know what, Raphael, I was just going to say the same thing. It's not terribly storage efficient because we have to store a lot of points in order to represent, details or just in general, even a large flat surface. Whereas with a mesh, we could represent that with just a couple of polygons. So storage is not particularly great. Okay. We could keep going. This is fun. I do enjoy this. I want to make sure, I want to be mindful of time though, because there's a lot of material to get through. So I'm going to go ahead and just forge on for now, if my slides will let me advance. Let's see here. Okay, great. So the last part of the title that I'm going to unpack is learning to represent shapes with programs. So before I kind of dig into this in a little bit more detail, I want to just provide a couple of notes on some terminology. I'm going to use the term shape program throughout this tutorial to refer to essentially a program that outputs some geometry. In other places around graphics, you might see such programs referred to more often as procedural models. This is kind of maybe the more standard term. Procedural model, in my view, can actually subsume a bigger class of entities. So things that generate textures as well could also be procedural models. So I want to use shape program to be specific to geometry generating programs. And the other thing that we'll talk about is that in general, these kinds of shape programs are going to be written in a domain-specific language, which we'll abbreviate as a DSL, standard abbreviation in the field, rather than a general purpose programming language. So we're not going to be talking about programs written in languages like Python or C++, but in languages that are crafted specifically for the task of spitting out some kind of geometry. Okay, so let's just briefly look at some of the ways of representing shapes with programs that have been proposed so far. So probably the one that a lot of people are familiar with, in fact, I think one of our responses on the chat earlier alluded to this, is constructive solid geometry. So we have some sort of primitive objects. These could be represented actually in a lot of different ways. They could be represented with meshes. In this particular slide that I stole from Ren Ng, thanks Ren, we're representing them as implicit geometry, and we're combining these via some expression tree of Boolean operations, things like union, intersection, difference. You can also do complement, which is not actually written on this slide. Right, and that lets us do some pretty cool things, like take seemingly a very small set of primitives. We can just have things like cuboids, spheres, and cylinders, but create a fairly interesting variety of geometries, particularly useful for specifying manufactured shapes, things that are produced, as a process of some kind of regular manufacturing device. I mentioned that representing these with implicits is actually pretty convenient. This was actually alluded to earlier, that doing Booleans on meshes is very, very difficult because of the topological considerations. But if we want to do CSG, if we want to do these Booleans on implicit surfaces, there's actually very, very simple formulae for doing this, where we can compute the intersection, union, or difference of a couple of different implicits with just these very simple formulas. There's something I'm sort of sweeping under the hood here, which is that these this assumes that these implicits are represented by sign distance fields. And for those who've been following some of the developments that have been going on around geometry processing these days, we now have other kinds of implicit surfaces that neural networks can learn that don't actually have sign distance field properties. And so not all of these rules hold for those kinds of representations. There's also, there's not really a standard class of programs for this, but I'm just going to sort of call it loosely CSG++. You have various kind of CAD modeling packages. OpenSCAD is one of my favorites because it has a nice kind of programmable interface, and it's free and open source, that take your standard Boolean operations from CSG and augment them with other useful modeling operations as well. So you can see, looking at this particular example, we have things like difference and union, which we're used to from CSG, but we also have things like transformation hierarchies. So we can translate something, we can rotate something. We've also got for loops, so we can iteratively specify some more complicated structure. We've also got the notion of being able to extrude some piece of geometry along some axis. So there's ways that we can kind of take CSG and plus it. And then you kind of take this out to its conclusion, and you can start to see some of these feature-based solid modeling languages that are the dominant paradigm in commercial solid modeling tools. So if you ever worked with SolidWorks or Autodesk Fusion 360 or anything along those lines, you have these tools presented as interactive modeling interfaces, but they really do build a program under the hood. And these paradigms for modeling include CSG as a subset. They can do all the CSG operations, but there are many, many, many other operations that involve sort of adding or removing or modifying features on solid objects. So you can see, here we're building a shape by kind of drawing a sort of a cross-sectional sketch and extruding it. And then some of these extrusions also involve operations like cutting. So we're extruding these cylinders and then, sort of doing a joint extrude plus difference. And then we have operations like filleting these edges, which make the model look nice. They also have some nice manufacturing and other properties, physical properties. So specifying these sort of edges around these facets and kind of smoothing them out. All right, so moving away from solid modeling, which is kind of the paradigm where we're most used to seeing these kind of program-based representations. There's also the grammar-based representations that have been popular in graphics. So L systems is one of the most classic examples. Here's an example on the right I'm showing from the Algorithmic Beauty of Plants paper, sort of the Bible of L systems. And this is a language that involves rule-based string rewriting. So all of these little tree-like structures on the right were generated by starting with what's called an axiom, some initial symbol. So in this case, it's just this symbol called F, and we'll talk a little bit in a couple of minutes about what that means. And then these L systems specify a set of rules that you follow to replace. Basically, you scan the string, you find any symbol that's on the left-hand side of the rule. Like here we have F goes to this whole other complicated mess. and you replace that string on the left-hand side with the string on the right-hand side. Of course, if I do that once, now I have a bunch more Fs in my string, and the next time I apply this process, I'll expand it out even further. And so you kind of iterate this either for some fixed number of iterations or until there's no more rewrites possible. In this particular case, all these L systems are infinitely recursive, so we would have to force it to stop at some point. Okay, so that gives you a big old string at the end of the day. It doesn't actually give you any geometry. And so then the process that follows is we actually take this final string that comes out of this, this iterative substitution process, and then we pass it to some kind of interpreter, which sort of scans the string, basically interprets it like a program, and converts that string into a geometry. Many different ways of doing this, but this sort of shorthand that's being used on this image is this kind of paradigm where you imagine you have a little pen that's kind of placed on the paper, and the F command says, move that pen forward by a fixed amount, drawing a line as you go. The plus and minus commands indicate that you should sort of turn left or right by some fixed amount. And these brackets indicate pushing or popping a stack. So basically sort of saving the pen position and being able to return back to it once you finish some particular set of operations, which is how you can get these recursive branching structures. Once you finish going off to some branch up here, the stack pops and you might return back down here somewhere. So these are most widely used, super widely used in graphics to model trees and vegetation, because they can be used to model lots of interesting natural growth processes, but they're useful in lots of other domains as well. So we've seen them used to produce architecture, to produce patterns for graphic design. There's lots of different use cases for this kind of tool. There's other kinds of grammars aside from L systems. So some folks might have seen shape grammars before. These are also based on a set of rewrite rules. You have an axiom and you have a set of rewrite rules. But what kind of separates shape grammars from L systems is that these don't operate on strings. They actually operate directly on geometry or on space itself. So your axiom, in this case, this is the example that I'm showing on the right, the axiom is actually a little square, and the rule specifies what to do when you see one of these squares while you inscribe another square into it. And you can iterate this process and end up with this kind of interesting sort of spiral structure of, quadrilaterals inscribed in each other. This kind of paradigm has been applied in graphics mostly for generating architecture or buildings, other kinds of cityscape structures. So if anyone's ever heard of City Engine, which is software that Pascal Muller developed as part of his PhD thesis and was later acquired by Esri, this is used for architectural visualization, for urban planning, also for generating big old cityscapes in movies, visual effects. There is this fairly powerful shape grammar called CGA that is under the hood of that entire system, and it lets you generate buildings, either buildings like the ones on the right, or kind of plots of a city blocks like the one in the middle. I have to take a moment to plug some of the work out of my own group. We had a paper at SIGGRAPH a couple of years back on representing the kind of connected part structure of manufactured objects using programs. And so we had this language called shape assembly, which is kind of this essentially a low-level assembly language, which specifies how shapes are put together. It has a bunch of interesting features. So it has subroutines. So we kind of have this chair, which is specified by a root program that says, it has a seat and a base and a back. But then each of these little proxy boxes for that part of the structure are subroutines, which then expand into, generating some other parts, like the back has this more complicated structure and the base has these 4 legs. You can declare these parts just as cuboids, kind of proxies of what the part geometry might look like. And then we have operators that let you specify how these parts are attached to each other. And that's what these little red dots here on the diagrams indicate as these attachment points. And there's a few other things like, we've got different kinds of symmetry groups, a couple of other higher level operations, little macros that let you do things like squeeze parts together, just kind of syntax sugar essentially. And this was useful. Well, we'll see what this was useful for a little bit later on. And then there's just, there's a whole host of other procedural modeling tools out there. One of the most popular ones, if anyone's ever played with Houdini, which is one of your kind of big 3D content creation packages, you can do a lot of things with it, like you could do with Maya or 3ds Max in terms of modeling, but it's also especially well known for its procedural modeling capabilities. You can't quite see it super well in this diagram, but there's this kind of node-based visual programming interface down here. So basically, you're kind of specifying a sort of a functional a functional program that has this data flow of how data flows from one operation to another via this visual programming interface of specifying each one of these little nodes represents some kind of function or operation on the data. And you can do things like build this super complicated tower. All of this was built procedurally by instantiating different bricks and sort of saying how they should stack together in kind of a spiral pattern and things like that. Okay, let's see. Great. So kind of wanted to ask you folks in the audience, is there anything I missed? Is there any other interesting procedural or programmatic shape representations that you've encountered out there in your experience? I'm always looking for more examples, always trying to find things that I might have overlooked. So anybody? It's a couple of minutes. Miles mentions wave function collapse. Procedural, but maybe not programmatic. Yeah, wave function collapse is interesting. It's kind of, yeah, it's kind of related to like texture synthesis in a way. Yeah, I think it's not, so you sort of program it by providing it examples. There's not really a way to write sort of programs in a wave function collapse language. The author of wave function collapse actually has a new system out called Markov Jr., which actually is programmable. I would actually encourage you to take a look at that. It can do some pretty cool things. So yeah, maybe that's one that I should have mentioned here, is that system. Any other thoughts? Any other things people remember seeing out there? Okay, well, seems like that's about all. So I'll go ahead and move on now. So again, I'm going to throw a question back to you. So now that we've seen some examples of different kinds of programmatic or procedural shape representations, I want to just, keeping in mind these learning problems that we were thinking of reconstruction or shape generation, where our goal is to train some kind of a function that can output geometry, or in this case, if we're thinking about programs as a shape representation, we want this function to output programs, and then those programs themselves could generate geometry. So what do we think might be some strengths and weaknesses of using programs as a representation for shapes? Just based on some of the examples that we've seen. Any thoughts people might have about what might be nice or not nice about these representations? Baptiste mentions parametric representations such as splines. I'm not sure if maybe that was an answer to the previous question about other kinds of procedural representations. No worries, totally fine. Yeah, so on this particular topic, An says it could enable better shape manipulation. Yeah, that's actually a good point. So we saw, for example, in that little video from Houdini, where we had the fact that you could just tweak a few parameters and you could change things like, the number of steps that were in the spiral staircase. So they definitely have really, really powerful editability or editing capabilities. You can there's a sort of a high level, fairly readable structure, and you can manipulate these attributes that then cause pretty neat, like potentially even broad scale changes to the geometry. Much harder to do that with something like a mesh or even one of these parametric, like say surface spline representations that Baptiste just mentioned. So editing seems great. That's powerful. Baron says shape analysis might be more difficult if your program representation is Turing complete. Yeah, that's a good point. Let's see. Hold on, I'm trying to scroll up to see these comments. Computing derivatives of the shape with respect to parameters. That's interesting. So if we wanted to actually be able to see how a shape would change with respect to some of these parameters, we might like the language to be differentiable. Karen says it could be hard to get the level of abstraction right. What kinds of abstractions are actually intuitive for users as opposed to just mathematically convenient? Yeah, so you can come up with a program that can represent a shape, but is this actually going to expose useful editing controls? Thibaut says a weakness is evaluation of the shape program can be costly. That's true. So yeah, it depends on how much logic goes into producing it. Raphael mentions it can be described by text, so you can use all the transformers for NLP for learning. This is a good point. I will mention this. So learning is actually quite nice for this. You don't want to have to debug your shape representation for edge cases. Yeah, that's a fair point. So we've identified some weaknesses. So potentially like speed of execution could be a problem. We also mentioned bugs could be an issue. Although I was going to scroll up to see what else was mentioned here. Right. So analysis could possibly be challenging depending on. I'm gonna call this a plus or a minus because I think sometimes a text-based representation can actually make analysis simpler. Okay. Good. Really interesting ideas. I really appreciate seeing these. I'm gonna try to save some of the. I'd love to save this chat history so I can actually look back at some of these and think about this. All right, so I'm going to give a couple of my reasons for why I think programs are good, and I'll also talk a little bit about some of the downsides, particularly as it pertains to learning. So some of the advantages, this is something that is particularly relevant to kind of more vision or reconstruction applications as a form of regularizing geometric structures. I'll talk about what I mean by that in a minute. The ability to interpret and edit the shape, we've seen that, but I'll talk about it a bit more. There's some interesting kind of high-level reasoning you can do if you have this program representation, and then the ability to do abstraction and composition. Of course, finding the right level of abstraction can be challenging, but if you can pull it off, there's some really interesting stuff you can do here. Okay, so I'll just go through a few of these in a little bit more detail. So what I mean by structural regularization is if we have program representations of shapes or even just visual entities in general, it can actually help us correct some mistakes that a reconstruction or vision system might make. So here's an example from a paper that Kevin Ellis and I and some others did a few years ago, where we built a system that would take these 2D sketches of diagrams, the kinds of things you might see as like a, like neural network architecture diagrams or other kinds of things that might show up as like something you might use LaTeX to create. It'd take the sketch and it would turn it into this kind of sort of C-like programming language that had the ability to declare primitives and parameterize them, organize them into looping structures, things like that. And so there's this example that we saw where we had this input sketch that looked like this. And if we just ran this through kind of a computer vision system that used some sort of convolutional neural network to interpret what it thought each primitive was, each object in the scene, then it would produce something like this, where it saw this kind of little smudge, this kind of imperfection in the sketch, and it sort of made the mistake of assuming, oh, that must be intentional. And so I'm going to interpret this not as a straight line, but as a line with an arrow, right? That's a valid construct in a diagram. But we as people can look at this and say, well, that's not really right. I mean, we can see that these three columns actually form, there's just repetitions of the same pattern. And so we kind of know that this pattern means that this interpretation must not be valid, that really this should just be a single straight line. And so if we have a way of representing this as a program, and we're trying to impose this kind of prior that, a simpler program is probably a better explanation for the input sketch than a more complicated one, then, naturally this will emerge as a consequence that, we'll sort of simplify away that little imperfection. You can also do this with sort of 3D examples. This is from a paper. I was not involved in this paper, but this is a similar system for taking 3D objects and turning them into programs. Again, sort of a C-like programming language that's sort of specific for specifying these kind of furniture objects. And so here they were working on single image 3D reconstruction, where I take an input photo of an object. And if I have some, convolutional neural network that takes that image and spits out, say, a voxel grid representation of the geometry, I might get something like this, which is, broadly speaking, it's kind of describing the right shape. Like you can recognize that thing as a swivel chair, but it has lots of these weird sort of bumps and errors kind of in the surface. But if I instead ran this through a system that tries to infer or induce a program that represents the shape, the program doesn't actually have in its output space, it actually can't output any geometry that has these weird bumps and wiggles and stuff in it. So because the output space of the program is restricted by construction, it means that we can't actually generate some of these types of errors that lower level reconstruction systems would. So that's actually quite a nice property. And in this case, this is an application where we actually happen to have the ground truth 3D model for that particular input photo. We actually know what, like literally what product that chair is, and we have access to its original CAD model. And, I think that the sort of program version is a closer match to what the ground truth actually was. My slides seem to be frozen again. There we go. So another thing we can do, so I mentioned that the restricting the output space, this property that the programs restrict their output space can kind of get rid of some of these errors in outputs. There's also ways you can do this to prevent kind of broad classes of invalid outputs. So this is an example of the shape assembly language that some of my students and I worked on, talked about earlier. And we use this to work on the task of reconstructing these kinds of part structure programs from point clouds. So we have these sort of input point clouds that represent various kinds of chairs. And there were other systems prior to the work that we did that looked at trying to recover this kind of part level structure of these objects. So one of them was the StructureNet system. And if you tried to use it to take these point clouds and convert it into their representation, which is kind of a hierarchy of boxes, it would do okay, but you get these cases where you have boxes sort of overlapping in weird ways. Doing these things that we recognize as people are very non-physical, like parts don't actually connect to each other that way. And the nice thing about the shape assembly language is it has this, in machine learning, people like to talk about the term inductive bias. So it has this inductive bias that's built into the language that parts have to be kind of physically connected to one another. And so that means that when we tried to optimize for or infer a shape assembly program that matched the point cloud, we actually couldn't even generate some of these kinds of errors. The language just wouldn't support it. So this was a nice way of preventing these kinds of invalid outputs from happening in the first place. Okay, so this is probably the easiest one to understand. The easiest advantage of programs is their interpretability or their editability. So one of the cool things we can do with this is, we can fiddle with various parameters the programs expose. We know, if I could take, this is from this sort of LaTeX diagram program induction system I showed earlier. We can take this kind of graphical model sort of diagram, infer a program for it, and then just take this sort of loop limit in the for loop, change it from 3 to 5 and re-execute. And now I get sort of a generalization or an extrapolation of that program. And we did this for a whole bunch of different kinds of diagrams, hand-drawn diagrams, to get lots of interesting extrapolations. Here's an example from our shape assembly system where we built a little, this is actually part of a user study, but we built a little interactive tool for editing these programs, which, let you kind of fiddle with these high-level parameters to adjust the shape to look like a target shape of interest. A really powerful application of this kind of editability is, again, in sort of solid modeling or product design, is this concept of reverse engineering, being able to look at an object and say, I want to now see the underlying process, sort of constructive modeling process that was used to build that thing in the first place. And so this is actually an output produced by a system that some students and I built in collaboration with Autodesk Research, where we would take this input model and break it down into a series of solid modeling operations. So here we add this, first we add this sort of big cuboid and sort of plug another cuboid on the side of it. The greens represent additions and the reds represent subtractions. Kind of deleted these sides, deleted this big chunk in the middle, and then kind of removed these little pieces on the side. Okay. Obviously, we can go into lots of more examples there. We've already seen some of them earlier. I also wanted to focus on some of the interesting kind of higher level reasoning capabilities that programs give you because they expose this higher level structure of the geometry. We can do things like, say, if I ask you, here are some 3D shapes. In this case, these are actually, shape part proxies. They don't actually have the full resolution geometry, but they kind of give you a notion of the structure of the shape. And I can ask, well, what are the most similar, I can do some shape retrieval, right? I can say, what's the most similar shape to this one that I have in a big database? And if I do this based on geometric similarity, I look for its geometric nearest neighbor using something like a chamfer distance, I might get the results that you see on the top row. But I can also, if I have a program representation of these shapes, I can ask for what is the sort of lexical nearest neighbor, the program in my database that looks the most similar in terms of its textual representation. And here I can get some interesting results where these things don't visually always look all that similar, but in some sense you could argue that they're actually closer semantically because they have the same part structure, they have the same way of declaring and connecting parts. And so it's actually easier to turn, say, this shape into this one than it is to turn this shape into this one. And this could be useful for different applications. There's also some fun stuff that we've done on looking at analogies. If I sort of say, okay, I take these two, in this case, these are images of very simple scenes. You could also do this with the shape programs that I showed before. If I say, okay, A is to B as C is to what, and I ask this of, say, a deep autoencoder, and I kind of do like latent space, like arithmetic, where I say I take the vector between the latent space embeddings of A and B, and I add that onto C, and then I decode that again. I'll get some garbage like this on the right. Whereas if I do this in program space, if I actually sort of figure out what are the diffs between the programs that describe these things, then I get the representation, I get the output that I actually want. I think the thing that makes the most sense. And you can do this for a couple other applications here as well. Okay, and lastly, I want to talk a little bit about abstraction and composition. So, one of the nice things about representing things as programs is we can also then start to do things like discover subroutines in programs. So this is an example from a paper that some students and I had at SIGGRAPH last year, where we had these programs that represent these kinds of object structures like chair structures or table structures. And what this animation is showing is every one of these boxes that's of the same color is basically finding in these programs kind of common substructures. And so it's able to find these common substructures, realize that, oh, actually, all of these programs have like this instance, for example, all of the yellow boxes, these all kind of represent the same kind of thing, just maybe with some parametric variations. And so we can identify those commonalities, we can abstract them into a little function, a little subroutine. And now we can do things like, for example, here's one of the subroutines we discovered. The system didn't discover that this should be called four-leg base. We named it that because that's what it appeared to be. But this is pretty nice. This is a program that just takes as input a sort of a piece of geometry, or perhaps a little local subprogram that represents the geometry of an individual leg. And then it just exposes two parameters, one which controls sort of the size of that particular leg, and one that controls the front-back distance. And this actually seemed to be the most kind of compact way to represent all of this kind of variation that occurred in this data set of programs. So we really were able to kind of collapse a lot of complexity into this very simple abstraction. And the nice thing about this is it allows for better editing. So here's an example where we have a couple of table programs, and the user goes in and makes edits to these different parameters of the programs that are shown in red here. And when we do that, we get some problems where sometimes the shape kind of comes apart in slightly weird ways that we don't expect. And the reason for this is that there's actually there's correlations between these parameters that if I edit one of them, I really ought to edit another one as well in a corresponding way in order to make the shape kind of retain the structure that it starts with. And so when we edit these raw programs, it doesn't really do that. But then when we go ahead and run this process of trying to discover these higher level macros, these higher level abstractions, we refactor the programs using those high level abstractions. And then we make essentially the same sets of edits. We discovered that these macros that we discovered actually enforce these parametric relationships. And so now the structure of these shapes kind of stays the way we want it to after we've made these edits, which is quite nice. Okay, so briefly, I know some folks highlighted some reasons why these programs might not be nice in terms of taking a while to execute or having to debug them. In terms of learning, there's a couple of things I wanted to point out. One is that their geometric expressiveness is limited by construction. So in that example I showed before, where this was the target shape we were trying to reconstruct from a single image reconstruction task, and this was what our sort of program prediction system spit out. this was really the best matching program that we could get. And it's good, it looks good, right? There's no obvious errors in the surface that we produced, but it's also not a perfect match to the target. And one of the reasons for that might be that the language actually doesn't have a way of specifying these kinds of arm structures, right? Where there's sort of a hole in the middle. And so this is kind of one of the weaknesses of these program representations, is that they can only generate what they can generate, right? The language, the operators, the primitives in the language kind of constrain the possible geometric outputs. And so if you try to use it to represent something that isn't within that sort of the range of those outputs, there's going to be some approximation error. So it's sort of a trade-off, right? You end up getting to remove the ability to generate all kinds of geometric errors, which is nice, but you might also remove the ability to generate some kinds of geometry that you would like to be able to see as well. So you have to kind of figure out where you want to be on that trade-off space. The other really big issue for learning, which we'll revisit actually multiple times a little bit later on, is that it's difficult to obtain data in this form, right? To actually obtain programs that describe shapes, particularly at large scale, that if we want to do something like deep learning. And that can be an issue that we'll talk about later. Okay, so these are the learning problems that I said we'd be interested in for this tutorial. So we have our reconstruction generation. So let's suppose we're taking a look now at these, this core part of these problems, which is this function that we're going to learn from data to reconstruct, to either reconstruct a shape or generate shapes. And so what class of function we should use here? I think this is kind of non-controversial that we're going to use some kind of neural network, because these are very flexible, powerful function approximators. But the more interesting question, I think, is what kind of neural network architectures would actually be appropriate for outputting program-like data? So this is actually a question to all of you in the audience. If I'm trying to produce a program like the ones that we've seen before, what kind of a neural network might I want to use to do that? This might be a little different than what we typically use in geometry processing. Anybody have any thoughts? Watching the chat. Baron says some kind of sequence neural network, like RNN or transformers. Okay, I'm liking it. Yeah, I think this is a good idea. So let's see. My slides seem to have frozen again. There we go. So in general, yes. So these kinds of sequence models are what we would refer to as language models. Because really, ultimately, if you want to kind of break it down to its lowest level, a program is just a sequence of tokens, just like a natural language sentence is a sequence of words. And so, yes, we can repurpose the same architectures that are used in NLP for things like natural language generation. There's actually, if you want an example of this at a much bigger scale, if folks have seen OpenAI's Codex system, which translates natural language problem specifications into code, this is exactly what they're doing. They're using large-scale language models to do this. And so this is a system where essentially what's happening is I specify the input to the system is the comment string in green, which gives sort of a text description of the problem to be solved and a couple of input-output examples. And then the system is supposed to return a program, in this case in Python, that actually solves that problem. So, the big dominant approach here nowadays is to use transformers. So these older language models that I've seen referred to in a couple of comments, things like recurrent neural networks, gated recurrent units, long short-term memory cells, kind of fallen out of favor. And these transformers are basically the new norm. There's really not time in this tutorial for me to do a sort of a comprehensive overview of how transformers actually work. But I did want to mention really the key idea for those who haven't been exposed to them before is this notion that in a sequence of tokens, we're going to try to predict the next token as some function of a weighted combination of features from all the previous tokens. Essentially, the transformer looks at or attends to all of the previous tokens, decides which ones matter the most for the prediction task it's currently trying to make. And this notion of sort of looking at all of your previous tokens and figuring out the right weighted combination is something that we call self-attention. So I am going to give a super brief overview of self-attention because I think it's a it's a pretty important concept that shows up everywhere these days, even actually in other forms of geometry processing. So the big idea is that I have some sentence, and I'm trying to essentially, I'm going to compute an output vector for each word as a weighted average or weighted combination of other feature vectors that are extracted from each word in the input sentence. So I'm showing here an example from natural language processing, but you can imagine these could also be text tokens describing a program. So here, what we're figuring out is that in this particular example, the system, this transformer is learning that to represent the word it, well, that should sort of pay attention to mostly the animal, because in fact that is what the object it refers to. So these colors, the darker colors, are showing higher attention weights. So the way this actually works is we start with this word, in this case the it word. We compute something called a query vector. So all of these words would start with some initial word embedding. This can be a learnable constant. In this case, you might use something like a word2vec system that actually produces an input word embedding. We have some small neural network that converts that into this query vector. And we do the same for every other word or token in the sequence. We have a small neural network that takes its initial embedding and produces a key vector. And then we basically just compare these. We just take dot products between them, which computes a score. And then we also have, again, another simple neural network function of each thing's initial embedding. We have value vectors for each word. And these value vectors, we just take a weighted combination of them, just multiplying the scores by the value vectors, summing them all up to produce the output vector for this particular word. So for these, for generating sequences, which is a kind of a particular form of transformer, there's this variant we call masked self-attention, where all I've done here is I've just deleted, let's see if I go back, I've just deleted all of the words that come after it. Because if we're generating a sequence and we're trying to figure out, what should this word attend to, it can't see any of the words that come after it because those wouldn't have been generated yet. So that's just this concept of masking out attention on the words that haven't been seen yet. And so in principle, if you were using this to do natural language generation, you would then use this output vector R1. You'd feed that into another neural network, which would predict some probability distribution over all the possible words that could come after it in the sequence. In practice, most of these transformers, if you look at things like OpenAI's GPT-2 or GPT-3, they actually stack many of these layers end to end, so that this R1 vector would actually become the input word embedding for the next layer. So they would actually stack many of these self-attention layers onto each other, and only at the very last layer would you take the output word embedding and use that to predict the next token in the sequence. Okay. So that was a crazy fast whirlwind overview of self-attention, just because I think it's an important concept. Obviously, not a lot of time to go into transformers in other detail. I did want to mention there are other architectures that folks have used aside from transformers. If you know something about the structure of the program beyond just, it's a sequence of tokens, there are other kind of tricks you might be able to play. So in this the shape assembly paper that came out of my lab a few years ago, we actually represented these programs using a hierarchical language model. So we actually knew that these programs had this kind of hierarchy of function calls. And so we could represent that as a tree structure. And then within each level of the tree, we would have a language model. At the time, we used a GRU, but probably nowadays, if we redid it, we'd use a transformer and use that to represent the program. So we kind of baked the hierarchical structure into the structure of the computation we use to both process and to generate these kinds of programs. Another one that I don't have a great example for, but which I think you could do in principle, is use graph neural networks. So in particular, if you have a program that is not, say, an imperative language or a functional language, but is actually more of a relational program that describes constraints, say, between entities, then I think a network that generates graphs would actually be a perfect way to do that. There is one other kind of a detail I wanted to mention, which is that really everything I've talked about so far has been about kind of neural networks that predict the structure of a program, kind of what like atoms, what operators are in the language. But these shape programs, when we represent geometry with programs, we have both their discrete structure, things like, what geometric primitive to instantiate or what operation to use to combine primitives. But we also have continuous parameters like shapes, like sizes and, colors and things like that. And so when we're generating a program and we actually need to produce a continuous parameter as part of the output, there actually can be multiple viable values that a parameter could take on at that particular point. And so there's an interesting question as to how we should try to model those values. And there's a lot of different techniques that folks have used. This is just kind of a sort of a tips and tricks slide that I wanted to make sure to get in here. One is just to discretize the space of values that parameter could take. Either you kind of discretize it uniformly, or perhaps you try to do some sort of adaptive binning based on the values that parameters take on in your data set. And then you can just treat that parameter like any other discrete token, predict it as an output of, as a transformer or something like that. That actually works pretty well in a lot of applications. There are some other systems that have tried to maintain these as continuous values and actually try to have the network predict the parameters of some continuous mixture distribution, like a mixture of Gaussians or a mixture of logistics. This can also work. I think it's a little harder to train, but people have had some success with it. And there's another fun idea, which I haven't seen done a ton, but I think it's interesting, and I think it'd be fun to play with more, which is that programs often involve variable reuse, right? We don't just always write in constants in every single time that there's a continuous parameter in a program. Sometimes we declare a variable and we reuse it multiple times. And so there's some classes of neural networks. You might take a look at pointer networks as one example, which actually have a way of kind of indexing into previously generated values in the program and using those to fill in sort of new values later on in the program. So I think that's actually a pretty powerful idea. Okay, so let's suppose that we've chosen an architecture. We're going to use transformers, say, for our reconstruction and generation tasks. The next question we have to ask ourselves is, how do we actually train these networks? Or we have to somehow figure out how to set up a learning problem. And as is the case with all of machine learning, the most reliable approach here is going to be to do supervised learning, where basically what this means in this context is we're going to collect a data set of shape programs, which I'll call X. And those, if we wanted to do reconstruction, we could execute those programs and maybe process them, maybe sort of synthetically scan them, whatever, to produce the sort of input geometry Y. And now we just have kind of a standard supervised learning setting. We can do likelihood maximization, whatever kind of training we want to do to learn these systems. So big question is, all right, so if we want to do this, what data sets like this exist? What data sets are out there that actually have large collections of shape program representations? So there's not a ton, but there are some that I think are worth highlighting. So I've mentioned the shape assembly work from my lab. I've got the URL here, and I'll put these slides up later so folks can take a look at these links in more detail. But this is a data set of these programs that describe the kind of hierarchical part connectivity structure of a few types of furniture objects. These are all derived from PartNet data, for those who've worked with the PartNet data set. There's also, if we're looking at sort of CAD solid modeling, there's the Fusion 360 Gallery data set, which actually has a few different sub data sets, but in terms of program representation, we mostly want to focus on this one that has basically a bunch of objects. And for each one, it has a sort of a feature-based modeling program that creates it. It's not a fully fledged feature-based modeling program. It's limited just to the operations of sketching a cross-sectional curve, extruding that to form a generalized cylinder, and then potentially optionally performing some Boolean of that extruded geometry with some other piece of geometry that's already in the program. But still, even with that, you can already formulate quite a lot of interesting shapes. We're showing some examples here. This is a pretty great data set. We've used it for some projects in our lab. And then a similar related data set, which is actually, I think, a bit bigger, is DeepCAD. Again, these are feature-based modeling programs restricted to sketch, extrude, and Boolean operations. And this is, I believe, derived from the ABC data set, which is another big data set that actually came out of this SGP community. Okay, so I focused on supervised learning. We're going to talk about other learning approaches just a little bit later on, toward the end of this tutorial. So just, if you have thoughts about what could you do instead, hold on to those for a bit. All right, so I wanted to kind of wrap up this part of the tutorial and by saying that all of the kind of considerations we've talked about so far, I think now let us think about like a design space of shape program learning applications where we have, I'm going to identify 4 kind of key axes of that design space. And we can use these to characterize existing works and also to think about how to maybe do new projects in this space. So the first axis is going to be the geometric domain. What kinds of shapes are we trying to either reconstruct or generate or process? There's going to be what learning problems are we tackling with the system? Are we doing novel shape generation? Are we doing reconstruction? Or do we have a system that can handle both? What is the language? What is the DSL that we're going to use to represent these shapes? And then what is the architecture that we'll use to actually generate these programs? Again, there actually is at least one more dimension that I'm kind of sweeping under the rug, which is what is the learning algorithm we're using? I'm going to assume we're talking about supervised learning for this part of the talk, but again, we'll get more into this in detail a little bit later on. So let's try to put some past papers into this design space. So I'll just start with the shape assembly paper from my group, where we had these programs that describe the hierarchical part connectivity structure of these furniture objects. So here, the geometric domain, again, we were talking about part structures of manufactured shapes. That was specifically what we looked at. This is something that allowed us to do both reconstruction and generation. We focused on generative modeling, but we actually had ways of taking unstructured inputs like point clouds, projecting them into the latent space of this generative model and then decoding. And we could also do some further optimizations from there to make the reconstructions better. We had this custom DSL, the shape assembly language that we designed specifically for representing these kinds of shapes. And as I mentioned before, we use this sort of hierarchical language model to both encode and decode these kinds of programs. We can look at something a bit different. So here is CSGNet. This is a paper from CVPR a few years back, which was looking at trying to take these input shapes and figure out CSG tree representations of them. So they tackled a few different geometric domains, mostly in 2D. So things like 2D furniture and 2D logos. This was specifically focused on reconstruction. So there was no generative modeling in this particular paper. Again, classic constructive solid geometry as the language. And their architecture, they used a convolutional neural network encoder coupled with a sort of an older style GRU recurrent language model as its decoder. Okay. There's a few other examples here. I'm going to skip over them in the interest of time, but you can look back at these later if you like. Okay, so at this point, I want to kind of take a little pause and ask, where do we go from here? So I've introduced a lot of different terminology, a lot of different examples of applications that have tried to learn to reconstruct or generate programmatic representations of shapes. And I just want to pause for a minute and ask everyone out there, I want to move into talking about, what are some of the big future works, the big open problems in this field. So I wanted to kind of poll you and see, have you picked up on any potential issues or problems with any of the methods we talked about so far? Anything that you're seeing as something that maybe needs to be looked at in a little bit more detail? So I'll just take a couple minutes to see what people think here. Oh, heads up, there's a question in the Discord. Not sure if you have it open. I don't. I actually don't really have a way to read Discord while I have the screen sharing going. So if anybody wants to repost that here, that would be excellent. Okay, great. I will take a look at that later. So yeah, any thoughts about maybe hold on a second. Maybe this is a question for right now. See. How do you back propagate if the output is a bug? Yeah. So interestingly, fortunately, in all of the systems we've been talking about so far, we've all been talking about supervised learning. And so we can do that without actually having to execute the programs during training at all. All we're saying is we have the ground truth program, and we have sort of stepwise supervision of every single operation we're trying to predict. So that gets around that problem. But you're right that if you didn't have that kind of supervision, and maybe you wanted to try to actually, you had to actually back propagate through the program, if you had bugs or other sorts of issues, that could cause a problem. Yeah. Learning expressive geometry operations as part of the programs. Interesting. Karen, you want to elaborate on what you mean by that? or if anybody else has any other issues they might have noticed, now's the time. How do we handle textures? Yeah, that's a great question. So far I've just been talking about shapes, just geometry. So obviously texture is highly correlated with geometry. And so probably if we want, I could imagine it would be nice to be able to say, build a system that maybe could learn just from images, like the way that some of these neural radiance fields representations can, and learn a procedural representation that has both geometry and texture. Baron has a great point. You have to deal with isomorphic programs, different program strings, which can generate the same output. Yes, that is actually a thing that comes up in most languages. There are multiple ways to represent the same geometric output. And we have to wonder about which ones do we prefer, if any. So I do have a slide on that later. That's a great point. Okay, I think I'm going to go ahead and move on for now, but this is really some interesting ideas so far. Thank you for sharing. Okay, so I'm going to highlight this is sort of my taxonomy of what I think are the big open problems in this field of sort of learning shape program representations. One is just increasing program complexity, learning without supervision or without ground truth programs, what it means to produce a good or usable program, and then kind of a big open question is how do we discover useful modeling languages? So I'll start with program complexity. We can do things like this. This is an example from the DeepCAD paper. We know how to learn how to reconstruct and generate programs that look like this. But how do we move from this kind of complexity to something more like this? This is just an example that someone produced in OpenSCAD that I stole from the internet. So I think that there's a couple of key ideas here, at least a couple of key ideas, probably lots of ideas that we need to have before we can really solve this problem. And those are abstraction and curriculum. So abstraction, we've already seen this before, right? This is the idea of discovering reusable subcomputations so that when we're trying to either reconstruct or generate a big complex program, we don't have to predict every little operation from scratch. We can sort of recognize, I can actually deploy this bigger subcomputation that I've learned. That will be definitely an important way to scale these systems. And then curriculum, which is sort of related, which is, how do we guide the network's training to kind of, nudge it in the right direction, present it with simpler tasks, simpler generation and reconstruction tasks before we have to have it solve more complicated or harder ones. And the reason I'm bringing both these up, I didn't exactly come up with this. This is actually insights from a recent paper called Dreamcoder, again, from my colleague, Kevin Ellis, which I think it really kind of embodies both of these principles. And it's really quite a beautiful system. Kevin is a cognitive scientist and an AI researcher. He's not a graphics person. So he does a lot of work. He does some work on representing visual stuff with programs, but he also does a lot of other kinds of program synthesis. So in this example, these are sort of Lisp-like programs for list processing. And what's happening here is basically he has this setup where he starts with an initial set of very simple Lisp primitives, things like map and fold, basic conditionals, and then has a bunch of input-output problem specifications that he'd like to be able to learn programs for automatically. Just basically, here's a set of inputs, here's the outputs that should be produced. And if you kind of try to teach this system to solve the most complicated list processing problems right out the box, it doesn't do a great job. But if you kind of give it a curriculum, if you order it and say, okay, I'm going to give you some simple ones first, and then it's able to sort of discover, I found this program that solves one of these problems. And this little program is actually equivalent to kind of the list filter function, right? It takes a predicate and it filters for everything in the list that satisfies that predicate. And then if you take this filter function and you add that into your list of primitives now that the language can use, then you can actually try to solve some more complicated programs. Now, with that filter function at your disposal, now you can sort of figure out how to solve the problem that returns the maximum element in a list. And then if you have this maximum function at your disposal, now you can solve an even more complicated program, which actually tries to find the nth largest element in a list. And so there's kind of this idea of bootstrapping your ability to solve more and more complicated problems. And I think something like this could also be really key for figuring out how to infer programs that produce these much more complicated shapes as well. There's some caveats about this system that don't make it directly applicable to what we're trying to do in geometry. One is that this curriculum is hand designed. So a human oracle basically manually sat down and sorted all of these tasks from easy to hard, which is not something we can really do with like in the wild shape collections. And the way that they form that abstraction only looks at discrete program structure. It doesn't really take into account the kind of continuous variables and all the critical relations between them, which is very important as we've seen for visual data. Nevertheless, I think this is a really fantastically beautiful paper. And if you're interested in this field, even though it's not a graphics paper, this is actually published at PLDI, which is one of the programming languages conferences. I highly recommend you take a look at it. It's really quite inspirational. Okay, so another big open problem I mentioned is learning without ground truth programs. So we've said, supervised learning is the most reliable approach to solving these problems. And I asked this question of, well, what data sets exist that provide us with, large collections of shape programs? And the answer was not very many. I was able to, pick out 3 kind of off the top of my head. And this is not surprising, right? It's very hard to obtain source code for large collections of shapes, especially if you're, trying to come up with a new language that you think is useful for modeling these shapes. So here's a question for all of you. What could we do instead? What other techniques might we try to deploy to try to learn how to generate or reconstruct these programs if we only had a data set of shapes? We didn't actually have the ground truth programs that created them. I don't know, any ideas, anything that we might try to use here? It's a tough question, but there are some techniques that maybe some folks might have seen that might be applicable here. Miles says, someone has to bring up adversarial learning. Yeah, like maybe somehow you could train some sort of a GAN that could spit out geometry and then spit out programs, execute those programs, and then check if somehow the executed geometry looked real as opposed to fake. Yeah, like that's the thing you could try. Probably pretty hard. We know that that adversarial learning can be very, very tricky, very finicky. Armand says autoencoder and PCA projection. I'm not quite sure what that would refer to specifically. If you wanted to elaborate on that, Armand, I'd be happy to hear more. Yeah, I mean, so maybe we're all kind of stumped a little bit. This is a pretty tricky problem. Okay, so I won't torture you anymore. Let's go ahead and see what things we might try. So one thing related to this notion of adversarial learning would be reinforcement learning. So there have been some success cases with this. So I mentioned CSGNet, this system that took these kind of 2D furniture or icon images and predicted CSG programs for them. The way they actually did this is they actually used reinforcement learning for a large part of the problem. They did a little bit of kind of supervised learning on some randomly generated data, which helped kind of get them into a good local optimum. And then they used RL to sort of fine tune from there. And so you can see what we're showing here is here's an input shape that we're trying to reconstruct by a CSG. This is sort of not really relevant to us. Here's what the system does if it's just been sort of pre-trained by basically like learning how to reconstruct just randomly generated CSG shapes. And then if we fine tune it with RL, it actually gets considerably better. And they have a few other tricks in the paper to make it even better still. But really the key bit was this right here. There's also this system called Spiral. This is not really for shapes exactly. This is more for images. This is a system, I think, out of DeepMind, which looks at how do we basically learn a program that takes an image as input and figures out how to sort of apply a sequence of brush strokes of varying colors and densities to try to reproduce that image. And this is a system that uses both reinforcement learning and an adversarial loss or adversarial objective in order to solve this problem. Because again, they have no ground truth programs that specify how to do this. Of course, the big problem with these approaches is they are notoriously fickle or unstable. Here's just an example out of one person's blog online about trying to do deep reinforcement learning and kind of discovering, much to their dismay, that running the exact same learning run 3 times, 2 out of 3 times, it just utterly failed. Didn't converge at all. So this is kind of a problem. So another trick that folks have used is to use some kind of continuous relaxation, some way to be able to differentiate through the entire program, and then be able to do backpropagation. This is a little tricky for these kinds of programs because typically they involve choices of discrete structure. Like for CSG, it's am I going to do an intersection or a union? But in CSG, there's at least a couple of ways that folks have come up with to try to say fix the number of possible primitives that can be used, and also the set of possible combinations of them, and then kind of gradually learn through sort of a soft relaxation which of those primitives and combinations should be used and which shouldn't be used. There's a couple of papers, one called UCSGNet, and there's this other one called CSG Stump, which embody this approach. And here I'm kind of showing the CSG Stump visualization is the easiest one to look at. They basically say, okay, I'm going to give the system K primitives. I'm going to have this first layer of operations, which are either identity or complement. That's what these do. And then there's an intersection, a layer of intersections. And essentially what it does is it basically figures out, for each of these primitives, should it be identity or should it be complement? It kind of has a soft relaxation and lets it interpolate between one of those two choices. And then there are all of these, basically every possible intersection could involve every possible input at this layer. And again, there's a soft relaxation, which lets it kind of gradually learn the weights of these, which ones should contribute to which intersections. And eventually, as training converges, it eventually converges to either a hard 1 or 0. Either the intersection uses that input or it doesn't. And then finally, there's a union at the top, which lets it sort of decide which of these intersections it should use to produce the final output. So this is actually pretty cool. I think it's actually, both these papers are excellent. They're really interesting, really clever insights. But the one thing I'll point out is that all of these tricks are domain specific. They're super specific to how CSG works, and you can't just readily extend these to other languages. So anytime you want to try this approach of continuous relaxation with a new language, you've got to sit down, be clever, think really hard, and find some new way to come up with the continuous relaxation of it. And of course, the other thing about these is a little bit undesirable is that they fix the sort of number of primitives, the sort of the complexity of the language is fixed by construction, which is not great if we want to be able to handle more complicated geometries and programs. There's one other approach I want to mention. I want to plug. This is a paper that I did with a couple students, Kenny and Homer, that we presented at CVPR about a week ago, which is kind of an interesting idea. It's a way of extending, sort of approximating supervised learning. So this is specifically for the reconstruction problem, where we're trying to reconstruct a program from an input geometry. And ideally, we do supervised learning. We'd have some paired data where we had, some shapes from some distribution we wanted to reconstruct, and we'd have the ground truth programs for the shapes. And we just use some kind of, we'd maximize the likelihood of that data, like cross entropy, whatever. And so we came up with a few strategies for when labels are missing. Basically, labels meaning when we don't have these ground truth programs, these Z's. One thing we can do is we can try to find some program which is not actually the ground truth program, but which does an okay job at reconstructing the input geometry. And so in this case, we're like our data distribution is accurate, but our programs or labels have a mismatch. So there's kind of it's a little bit wrong, but maybe we can get something useful out of this. Or we can find some other shapes which are not quite from the distribution of shapes that we care about, but where we actually can get the ground truth program. And so we can have this sort of known pairs of shapes X and program Z. And so here our data distribution is slightly wrong, but at least our programs are correct. And so the hope is that by combining these two techniques, where one case where the data the data distribution is correct, but the programs are slightly wrong, and the case where the data distribution is slightly wrong, but the programs are correct, if we can combine these two, we might be able to do pretty well. And so that's what this plaid system that we developed is all about. So there's basically just a bunch of ways that we come up with these different sort of slightly wrong pairs of programs and shapes. So in this diagram, what I'm showing is what we can do is we can take some shapes from our distribution of interest, like maybe we're trying to reconstruct these chairs. We can use some, whatever model we've got currently. Maybe we get this by pre-training on randomly generated shapes. We infer the best possible program that we can find for it. And then what we do is we just say, okay, well, the best possible program that I can find for it, I'm just going to say that is the program which generates the shape. And I'm going to pair those up as part of my training data. Now that's wrong, right? This isn't actually the program that generates the shape, unless this model was already perfect, which it's not. But there's some useful signal there. Another thing we can do then is we can take these best possible programs that we inferred for each shape, and we can execute them to get this shape. And so now what we have is this, we can pair these up, and this actually is the correct ground truth program for this shape, but this shape isn't exactly quite from our target distribution. It might be a little off in some way. But we can do that. That's another way we can produce these pairs of data. And then the third technique we have, this is actually an instance of a much older, well-known learning algorithm that I think Jeff Hinton came up with back in the 80s, called the wake-sleep algorithm. But we can take these best programs we've inferred so far, and we can train a generative model, like a transformer of some kind, and we can generate more programs that look kind of like them. And then we can execute those programs to get whatever shapes they produce, take these, pair these up, and use those as training data as well. They're all just different ways of getting pairs that are slightly wrong, but have characteristics that complement each other. And then the technique at the end of the day is we just basically run learning that looks like supervised learning, but every batch, we just sample a random batch from one of these different methods, one of these different ways of producing these slightly wrong supervised pairs. And the cool thing is, at the end of the day, when we do this, we did this on 2D and 3D CSG and also on these shape assembly programs. I'll kind of skip to the big takeaway here, is that when we combine drawing training data from all these different kinds of methods, we actually get programs that reconstruct the target shapes much better than reinforcement learning, which is this line here, or any of these kind of individual ways of generating slightly wrong data. So in terms of geometric reconstruction accuracy on 2D CSG, 3D CSG, and on the shape assembly programs, it does basically better across the board. It's actually considerably better than reinforcement learning. So here the red curve is RL. I'm kind of plotting its convergent rate as you train it over a certain number of hours. And this green curve is the one that has all of our methods combined. And you can see that basically after, here's where RL sort of plateaus. After like 40 times less compute, we're already kind of hitting the level that RL gets to. So it's way faster, it's way more stable. And it actually requires even less training data. Even if I'm using just 1,000 shapes with this technique, it's already better than a reinforcement learning is with an order of magnitude more data. So it's pretty nice technique. I will say, just to wrap up what we're talking about here. So RL, always applicable, but pretty unreliable. I'd say it's kind of a method of last resort. Use it only if you have nothing else, no other options available to you. You can do these continuous relaxations. These are possible for some domains, but they might require some particular innovations for a new program. This plaid technique that we have developed, I think, shows a lot of promise, but we still need to verify that it works on more complex programs. We've only done it on some fairly simple domains so far. And so overall, I would say that learning without programs is still kind of an unsolved problem. So this is still something that I think needs a lot more attention. So this other this second to last open problem I want to highlight is, how do we know when we've produced a good program? So the existing work that we've looked at so far all just focuses on whether the geometry that the program spits out is good, right? For these kind of reconstruction learning problems, all we've cared about is, does the predicted program's output geometry match the input geometry according to some metric? So here, again, this is the table that I was showing before for that plaid paper. All these metrics we were looking at were things like the chamfer distance of the program's output geometry to the input geometry, or the volumetric IOU of the program's output geometry to the input geometry. But as someone mentioned earlier, in fact, in most of these modeling languages, multiple programs could actually produce the same geometry. And so which of those should we prefer and why? What metrics might we use to decide whether one program is better than another? And in the sort of the broad field of program synthesis, everybody really is making the same sort of Occam's razor assumption. They're assuming that shorter programs are better, that if you can represent the shape more compactly, that's more likely to be an accurate representation, to not have sort of spurious, unnecessary operations. And that makes sense up to a point. But also, as programmers, we know that the shortest program isn't always the best. There's many examples of so-called business card ray tracers. I don't know if you've ever seen these, where someone figures out how to take a fairly complicated piece of code like a renderer and compact it down into something that fits on the back of a business card. So we know that the most compact program is not going to be the most readable, the most usable, the most editable. And so there's really this question we have to ask is, how are we going to produce these sort of good, what does it even mean to have a good program in terms of usability or editability? And how do we produce them? With supervised learning, the network is going to learn to mimic the qualities that are in the ground truth programs you give it. So if we assume that people wrote those, they wrote them well, they wrote them to be usable, then, the problem's already solved for us. But as we move towards learning without ground truth programs, we have to figure out, what kinds of qualities of these programs do we want to enforce? And how do we actually enforce them during learning? How do we actually encourage our network to actually take on these properties in its output? And so I think this is another big open problem at the intersection of a lot of different fields. There's graphics, there's human-computer interaction, obviously learning, and also programming languages. This is an interesting one to look at. And finally, I'll end with this kind of big challenge of discovering useful modeling languages. So, many manufactured objects actually begin their lives as parametric CAD programs. So CAD programs are actually a pretty natural choice as a sort of a target for trying to infer or generate programs for these kinds of shapes. But are they the best choice? And in general, given a particular data set or distribution of shapes or visual data, what language might describe that data set best? Maybe we're talking about a bunch of architecture or other kinds of natural objects, animals even. What language best facilitates some kind of desired interaction or editing operations we'd like to be able to do? And can we actually discover these languages automatically just from the data? I think this is kind of a grand challenge problem in this field that's fun to try to make progress on. Okay, so I'm almost out of time, so I just want to wrap up with a few kind of parting thoughts for folks who might be new students interested in working in this area. The first thing I would say is that, so I mentioned this design space, this kind of 4-quadrant, 4-axis design space for problems in this field. And I think you can use this as a tool to help identify potential project ideas, potential research ideas to work on. So for example, you could try to learn program representations for some new geometric domain that people haven't really done before yet. So like learning to generate buildings or some creatures, or maybe even clothing patterns. These are just a few examples I came up with off the top of my head. You could try to predict programs in a new DSL, even a new one that you've come up with yourself. So here's an example of using Houdini programs to represent kind of procedural rock geometry. Could you perhaps figure out how to infer programs in some subset of the Houdini procedural modeling language? And you can also experiment with new network designs. So here I'm showing an example from CSGNet where they had the CNN encoder, which then passed its features to this recurrent decoder to predict a CSG program. One of the kind of unsatisfying bits of this architecture is that all of the information about the input shape gets squeezed through this narrow layer of the encoder before it's passed to the decoder. Perhaps we could experiment with kind of new interesting ways to kind of connect local parts of the input geometry to local parts of the program space. Like, what would it mean for there to be some form of attention that relates program tokens back to some notion of geometric local regions in the input? And of course, you're looking at learning problems, you could identify other modeling tasks where learning could be helpful and think about, what could you do there? So just to wrap up with a few other little bits of advice, miscellaneous pieces of advice, I think one thing I would suggest if you're interested in this area is to read broadly. So yes, definitely read papers from SIGGRAPH and SGP and CVPR and venues like that. But there's also really interesting program synthesis papers, even synthesis papers that are not really related to visual data at venues like iClear, NeurIPS, or even programming languages conferences like PLDI, like that Dreamcoder paper that I mentioned. There's some real gems here that you might be able to glean some insights from. I would also suggest, take a programming languages course if you haven't done so. It'll definitely give you some interesting insights into, how to design new languages for different kinds of geometric data. And it's also just good as someone who's going to be writing code for a large part of what you do to have some more insights into how these things work and why they're designed the way they are. And lastly, I would say it can sometimes be valuable to adopt this. There's this perspective you'll sometimes hear program synthesis people say, which is that, every machine learning problem is a program synthesis problem. Because, what is machine learning trying to do? Well, we're trying to produce some kind of machine learning model from data. Well, that machine learning model is really just a program. It's a subset of all possible programs. So it's kind of a flippant statement in some ways, but thinking that way can actually let you find ways to apply techniques in unexpected places you might not have thought to. So for example, I had a project in my group, actually we're still working on it, which involved reconstructing shapes via retrieving and placing different parts. And when we kind of realized, actually, you can view this retrieval and placement as a program, we realized that we could actually apply some of the unsupervised learning techniques from that plaid paper that I mentioned. And that was an interesting connection to be able to make. Okay, so I think I'm just at time. I don't know how I managed to do that on time. Hopefully this wasn't too much of a whirlwind at the end. But I wanted to say thank you again to Rizzi and the other organizers of SGP for inviting me. Thank you all for sticking around and listening. I hope this was informative, maybe a little different than what you're used to hearing. So yeah, feel free to get in touch after the conference. If you'd like to talk more about some of these ideas, I've got info here about how to contact me. So yeah, thanks.
Okay, thank you, Daniel. Thank you, Daniel, for this creative, interactive, and actually engaging talk. I think everybody enjoyed this talk. So I think we have time for 1 or 2 questions.
Let's see. I see Karen earlier asked, is there value to coming up with more plausible or human construction histories as opposed to the most efficient or accurate programs? Yeah, I think that exactly gets at this kind of open question I mentioned of, what does it mean to have a good program? Like, we want to reconstruct, we want to produce accurate or high quality geometry, but we also want something that someone can actually work with. And so I don't think anyone's really done the legwork of figuring out how to studying what actually makes these kinds of programs usable. I know there's been work in the broader PL community about how to make programs usable, maintainable, but when it comes to like what is the actual modeling practice that people in, say, parametric CAD really do, I don't know yet. So I think that's kind of interesting. Maybe time for one other question, perhaps.
Maybe I will ask one. So in this talk, you mainly talk about represent 3D shapes with programs. What about the 3D scenes? Do you think it's harder or easier?
I think, yeah, 3D scenes are interesting because in some ways they're, how to describe this? So the relationships between objects and scenes are less, I think, constrained than, say, the relationships between parts of objects, which is both an advantage and a disadvantage. Like in some ways, it means it's more flexible, like you have more leeway to get things wrong in terms of learning to produce outputs, but it also means that like there's just more possibilities of what you can do. So I actually do have a student working on this right now, working at trying to generate programmatic representations of where objects can go in scenes. So we'll see. We'll see how well it works.
Looks interesting. Yeah.
Okay. So I actually did want to answer this last. Felix mentioned, he said the grand challenge would be to discover the best language for a given domain automatically. Isn't the best language the language that artists, designers come up with to express what they want to do? Yeah, that's a great question. I think that the idea would be that we can't expect that any automated system to be able to do this completely on its own. I think the idea is to say, could I take a sort of a distribution of shapes and produce, like, suggest possible languages to somebody, someone who might want to work with them, and then to figure out, which ones actually work better. I never want to suggest that somehow we're gonna automate away the role of either artists, designers, or even kind of technical artists who are creating these languages. Really, these tools are intended to augment their capabilities and make it so they don't have to spend as much time doing the tedious stuff and have more time doing the cool stuff. So yeah.
Cool.
Right.
Okay. I think time is up. And let's thank Daniel again for the very interesting and inspiring talk. Thank you. Thank you very much.
You.
And if you have any other questions, you can post it in the Discord, and Daniel can answer those questions later. Thank you, Daniel.
All right, thanks.
So we will have 10 minutes break, and we'll be back at 6.
Hello everyone, my name is Hao Su. I am a professor from UC San Diego. Today, I'm very happy to give a short lecture on a popular problem, deep learning on point clouds. We will discuss some representative algorithms of the field. Due to the prosperity of the field, there are many concurrent works. I will just pick the ones that are pioneering or the most familiar to me. Pardon me if I'm not able to cover your work or your favorite work. So here is the agenda for today's short course. Now first, I'm going to introduce why we are interested in point cloud. And then I'm going to introduce some of the representative algorithms. We will start to introduce the backbone network architecture design for point cloud analysis. And then we will show a few applications with some featured interesting perspectives. So why we are interested in point cloud? So we are interested in the geometry of objects. And point cloud is perhaps the simplest representation of 3D. Usually it's made of points sampled from the surfaces without connectivity information. For some of the applications like physical simulation, the points could also be from the interior of the object. And mathematically, a point cloud is a collection of XYZ coordinates, or a set of coordinates. And for each of the coordinates, sometimes it comes with the normal information. The simplicity of point cloud makes it easy to be captured. And a lot of times, that's the only thing available. For example, in autonomous driving scenario, if there's a LiDAR scanner installed, then it's able to capture the point clouds when the car drives. And then in indoor environments, Kinect is able to capture the depth maps and fuse into a point cloud. And for the stereo technique that could be used indoor or outdoor, they also give us point cloud. Well, it's worth noting that for the point clouds we obtain, they usually face a lot of challenges. Like the resolution might be limited or might be different given different types of sensors. And there might be the occlusion caused by other objects, or there are self-occlusions. And there could be noise due to the sensor sensitivity, and there would be registration issue that happens at fusing the point clouds along the temporal frames. And the simplicity of point cloud also brings in a second advantage. There's no connected information, and therefore it's often easier to handle. For example, point cloud is sometimes viewed as a canonical representation of the surface. And if you add connectivity, there might be many different ways to add connectivity, but actually corresponds to the same underlying surface. And you will see this point when you see those follow-up algorithms. Next, let me introduce the backbone networks for point cloud analysis. Well, the fundamental challenge of applying deep learning on point cloud data comes from the irregularity of 3D data. Now, most successful deep learning algorithms assume regular data as input or output, such as images. Now, images are 2D matrices of intensities and colors, and this allows the convolution operation, a most basic building block for convolutional neural network. In contrast, point cloud is, well, an unordered set of point coordinates, and the convolution cannot be applied. So for the next, we're going to introduce PointNet, which is a kind of deep neural network architecture specifically designed to process the unordered point sets. It achieves end-to-end learning for unstructured and ordered point cloud data. If we think a bit more, then we should realize that for a neural network to process the point cloud, it has to satisfy two properties: the permutation invariance and the transformation equivariance. For now, let us assume that a point cloud is stored in the memory as a 2D array. It has n rows, and each row corresponds to a point, and d columns, each column corresponds to a dimension. For example, the x and y coordinate or their normal information. Assuming this 2D memory layout, let us introduce the permutation invariance first. Now, by permutation invariance, we mean that if we change the order of the points stored in the memory, like you permute the rows of this 2D matrix, then for the function or the neural network to process this 2D array, the output value should not change. Mathematically, a neural network is just a function, and then in a functional view, a permutation invariant network just corresponds to a symmetric function. Recall the definition of the symmetric function. For any ordering of the argument, the function value is always the same. And many functions are symmetric. For example, the max function is symmetric as it is order invariant. The summation function is also symmetric. So guided by this observation, we can construct a symmetric function on 3D points in this way. First, we transform each point independently and identically by a small network. Then, we aggregate the point transformations by a simple symmetric function. Lastly, we post-transform the aggregated information by the small network. And this network always corresponds to a symmetric function. But the one question still remains: can any symmetric function be approximated by this simple network? Well, interestingly, we can show that any symmetric function that is continuous can be arbitrarily approximated by PointNet. Of course, if you want higher accuracy, you will need more internal neurons, which corresponds to, for each point, the output dimension by the H network should be higher. This is really great news. Now let's take a look at a neural network that's used in practice based upon the PointNet architecture. So the input is the n by 3 matrix 2D array that corresponds to a point cloud of n points, and each point is just x by z. So for each of a point, it will be transformed by several MLPs. And in the end, for each point, it becomes a high-dimensional vector, 1024 dimensions. And there are n points, and therefore, the intermediate representation is n by 1024 matrix. And then we will do a max pooling. Note that this pooling is done for each of the column. And therefore, in the end, the entire shape is represented by a 1024 global feature. And then we will have a post-processing MLP that will predict the semantic category of the shape. And therefore, in the end, we get K output scores. This network can also be extended to do shape segmentation. Here, for each of a point, there is a local embedding that's 64 dimensions. Now recall that we have the shape level feature that's 1024 dimensions. So we just replicate the global feature and concatenate with each of the local embedding of the points. And that gives us each point as 1088 dimensional vectors. So we can run a few MLP layers to predict a per point semantic label. Now here is the characteristic property of PointNet, which is that it's pretty robust to data corruption. We use the faulty cloud shape classification as example. The x-axis is the ratio for the missing data. And one axis is the accuracy. And we can see that as we are missing a lot of data, the PointNet performance is quite stable. Whereas the baseline approach, which is to do the 3D convolution on the volumetric representation, the performance drops fast. So why is PointNet so robust to data corruption? Let's try to understand the point by some visualizations. The visualization tries to answer the question. Recall that our global feature vector is a 1024 dimension. I'm asking, if I'm dropping one of the n input points, will this global feature change? In other words, we want to test which input points are contributing to the global feature. Now here is the set of results. The first row is the point clouds of the original shapes. Now if we want to drop some of the points, the feature will not change. In fact, for those points, if we drop them, the feature that will change will be called the critical point set. And we visualize the critical point set. And you can see that it's a very sparse subset of the original set. And in fact, for this critical point set, the number of points will not exceed the dimension before you do the mixed pooling for the point features. Like for example, in an experiment of 1024 dimensions, at the most 1024 points belongs to the critical point set. And for this point, you can actually prove mathematically. Now we can also ask an opposite question. That if we try to add some points, will it affect the point cloud feature? So let's check. For adding what points will we not affect the global feature? So here are the results. And you can see that for the upper bound set, it will give the same global feature as the original shape. In fact, for any point set that's including the critical point set and included by the upper bounded set, it will be the same global feature. So we can even conduct a further analysis on the features in the first layer. Recall that for each of the point XYZ, it is transformed by an MLP, which we call it the H network, and assume that the last layer of this MLP is a ReLU. So we can check the output after the ReLU operation. Suppose that there are 1024 dimensions of this layer after the ReLU, and we check the dimensions one by one. So for each of the dimension, let's check what points will excite it. Practically, we will change the location of the XYZ point and check for a point at different locations whether the certain dimension will be excited or not. And then we'll be able to get the visualization as here. For example, here is one of the dimensions. And you can see that if the XYZ, the input point, is within this gray region, then the dimension is excited. On the other hand, if it's the empty space, then this dimension is 0. And therefore, you can see that for each dimension, as the output of H, it's actually learning an indicator of whether a certain region in the space there is a point or not. So you can think that the first layer of PointNet learns to partition the space in an adaptive manner, and just to test whether there's a point in it. PointNet is a basic building block for a lot of neural networks processing point clouds. The very simple design of a PointNet gives the advantage in interpretability and some good robustness properties. However, there are also certain limitations of the PointNet architecture. And we can see the point by making a comparison with the classical convolutional neural networks. We see that in PointNet, every point is transformed to become a high-dimensional vector, and then the information on entire shape is pulled altogether. And therefore, there lacks the local context for each point. And that limits the ability to capture repetitive patterns. And the second limitation is that the global feature depends on absolute coordinate, and that will affect its generalizability to the unseen scene configurations. So for the next, I'm going to introduce some follow-up work to address the limitations. So next, let me introduce a few works that tries to address the local context problem and the translation invariance problem. So PointNet++ or PointNet v2 address the problem by designing a multi-scale PointNet architecture. It starts from endpoints. Here, the example is assuming that the points are on the 2D plane, but it works similarly in a 3D space. So it will sample a subset of points as the anchor points. We could consider using farthest point sampling to get the anchor points. And then, for each of the anchor points, we will find its local neighborhood. So local neighborhood forms a small set of points. And then we will subtract the coordinate for each of the point in the local neighborhood by the position of the anchor point. And this gives us a normalized local set. So we could apply PointNet in this normalized local sets and get a high-dimensional feature of the group. So that finishes one layer of applying PointNet locally. And then we have a smaller set of points, but each point has not only the XY coordinates, which are the anchor points, coordinates, and also the features of the group. So we could use XY coordinates to group the points, and each point now is the high dimensional point, but we can still apply a PointNet to aggregate information. So we can repeat this process by sampling anchor points and find local neighborhoods and use a PointNet to abstract the local neighborhood until we have a global feature. This is called the set abstraction operation. Another idea to address the local context problem and the translation invariance problem is to view the point cloud processing problem as a graph processing problem. For example, you could consider to build the k nearest neighbor graph and then treat all the nodes as the points, and for every neighboring points you add an edge. So you could use graph convolutional neural network to process the points. Representative works include like DGCNN and the relationship convolutional neural network. Now, a third idea considers to build a local neighborhood in a way that is volumetric. So it will try to build a coarse volumetric form of the input. So for each of the cell, it includes a number of points. And locally, you could use PointNet to extract a local feature. So then, for the 3D volume, for each cell, there is a feature vector. And you can just treat it as a 3D volume in each cell with a fourth dimension as the channels of features. And then you conduct 3D convolution. This becomes popular in some applications that require extremely fast computation, because here the neighborhood relationship is by the regular grids, which can be computed very fast by hashing. Another fundamental challenge that people often talk for point cloud learning is the rotation equivariance problem. So why we are interested in rotation equivariance? Well, this is because for the deep neural networks that we have trained, they are just fitting the input patterns. And in a lot of data sets, 3D data sets like ShapeNet, the shapes in it are aligned by orientation. And therefore, if you are doing shape classification or origination in the wild, the shape is not the same oriented as the shapes in ShapeNet, it will fail. It is just an example. And one way to address the problem was to use data augmentation. But data augmentation is very costly, and also it will reduce the effectiveness of the network by taking a lot of its capacities. So how can we address the rotation equivariance problem without doing data augmentation? There are many good works of this line, and here I'm just going to pick one of the representative works to introduce, which is called the vector neurons, or VN. This is a general framework that is simple but quite versatile, improving the ability of many existing point cloud networks. It works by introducing a number of building blocks for building equivariant networks, like linear layer, the nonlinear layers, the pooling layer, the normalization layer, and also the invariant layer. And therefore, for your existing point cloud that is not point cloud network is not equivariant, you can replace your layers by those newly proposed ones, and then immediately you get a equivariant network for free. So what is the key innovation of vector neurons? Is in representing the neurons. In deep learning, we are very used to have each neuron as a scalar, and therefore the feature vector of a shape is a 1D array. For a layer, for example, the fully connected layer, it becomes that we try to connect neurons that are the dimensions of the vectors. And vector neurons extend the concept of a neuron as a scalar to a neuron as a 3D vector. This is a bit like complex numbers, but complex numbers are like 2D vectors, but here the vector neuron is using a 3D vector for each of the neuron. Therefore, in the classical neural networks, the feature vector is the 1D array, but for the vector neurons, the feature vector is a feature vector list, as in the paper, and which is a 2D array. And then we are building the fully connected layers between two vector neuron layers. We are adding connections to link the different 3D vectors in the layers. In vector neurons, to achieve the equivariance of the nonlinearity, that's a bit tricky. Now let's see how we could transform the classical ReLU to become the ReLU nonlinearity with equivariance. Assume that we have a point cloud and there are endpoints. For each of the point, it's represented by C neurons, and note that each of the neuron is a 3-dimensional vector. And therefore, for the vector list representation of the point, it's a matrix V, that's 2D. Each row corresponds to a neuron, and each column corresponds to one of the 3 dimensions. We assume that this V is C by 3. Let's describe how we achieve the ReLU nonlinearity for such a vectorized neuron representation. So for the vector neurons, each vector plays as a complex number, although not exact complex number. So when we do the ReLU operation, there is an idea that it will try to truncate the value along certain orientation, but not along every orientation. And therefore, for here, we will learn the direction that the nonlinear transformation will take effect. We introduce 2 matrices, W and U, each of which is 1 by C. Recall that C is the number of the vector neurons. So W and U will transform the vector neurons for a point to become 2 3-dimensional vectors. Then, if the Q and K has angles less than 90 degrees, we will just keep the learned feature Q. Otherwise, we will find the projection of Q onto the K direction and remove the component. Here, the operation to remove the component projecting to the direction is the same as how we did for ReLU, that we truncate the value below 0. For other layers of a convolutional neural network, the vector neurons paper gave the surgery to make them equivariant. The vector neurons paper shows how to translate the original point net to an equivariant version of the point net by replacing the original MLP layers H by the equivariant MLP layers F and the original pooling operation by the equivariant pooling operation. The paper also showed how to transform another graph neural network like point cloud learning framework, which is the DGCNN, to become the equivariant version. It just uses the proposed new edge convolution, which is equivariant, and the pooling operation is equivariant to replace the original layers. The paper vector neurons also showed some very nice results on shape classification and other interesting applications like surface reconstruction. Let me just show you some results on the classification. On the benchmark model net 40 for shape classification, the vector neurons networks shows very good robustness to unseen rotations. If you are interested in more results, especially the implicit function prediction, you can refer to the original paper. Next, I'd like to discuss a bit of some latest architecture design tricks. Because transformer is so popular, there are also approaches to consider introducing transformers to increase the attentionability in point cloud analysis. In fact, you should not be surprised by seeing those transformer style works to model point clouds, because point cloud itself is just a set, right? So each point can be thought as a token. So in the community of sequence modeling, there are different ways to consider the connectivities between or among the tokens, right? Like the convolution gives very local receptive field, and recurrence gives gradually increased connectivity, and self-attention builds a fully connected connectivity among the tokens, and then causal attention considers some temporal, considers the error of the time. Okay, so in order to achieve self-attention, a very powerful tool is the transformer. There are many works in the past few years that tries to add transformers to like point cloud learning, and I just listed some. I'm sorry that I'm not able to enumerate them all. Okay, so here I'm going to illustrate the idea using a work that's called the PCT, the point cloud transformer, published on CBM. I chose it because the paper is pretty comprehensive in illustrating the possible ways to add transformers to point cloud analysis. So here I will pick two ways to model the attention between the points. The first is the sentence modeling style. While in the paper PCT, point cloud transformer, it says that this is a naive way of modeling. So, so we have a point cloud, right? Assume that there are n points, and using the MLP as we did in point net, we'll lift the point to become a DE dimensional point embedding. And then we could actually introduce three matrices, the WQ, WK, and WV. And the three matrices are linear transformations to compute the query, the key, and the value for each of the point. And then you could just do as what you did for image analysis to achieve the self-attention using the query, the key, and the values. Note that here the key advantage is that you're able to attend to very remote points in space. And then one of the issue is that now if your point cloud has a lot of points, then this means it's huge computational complexity. Then the paper also introduced an idea to progressively achieve self-attention among the points. So just to read what the paper says. It says, to draw upon the ideas of PointNet++ and DGCN to design a local neighbor aggregation strategy, the neighbor embedding, to optimize the point embedding to augment the PCT's ability of local feature extraction. So there it introduces the hierarchy and the local context. Okay, we just introduced some backbone point cloud networks. And in fact, there are some issues like the challenges brought by the non-uniformity of the surface sampling. But for the sake of time, we don't have time to discuss it in depth. And next, let me show some of the applications of the backbone point cloud networks. They are the 3D detection and the 3D generative model. So what is 3D object detection? Well, in our setup, the input is usually the sensor data of a 3D scene, like the RGB images, like the depth maps, like the range map from the radar. And then we want to localize the object in it and identify the semantic classes for each of the objects we're interested in, and then even estimate the pose of the objects, for example, by orientation and location. And a lot of times, we might want to complete the bounding box of the object for the part of an object that are even invisible. So let's be concrete, and it's very suitable to use point clouds to represent the input of the 3D scene. For example, there are n points in the point cloud, and therefore for each point is a 3 plus c vector that the dimensions represent the x, y, z, or features like the color from the RGB camera, or like the intensity for the surface reflecting the radar waves. Then for output, we prefer to use upright aligned 3D A-model bounding boxes. Like if we predict the bounding boxes, there could be information about where the object is, the size of the bounding box, and the orientation of the bounding box. And then for each of the bounding box, there could be the semantic class for the object in it, and then a score of the bounding box that represents the objectness. Now, in general, the solutions to the problem can be grouped into 3 families. The first family is image-driven, which leverages 2D object detectors on the input RGB images. And then the second family is called the dimension reduction, which mainly use the bird's eye view detectors but are 3D native. And then the third family leverages the sparsity in 3D. Let's explain them one by one. So let's start from the image-driven 3D object detection. As we are capturing the point clouds, it's very often, like in autonomous driving setup, that we will have the registrations between the input views and the point clouds. Like for the pixels, we know which point in the point cloud it corresponds to. And then it's possible for us to leverage the mature 2D object detectors to propose objects from the RGB images. Like we could have the input images and point clouds registered, and then run some 2D object detector on the image. And that gives you a 2D bounding box. For the 2D bounding box, when it's lifted to 3D, that corresponds to a view frustum. The view frustum will crop out a certain portion of the point clouds. We remove the points not belonging to the frustum. So within the frustum, there are the points that belongs to the object of interest there are also points that belong to other categories. And particularly, I want to mention that for the 2D object detect step, not only we have the bounding box, but for every box, there's information of the object category that the bounding box should cover. And therefore, within the frustum, we try to segment the points that belongs to the object category of interest. So here we basically solve a binary mask prediction problem. Like for every point, we predict whether it belongs to the object interest or not. And that will allow us to remove points irrelevant to the object interest. And for the very next step, we will have fewer points, and we will predict the A model bounding box. So what is A model bounding box? That means the bounding box cover the entire object, including the invisible part. So for the second step of instance segmentation and the third step of A model bounding box prediction in the work of frustum point nets, they're both done by the point net. And therefore, the idea is the point nest for the data-driven object detection in the frustums. The method is very effective in practice. Let's take a look at this key result for detecting vehicles and cyclists and person. Okay, so we have the 2D bounding boxes. Then for each of the 2D bounding boxes, it corresponds to a 3D A model bounding box. We can see that the orientation of the objects are well predicted, and a lot of times they are just a predict from just like a dozen of points. And besides, it's very good at predicting or regressing the A model bounding box. Okay, so from the success of frustum point nets, we learned two key lessons. The first lesson is representation matters. To illustrate the point, we have a baseline result that's from the instance segmentation on the depth maps. So given the depth map, we can actually use mask RCN to perform a per pixel semantics or instance segmentation and pop it up in 3D. As we can see, it's actually very difficult to handle the boundary very well. Because for those points, although they are very distant in 3D, on 2D image space, they are very close. So it's difficult for CNN to handle it well. On the other hand, the point net solves the segmentation problem natively in 3D, and therefore is able to get a much cleaner segmentation results. And the second lesson we learned is that coordinate transformation really matters. Okay, so in this work, we actually introduced the 4 coordinate frames. The first, the camera coordinate frame, which is the frame for the LiDAR to capture the point cloud. And then once we have the object located on a 2D image, we build a frustum. We actually could build a frustum coordinate by aligning one orientation of the frame to be at the center of the frustum. Then for this approach, it addresses the translation environment for the object captured in image space. And then when we have the crop the points belonging to frustum, we can compute the center of the points, which is likely to correspond to where the object locates. So we can translate the frustum coordinate so that its origin aligns with the center. So that allows us to address the alignment of object vector. And then point net has a spatial transformer architecture that further aligns the orientation of objects. So from the right table, we can see that by introducing those additional alignment or the connectalization by the coordinate transformations, we're able to boost the performance by quite a large margin. So to summarize, we need to respect and exploit the 3D. The representation matters because we use 3D representation and 3D deep learning for the 3D problem. And canonicalization of input matters because it reduces the need for data augmentation and also helps to generalize to unseen scenarios. So to achieve this goal, we exploit the geometric transformations in point clouds that are unique in a 3D space. And note that in a 2D space, we're not able to achieve the real 3D transformation. But although the frustum point nets is very powerful, there are certain limitations because it has hard dependence on the 2D detectors. And thus, it will miss objects due to strong occlusions in the 2D views, or unfavorable limitation conditions that causes unclear RGB image, or like some difficulty in detection in RGB image. And also note that although we have provided semantic category for each of the bounding box, in fact, when we build the frustum, we're only locating a single object within the bounding box. Like if you have a few people walking together, then if your 2D bounding box is not so accurate, inside the frustum, the point net will have difficulty in associating the points and predict the instance segmentation. And therefore, we seek for solutions that is more 3D native, that we want to get object proposals from 3D point clouds. So the second family approach addressed the problem by the dimension reduction. Okay. The basic idea is to consider the bird's eye view 3D object detector. And in fact, those approaches will try to convert the 3D learning problem to a 2D learning problem. But I'd like to emphasize that the key difference for here to convert the 3D problem to 2D problem than the previous approach is that for the image-driven approach, it'll leverage the perspective transformation to get a 2D image from the 3D. And then the perspective transformation will have distortion effects. Some distances will get longer or some will get shorter. Whereas for here, we want to respect the 3D more and use the way to convert 3D to 2D without the distortion. Like for an earlier work in CGPR 2016 by Qi et al., we proposed to use elongated kernel to convolve the 3D volumetric space. This elongated kernel that is small in the width and height dimension, but thick in the depth dimension, could gradually transform a 3D volume to become a 2D pseudo image. And then we can use your favorable 2D image detector or like a segmentation algorithm to get the objects. A more modern attempt is the point pillar work. So this is suitable for autonomous driving setup. To consider there's a street view, right? And then we assume that the x, y, z is a coordinate of each point, and z corresponds to elevation or height direction. So the method will discretize the xy space to 2D grids. So for each 2D grid, we will build a pillar that includes all the elevations. So the pillar will cover certain points inside it. So for the pillar, we will use a point net to process the points inside it and get a per pillar feature. For example, you get a 64-dimensional feature. And then this input view from the bird eye view this point cloud from the bird's eye view is converted to a pseudo image. Like here, for the pseudo image, you could use your favorable object detector like the SSD 2D detector to predict the objects and predict orientation bounding boxes. So the significant advantage of the bird eye view approach is that it has good inference speed and also very simple to implement. Now take a look at the figures on the right. They are the plot. The x-axis is the runtime, which is in terms of hertz, and the y-axis is the performance. For each of the dots with a label that represents an approach. The PP represents the point pillar approach. And we can see that point pillar is able to run at a good speed, but also with decent performance. There are also certain weaknesses of the approaches that they usually assume a projection plane. And this prevents it to work well for complex 3D scenes. For example, in 3D street view, usually within an XY grid, the elevation, the points concentrates around a certain elevation. Whereas in indoor scene, the points could be very much evenly distributed at different elevations. And therefore, the aggressive compression of the dimension is not such a good idea. Okay. So for complex indoor environments, it's probably more suitable to consider leveraging the sparsity in the 3D space. Well, although objects lies in the 3D space, a surface is actually just a 2D manifold. And from the perspective of the 3D, it actually just occupies very limited volume. And therefore, we call it as a sparsity, and it could use the sparsity-aware backbone architectures to design good networks. And this is more suitable for like the complex indoor environments. Now let's use some example to illustrate the sparsity. So left is the image, which is a dense 2D pixel array, and the right is the visualization of points. And you can see that they are only on the surface. So that only occupies a very limited space in a 3D. Now representative work of this family is the PVN 3D work. It assumes a pair of input, the RGB and the depth map, which are registered with each other. And then it will use a convolutional neural network to process the image input and get a per pixel feature. It will also use the point net to process the point cloud to get a per point feature. Now because we have pixel and point registrations, we're able to augment the point features by the pixel features. So for each of the point, there will be the feature to describe local geometry and also the appearance. And then for the approach, it uses a MLP to predict a per point semantic label, like the semantic category the point belongs to. The method for each point also predicts an offset that is from the point to the center of the object it belongs to. So then for each point, it has a prediction of the object center and the semantic label. And we could vote and cluster and then got instance segmentation of the objects in the scene. The pipeline not only gets the instance segmentation, but also wants to predict the orientation of the object. To achieve this goal, it uses the 3D key point detection approach. The method assumes knowing the key points of each of the object in some canonical space. And for each of the object in the scene, it will also predict the location of the key points. The prediction of the key points are again using the offset prediction approach, and then also by voting. So with the predicted key points for the object in the scene and the known key point locations in the canonical space, it's actually able to vote and cluster and solve the relative transformation R and T from the canonical space to the camera frame using Umiyama's algorithm. And therefore, it's able to predict the 6-degree freedom pose of each object. Another example is the more recent work called CAPTCHA. CAPTCHA tries to achieve the part-level object pose tracking for rigid or articulated objects. For more of the details, you can refer to the original paper. Okay, next, I'm going to talk about another family of problems that are generating point clouds, or the point cloud generative model. So there are a few ways to build generative models. And then for each of the approach, there are certain works for point cloud understanding as well. Now, the first family approaches use the variational autoencoder style methods to generate points. As we know, for VAEs, right, they will use the data itself as the supervision. This is like predicting the self. Like for image reconstruction, for image generative models, it will try to reconstruct images. And then for here, we will try to reconstruct the point cloud. Now, compared with the image setup, the key challenge is how do we build a loss to compare two point clouds? So we need some kind of point set distance. Now, in this early work to describe a point set generation network. It proposes to use the chamfer distance and earth mover's distance as the loss function. The key idea is to solve the point correspondence problem between the ground truth point cloud and the predicted point cloud. And note that for this process is part of a network, but is justified to be differentiable, and therefore we can build a variational autoencoder style generative model for point clouds. And it's also possible to use generative adversarial network style architecture to build a generative model for the point cloud. So in the early work, learning representations and generative models for 3D point clouds, the authors used the fully connected layers as the generator, and then used the point net as the discriminator. On the right side, you can see some of the representative generated results. As we can see, the general shapes looks reasonable, but the details are a bit not ideal. It has been a big challenge to consider improving the local details of the results for like GAN style generative model of point clouds. But there are some difficulties. Okay, basically for almost every point cloud GAN in field, they use the point net as the discriminator, not even point net plus plus. But we do know that the point net focused on the general shape, but not the details. As we mentioned when we introduced the point net in the previous section, point net has the critical set and the upper bound set. And then between the two sets, they just are the same for the point net. And therefore, it's really important to use a discriminator that would give better supervision to the generator. However, we find that in practice, it's pretty tricky. So because for the discriminators stronger than point net, like point net plus plus, they are usually very sensitive to the differences in point cloud density than the shape. What I mean is that, like for this generative adversarial network, the discriminator is responsible for telling the difference between the fake data generated by the network and the real data. But for point net plus plus or DGCN, those stronger networks, they tend to attend to like the density patterns rather than the shape of the points. Okay, and usually they are just too powerful for the generator to improve the shape. Like in the paper that was by Wang et al., they show some of the visualization for using different variations of point net and the point net plus plus and DGCNN for the discriminator. As we can see that it seems like only variance of the point net could work. Okay. Through the experiments of my own group, we have one conclusion that we should try to avoid using batch normalization, because for the input of the point cloud of the point net, they are the coordinates, and the batch normalization will cause some very tricky scaling issues. Okay, so to summarize, it is an open problem to find point cloud discriminators better than the point net. And if you're interested in the problem, I encourage you to have a try. A third family of important family of generative models is the diffusion model. And diffusion model has also been applied to point cloud very recently. So in this work, it tries to use the denoising diffusion model to transform the Gaussian noise, the point clouds from the Gaussian noise to some meaningful objects. It basically applies point net repeatedly to move the points to the right position. And the paper also shows that it's possible to generate the point cloud by diffusion model conditioned on an incomplete point cloud. So it's able to do the point cloud completion. Take a look at the following results for diffusion model-based point cloud completion. The first column is the partial point cloud input, and then the follow-up columns are the completed point cloud. You can see that the diffusion model works pretty well and it's close to the ground truth. So just now, we have introduced two major applications of point cloud for object detection and for building generative models. Next, I'm going to talk about a topic that is to connect point cloud to other type of 3D representations, especially the surface. So here's the formulation of the problem. We assume that we have the point cloud as input. The point cloud could be the points with XYZ coordinates, or could also have normal information. And we'll see that for this application, normal is very important. And then what we want to get is a mesh. Okay, it's a mesh of the object surface. So basically, we would like to recover the latent connectivity information between the points. In general, there are two families of algorithms to convert the point clouds to surfaces. We call one family of approaches as the explicit methods. So the idea is, given the points, try to connect the points to become edges and faces. And then there's a second family that is indirect. We call it implicit methods. So from the point cloud we have, we try to predict an implicit function that corresponds to the surface of the object. We know that the implicit function is a function that the surface is the level set of it. Well, in practice, it's very often to consider using the signed distance field, or SDF, as this implicit field function. So given the implicit surface function, we could actually extract the surface by, the isosurface by algorithms like Martian Cube. Next, let me introduce them one by one. Well, the first family algorithm is the explicit methods. I think it's best to illustrate the general idea by an algorithm called ball pivoting. So here is a 2D example, and you can see that, you start from like a corner of the set of points, and then you have a ball of a certain radius. And then you try to roll the ball, and while you're rolling the ball, it'll hit the points, and then it'll go around the surface object, and this will in the end give you a closed polygon. For the 3D surface reconstruction, it's similar. It's just like the ball will roll and then will give you the triangles. Now, it's obviously, it's pretty obvious that it's very tricky to set the radius of this ball, right? When it's too small, is likely to create a lot of holes, but when it's too large, it's ignoring some structures at a small scales. Well, it's not even hard to decide the radius of the ball. Sometimes it's just impossible. Like, take a look at this example. We have these points, and in our mind, we tend to interpret as two circles, right, or ellipses. But in fact, the gaps between the points for the same ellipses is larger than the distance between the two ellipses. And therefore, if you run the ball pivoting, it's very likely to connect the two spheres, two ellipses or circles together. And there's just no row value available allows us to separate them. So why do we humans are able to learn to see the separation? Because in our mind, we have some geometry priors. Okay, this example motivates the need to consider learning approach for the point cloud to surface conversion problem. Now, here are some real examples. If we apply the ball pivoting algorithm, we will get the surface reconstruction from point cloud as the top row. Okay, so in fact, for this chair, we see that between the slates, there should be the hollow space, right? But for the reconstruction, we're not able to see them, although we actually see some small dents. Okay, and then another example is this chair, right? This chair with the back. On the back, between the slates, there should be the empty space, whereas the algorithm is not able to reveal it. But we can use learning-based approach to address the issue with much better quality. Here's the result by a paper that uses intrinsic-extrinsic ratio to reconstruct the surface from the point clouds. And you can see that we are able to separate the slates here, separate the bars at the back, right? And for the surfaces like the monitor on the screen, there are much fewer small dents. So how did it do? It actually uses a 3D geometry concept that is the intrinsics or geodesics. So what is the geodesics? Now consider this surface, right? And there are the surface of this chair. There are 2 points on the surface of the chair. Well, you could easily measure their Euclidean distance. See, you draw a line segment between the center of this 5 star and this dot, right? And then the length is the Euclidean distance. But the Euclidean distance is not along the surface. Now, consider if you do have access of the connectivity information of the point cloud, then there will be the surface, and then on the surface, you can actually try to find the shortest path from the center star to the center of the ball, right? And the length of this shortest path is called the geodesic distance between the surface points. So for our learning-based approach, at training time, we have the points sampled from the meshes, but also we have the ground truth mesh, assuming this is known to the algorithm. And then, in fact, we're able to predict the geodesic distance between points on the surface. Okay, so we have introduced the idea of the intrinsic or the geodesic distance. And then next, we're going to introduce an algorithm that leverages the intrinsic distance or the geodesic distance to reconstruct the surface from point cloud as well. Okay, so let's define a quantity which is called the intrinsic-extrinsic ratio. Now, given 2 vertices u and v on the surface, this ratio is defined as the geodesic distance between the 2 points and the Euclidean distance between the 2 points. If we define this quantity in this way, what shall we see? So here is a visualization of this ratio. Now, given this point cloud of the chair, then we will choose 1 point on the back, which is actually on the bar. And then we compute within this window, we compute the geodesic distance from this point to any other point. And this is the visualization. That's the geodesic distance from the point to any other point. Blue means the distance is small, and yellow means the distance is big. Okay, and you can also compute the intrinsic-extrinsic ratio between this point and well, for well, pair of points of this one and any other point at the back. Okay, and we also use the color to visualize this ratio. We can see that for this part, the ratio is close to 1. And for this part, the intrinsic extrinsic ratio is very big. So basically, if the ratio is close to 1, you can say, well, the 2 points are well, on the same surface. Okay, otherwise, it may not be, may not, be able to be directly connected. Okay, and in fact, that was for a pair of points. For a triangle, you can also define the intrinsic extrinsic ratio, and the ratio is defined by, well, the sum of the geodetic distance between any pair of the 3 vertices divided by the Euclidean distance between any pair of the sum of the distance between any pair of points. Okay, so if the point UVW is close enough, we should also check its IER ratio. If this IER ratio is also very close to 1, like within 1 plus epsilon, then it's likely that we should connect them together to form a triangle. Now, if this ratio is very big, even if they are close, you shouldn't connect them. Okay, so, well, I just mentioned that you can use a network to predict this DG, the geodetic distance, but what really matters is this ratio, right? And therefore, in practice, we learn a neural network to predict the ratio, or predict whether the ratio is below the threshold. Okay. So this intrinsic extrinsic ratio for triangles allows us to connect the points to form the surfaces. Like here, we use a greedy algorithm to connect triples of points into surfaces following the intrinsic extrinsic ratio, and we get this desk with descent looking, well, although there are still some issues of the host. But then for the k-nearest neighbor that we just connect nearby points to become triangles, that actually has much larger issues. Okay. So these are the explicit methods that would directly connect the points to become the surfaces. And next, let me introduce the implicit methods. And the first convert the point cloud to a implicit field function, and then we extract the isosurface of the implicit field function as the surface. Okay, so what is an implicit field function? Okay, in fact, here this is signed one, and we assume that we have a watertight manifold of some object. Okay, the surface, and then for the points inside the surface, okay, because the watertight you can decide inside and outside. Now for the inside, we say the function value is less than 0. And then for the outside points, the function value is greater than 0. And therefore, the 0 level set or 0 isosurface is the surface. Okay, so well, you can see this rabbit. Inside is blue, that means it's negative value, and outside is red, that means it's like positive value. Okay, so it's very often that people try to put the sign or build the sign distance field as the implicit field function. Now here, it just means that for the magnitude of this function, either interior or exterior, we make it to be the distance to the surface. Okay. So having introduced the concept of implicit field function, we can introduce the skeleton of the implicit meshing algorithm. There are 2 basic steps. The first step is to estimate an implicit field function from the data. Here the data is the point cloud. And then we extract the zero isosurface. Usually we need the normal information to build the watertight meshes. This point is very different from the explicit methods that we don't really need the normal information. It's also worth noting that obtaining the consistent normal orientation is non-trivial. Okay, and in fact, there are special cases like the Mobius strip. There just does not exist a consistent normal orientation. But here we're talking about the watertight meshes, like for this family of approaches. Well, theoretically there is the consistent normal orientation, but to achieve the consistency, it's actually quite a global property, and therefore just having the normal estimation from fitting a plane locally will not guarantee the consistency. And in fact, there exists learning-based approach to predict the normal so that they are consistent in orientation. But for the sake of time, we don't discuss it. We just assume that if we have the information. Now, if we have the information, we can actually use a neural network to convert a point cloud with the normal information to become approximate implicit field function. So typically for the points, because they have normals, you can move the point along the normals or the opposite direction on the normals, and then you will get some different points, right? Now these points, when they're along the normals, you give them the positive sign, and then when they're along the negative, the normal direction, you give a value of the, negative sign, and you can just use the neural network to take move the points as an input, which is x, y, z as the input, and then predict either the positive distance or the negative distance, depending on you move along the normal or not. Okay. In this way, you'll be able to train a neural network. And in fact, it's the way that you'll learn neural network to overfit a single shape. Okay, so if you want to have a kind of like implicit field function for a family of for a collection of shapes, you can also consider to use the code of the shape. And then you will feed the code of the shape and S, Y, Z together and use MLP to predict the sign distance field value. So after this step, assume that you basically have obtained a sign distance function for the corresponding point cloud. For the next step, we need to extract zero isosurface. How did we achieve this goal? So we will first decompose the space into volumes, and then at all the vertices, we will evaluate the sign distance function. So then you have a 3D volume. At the vertices, you have positive or negative values. And then you can run an algorithm that's called the marching cube to extract the surface. And note that if you want to get a high resolution surface, usually you need to make the 3D volume quite dense. Okay, so these are the approach that assumes consistent normals are given. Now, what if you don't have consistent normals? It's not impossible to address the setup. There's a process sign agnostic learning approach for getting the sign distance function. So the method is able to take a point cloud without normal information and obtain a unsigned distance function. And then it will be able to convert this unsigned distance function to a signed one. And then for this approach, you actually need to know just the one point, which is in the interior of the surface. So this single point in the interior helps you to identify the sign. Okay, so just now we introduced an algorithms to convert point clouds to surfaces, right? And next, we're going to introduce how point cloud could be used to achieve inverse graphics, or more explicitly, how to achieve radiance field estimation using point cloud. The original NERF model optimized the scene by taking hundreds of multi-view images. Along each camera array, NERF samples hundreds of shading points, and even most of them are in empty regions. Now, during shading, NERF encodes the entire radiance field as MLPs, which take the shading location, the ray direction, and output RGB color and the volume density. Now, since NERF is unaware of scene geometry, its shading sampling is inefficient, and using a single network to encode a scene also makes it hard to scale and converge. Now, to address the issues, Point NERF leverage multi-view reconstruction methods to quickly reconstruct a point cloud. Then it installs neural features on each point and obtain a neural point cloud. During rematching, Point NERF skips all the empty regions and only computes shading near the geometric prior. This efficient sampling strategy differentiates Point NERF from previous NERF models. Once the array arrives the nearby regions of the geometric prior, Point NERF queries k nearest neural points and uses the relative positions of their point features and the redirections at input to compute RGB color and volume density. So the efficient sampling strategy, the radiance field localization, the flexibility of points help Point NERF to achieve fast convergence, high rendering quality, flexibility for editing, and strong scalability for large scenes. So to get the shape prior from the 2D images input, a multi-view reconstruction network generates depth images and combines them to a point cloud. Well, the method can also use an existing point cloud. Then, another feature extraction network projects the image features onto the points and finally create a neural point cloud. So during optimization, Point NERF only samples the shading points near the shape prior. For example, XA, XB, and XC. The k nearest neural points are queried, and the features are aggregated according to the relative positions to the shading location and the scale value and point confidence. The MLPs use the aggregated features to generate view-dependent colors and the volume density. After aggregating the radius along the array, we can calculate the rendering loss between the generated and the ground truth color on the pixel. Okay, and then the gradients will optimize not only the MLPs but also the point features. Now, since the radiance field is distributed as point features, a local representation without the limited resolution, Point NERF can encode more fine-grained details and high-frequency information, and thus finally achieves better rendering quality than NERF, sparse voxel-based NERF methods, and other point-based rendering methods. By leveraging the shape prior and image feature projection, point nerve also achieves a convergence speed which is 30 times faster than nerve. In the end, let me introduce some methods to connect point cloud learning and the language. So pre-trained vision language models cover a broad set of visual concepts and use natural language to refer to the learned visual concepts. For example, CLIP includes a text encoder and an image encoder and is trained with over 400 million image text pairs using contrastive pre-training. So the pre-trained vision language models have already transferred to many 2D vision tasks like zero-shot image classification and text-guided image synthesis. Now, 3D deep learning suffers from severe data scarcity, especially labeled data. Can we leverage the rich knowledge and the visual concepts from the pre-trained vision language models? Now, the key is to build a bridge between the 3D data and the 2D images. For example, we can render or project the 3D data onto 2D images. And this could be achieved by renderer. If you want to backpropagate information from the image space to the 3D space, you can also consider to use a differentiable renderer. And if you have the RGBD images, well, it's even simpler because the 2D pixel is already naturally associated with the 3D point. So there is recent work that's called point clip, which understands the point clouds using the clip. The method is kind of straight, that it first project the 3D point clouds onto the 2D. And then, well, because 2D images are connected with the language by the clip, you are able to connect language with 3D. You could do zero-shot classification, like you could directly use the pre-trained visual language model to predict. Or you could do few-shot learning, that you could fine-tune the classification head with a few 3D point cloud data with the labels. There are also works that tries to achieve like text-driven shape generation. So given a sentence or some text description about what you want to generate for the 3D shape, you try to generate a shape, and then you could use the clip feature as a discriminator and check like whether the embedding of the shape that you generate will match the image embedding for the reference that you provide. So this similarity score could be used to supervise the optimization of the shape. Okay, so today we have introduced many point cloud learning algorithms, including the backbone point cloud networks, like how to use point cloud to achieve 3D object detection or part segmentation, and the 3D generative models, and how do we use learning to convert a point cloud to surface with the basic geometry priors, and how we could use point cloud to achieve inverse graphics like the nerve, and even how can we connect point cloud to other data modalities like language. But I really want to say that learning on point clouds actually is such a popular field that there are many, many more problems that we have not covered. For example, there's a problem that's called the consolidation, or like the super resolution of point clouds. And then given a point cloud with the normals, how are we able to predict the normals that have the consistent orientation, right? And then how do we achieve like the completion of the point cloud from only a partial one? Well, we very briefly mentioned in the diffusion model part, but actually for this problem, there are also a lot of ideas that are very interesting. And then we, well, skipped a very important problem, which is the path discovery. And there are a few different ideas, like use bottom-up grouping, or like use correspondence-based approach, or like even to connect the 3D point cloud understanding to languages. And then there are the problem of self-supervised learning. And in the past recent years, like there are the work of like consider contrastive learning on point clouds. And in fact, we also didn't have the time to cover like transformers for point clouds, which is very helpful if you add self-supervised learning to it to train. And then there are the works that will consider to deploy point cloud learning algorithms on real machines, like all hardwares. And then it's important to accelerate the inference speed, like to consider quantization or to consider network compression. And then there are the problem of studying the adversarial robustness of point cloud learning algorithm, and many more. So for the sake of time, it's not possible to cover them all, okay? Well, if you're interested, I encourage that you check the literature from like CV, CG, machine learning, robotics, all these communities. There are a lot of point cloud learning algorithms. So I'm also teaching a course at UCSD, which is a graduate level course that covers a broader set of topics in better depth. If you're interested, you can go to my homepage and find teaching and go to the ML meets geometry course. And well, all the slides are public. So if you're interested in the general direction of point cloud learning, welcome to join this stream. There's still a lot to explore. And thank you very much for listening to my presentation today.
Hello, everyone. So due to some technical issue with joining Zoom, and the Q&A session will be done in the room voice channel 2 on Discord. Please ask the questions there. You can also type questions in the channel for this graduate school deep learning on point cloud. I see. Oh, I see someone join. Okay.